Hello, good afternoon to all of you, and welcome to Unacademy, one-stop destination for English medium civil services aspirants. Welcome to this special marathon session where we are going to cover the entirety of the portion of geography relevant for your prelims examination. Now, when it comes to geography, there are various different classifications: world geography, Indian geography, physical geography, and so on. So, here we are going to cover in its entirety, starting from the portion of physical geography, where we shall be having a comprehensive coverage of topics associated with geomorphology. Then we are going to have a comprehensive coverage of climatology, what is relevant for your examination. Then, in terms of oceanography, what is relevant in terms of ocean currents, the cold currents, warm currents, everything which you can expect a question to be germinated from. That is something we are going to cover. After that, we are also going to cover the portions of Indian geography, including Indian physiography, then Indian climate, that is Indian monsoon, agriculture, some of the major crops, the crop growing areas, minerals, the mineral distribution, and also some of the important things such as rivers, the river tributaries that are there, forest distribution, soil distribution. Along with that, with the help of the maps, we are going to form a kind of a very bullet pointed understanding. And this video in itself will be sufficient for your entire revision for the prelims exam. But mind you, this is a kind of a revision session and a revision video for that matter. Now, having said that, regarding the PDF and the PPTs of the present session, which is going to be held, you can download it from the Telegram link, which is provided here. Now, previously, also in our entire endeavor to help you prepare for the prelims examination, we have been coming up with a lot of videos in order to help you prepare in a better way and in a holistic manner. So, we have come out with the marathon sessions and compilation of Ramsar sites, world climate, the environment ecology throughout the previous year, what are relevant, the species in news, the protected areas in news, the places in news. There are multiple different videos which have basically been put up on the Unacademy channel. All of those videos you can access from this Telegram link along with the PDF. It's you can basically download it. Okay. Now, having said that, what are the topics that we are going to cover in the portion of geomorphology? Geomorphology is where questions are asked, prelims based questions are asked. So, we are going to start with the interior of the earth, then origin of continents and oceans. Here, we are going to cover the continental drift theory, what is the plate tectonic theory, major plates, minor plates, the aspect of convergence, along with the examples of the world map as well. Then, earthquakes and volcanoes, the intrusive and the extrusive landforms created by volcanic eruptions, the Mercalli scale, P wave, S wave, and then the type of landforms which are created. That is the erosional and the depositional landforms created as a consequence of the action of gradation. Everything we are going to cover in the portion of geomorphology. Now, before we initiate the discussion for the interior of the earth, an announcement. So please pay attention for 1 minute. That is, we have come up with a dream project, that is the Platinum program. Now, in this Platinum program, we have a unique way in which we ensure that the students pay attention to the sessions as well. We ensure note making practices as well as live answer writing in the class itself. Also, the kind of hand holding which is required by the students. Many of the times, as a candidate, you feel lost that when to prepare, how to prepare, whether you are able to complete your targets, etc., or not. So that is where you will be mentored by the individual educators as well. So this is for the aspirants of 2026 and beyond. So now the paid classes have been made available, the four paid classes at zero cost. So you can attend that at 7 p.m. on the dates of 13th, 14th, 15th, and 16th of May. That is free of cost, and you can attend that. Okay. Now, having said that, let us start with the first topic, that is the interior of Earth. So, interior of Earth. What constitutes planet's interior? And what is the planet's interior made out of? And this is something which the geographers have always been puzzled about. And there have been a lot of various different sources of information based upon which we get an idea about what is present in the interior. When we talk about the crust, mantle, and the core, Now, how do you get an idea about what is present in the region of the core? What is present in the region of the mantle? How voluminous is the portion of the mantle and the material density and so on? So the information regarding the interior of the earth, that is basically based on the source of information, sources of information. Now, these sources of information that we have, these are basically classified into two parts, that is the direct source and the indirect source, direct and indirect. Now, when we say direct sources of information, what constitutes direct sources of information? So, direct sources of information basically include the volcanic eruptions which occur time and time again. Because whenever a volcanic eruption does occur, materials from the interior they are poured out and they move on the surface. So that gives you an idea about what would have been present in the interior of planet Earth, which has actually emerged out now. Right. So here, basically, amongst the direct sources, one is the volcanic eruption. Now, then what are the other direct source? So in the case of direct source, another aspect is by mining and digging. Now, you see, the deepest mine that we have across the planet is not more than 10 to 12 kilometers deep, and it is situated in the region of Kola Peninsula to the northern part of the Eurasian landmass. Now, having said that, when we talk about this indirect source of or the direct source of information, by mining and digging, you get an idea about how the temperature starts to increase as you move into the depth, as you move into the interior. Also, you get an idea about the fact that how the materials start getting compressed as you move into the interior, the material density, the material nature, all of that starts to change. So mining and digging also forms a direct source. Mining and digging. Now, by the way, before I forget, now the query regarding the breaks. When will you have breaks in this marathon session? So this is going to be a long marathon session, but we are not going to give break every 30 to 40 minutes. So every 2 to 2.5 hours or after completion of every major subunit, we are going to give you a break of 30 minutes to be able to recharge, replenish your energy, and then we will begin again. So the first break that you can expect is after 2 to 2.5 hours. Okay. Now, having said that, we come to the indirect sources of information about the interior. Which are the indirect sources of information for the interior of planet Earth? So, amongst the indirect sources, you basically have the most important of the indirect source of information is what? It is the presence of seismic wave. Whenever an earthquake does occur, whenever there is occurrence of an earthquake, almost immediately there is release of energy waves, which are known as seismic waves. Now, these seismic waves, they travel throughout the interior of planet Earth. Now, how do they travel? Where do they travel? The kind of deviation that they undertake, all of that gives you an idea about the regions through which they have moved. So, the seismic waves, particularly in the case of the seismic waves, the body waves, that is the P and the S waves, they become very relevant to give you an idea about the interior. Then, other than that, you have the asteroids and the meteors, the comets, all of them. Now, these are basically the celestial objects which move around the solar system. Some of them, they fall on the Earth's surface as well when we talk about meteors. Now, we have to keep in mind that the planet's formation in itself, how did the planet get created? Planet was created almost around 4.5 billion years ago as a result of accumulation, what is also referred to as the accretion theory of formation. Accretion refers to accumulation. So that is something regarded as the accretion theory. So basically, what actually happened was that around 4.5 billion years ago, around the sun, you had a series of various different materials, billions and trillions of materials of different sizes. They were moving around the sun. Now, these materials they collided and formed the early planet or the protoplanet. Now, in this particular case, when we talk about the case of the meteors, the asteroids, the comets, all of them, they still represent those kind of materials which would have come together to lead to the formation of planet Earth. And that gives you an idea about what would have been present at the interior of planet Earth as well. So that is where asteroids and meteors are an important indirect source. That is why you will find that there are various different space missions which are launched in order to understand more about these asteroids, meteors, and so on, and the other phenomena associated with them as well. Right? So, asteroids and meteors, they are also important. But other than that, you have the gravitational and magnetic anomaly. Gravitational and magnetic anomaly. That is, how do we get to know about the interior with the help of the gravitational and magnetic anomaly? So we have to understand, for example, that planet Earth is not a perfect sphere. Is it a perfect sphere? Absolutely not. The poles are slightly flattened and the equatorial region is slightly bulged. That is the shape which we refer to as a geoid, isn't it? So that means the distance from the center of the Earth to the region of the poles is slightly different as compared to the distance of the center from the region of equator, isn't it? Because the shape of the planet is like that. It is like a geoid. So that means the gravitational pull which will be extended or which will be felt around the region of the poles will be different as compared to what you experience at the region of equator. Now, measuring this gravitational anomaly gives you an idea again about the material density in different regions. But what about magnetic anomaly? We will study about geomagnetism very soon. What is the concept of geomagnetism? But I hope we are aware that planet Earth behaves like a bar magnet. Now, when I say planet Earth behaves like a bar magnet, it has got a distinct north and south pole as well. Now, why it behaves like a bar magnet? Because of the portion of the outer core as it rotates. Now, we will talk about it in greater detail in the coming few slides as well. But then, how does that magnetic field keep on changing with respect to time? Sometimes you have magnetic reversal as well. So that gives you an idea about what is happening in the region of the outer core. For example, recently you had a change in the magnetic poles around the year 2020. Now that gives an idea to the geologists and to the various geographers that something has changed in the region of outer core. A blob of mass of iron and nickel have shifted from one place to another. That is why there is a change in the case of the magnetic poles as well. So that is where magnetic anomaly becomes very relevant and becomes very important as well. So these are your direct and indirect sources regarding the interior of planet Earth. Now, based upon this set of information, we know that interior of or the structure of Earth can be broadly classified into three basic parts. You have the outer surface, which is the thinnermost, right? The least density. That is the region of the crust. Then inside the crust, you have the thick mantle, which extends up till a depth of 2,900 kilometers from the surface. So that is the portion of the mantle. And the innermost portion is known as the core, right? You have the outer core and the inner core associated. The easiest analogy to understand the interior of planet Earth is the case of a coconut. Now, if you would have taken a look at the coconut, you would have seen that there is the outer brownish shell, which is very thin, but then nonetheless solid. It is brittle, breaks very easily, right? Inside it, you have the white pulp. Now, that is also solid, but is it the same structure of solid that you find the outer brown shell? No. The whitish pulp in the coconut, if you press it, it can be compressed. If you slightly try to put pressure on it, it can be elongated as well, right? So it tends to get deformed as compared to getting broken easily. That is the property of the mantle. And similarly, in the case of the core, inside you also have liquid. In the case of the coconut, inside you have the presence of liquid. And same is the case with the core as well. It's a different matter altogether. That when we talk about the core, outer core and inner core show different property, which we will take a look at. Now, starting with the region of the crust. Now, crust is the outermost layer, right? Now, this is very, very thin. And also keep in mind that it is very brittle. And when I say brittle, what do I mean by that? Brittle basically here indicates that it has got the property whereby it can break very easily. Now, why is it that it is very brittle? The reason for the crust being very brittle is very simple, that it is first of all thin, and secondly, it is brittle because it is cold. Out of all the various different layers in the interior, the region of the crust is basically coldest one, and that is why rather than getting deformed, it breaks easily. Now, when we talk about this crust, please keep in mind that the thickness varies when you talk about the oceanic crust and the continental crust. Crust is largely made out of lighter material. At the time of formation of planet Earth itself, you had the situation where the lightest materials they came closer to the surface before the planet Earth started solidifying. So that is why materials like silica, the silicates of aluminium, etc., they form predominantly the portion of the crust. Now, this crust can be classified into the continental and the oceanic crust. Now, the thickness tends to vary. You see, when we talk about the continental crust is much thicker. Okay. It has got a thickness of close to around roughly 20 to 30 kilometers in the case of the continental crust. It has got a thickness of almost 30 kilometers. And you also have to keep one thing in mind, that when we talk about this region of the crust, now continental crust is not always going to be only 20 to 30 kilometers. In certain cases, for example, when we talk about the region of Himalayas, where there is a large amount of crustal compression due to the collision of the Indian and the Eurasian landmass, the crustal thickness can go up till around 70 kilometers. Okay. So that is how wide the crust can become, particularly underneath the region of thickness of compression, such as the region of the Himalaya. Now, then, when we talk about the continental crust, it is made out of lighter material. Lighter materials like silicates of aluminium and so on. So, the density of continental crust is less. It is close to around 2.7 gram per centimeter per centimeter. That is the thickness of the continental crust in general. Now, it is made out of granitic rock. Okay. That is what is a property that you will find. Now, this is something where the NCRT has mentioned it incorrectly. So please ensure that while you are revising from the NCRT, you keep a track of this. NCRT has committed multiple errors in the entire subject of geography. So please keep that in mind. So the continental crust has got a lesser density of close to around 2.7 gram per centimeter cube. It is largely made out of granitic rocks. Whereas when we talk about the oceanic crust is thin, but it is dense. It is heavy. Oceanic crust is basically made out of basaltic rock, rich in iron, magnesium. So that is what the oceanic deposits are also constitute. It has got a density of close to around 2.9 to 3 gram per centimeter cube. That is the case of the oceanic crust. Okay, I will give you the entire compilation very soon. As soon as we talk about the all the layers of the planet Earth, I will give you a compilation for quick revision as well. Now, after this comes the layer of mantle. Now, mantle extends up till a depth of 2,900 kilometer from the surface. Voluminous, right? Almost 64% of the interior is covered by the portion of mantle. Mantle is in a solid state. Always keep that in mind. Mantle is in solid state. But within the region of mantle, mostly in the upper layer of the mantle itself, you have a semi-molten layer, semi-plasticky, semi-solid layer, which is known as asthenosphere. Now, why is it that asthenosphere is semi-solid or semi-molten? That is because when we talk about the portion of the mantle, first of all, mantle is in solid state. Okay. Keep that in mind. Please don't get confused in this. Most of the candidates, they start thinking mantle is in liquid state. It is not the case. Now, how does the structure pan out to be? So think about it. Let's suppose this is your surface. Okay. Now here you have the portion of the crust, innermost. Then you have the entire portion of mantle. Now, within this portion of mantle itself, in the upper layers, you have this semi-molten, semi-solid layer. This is what you refer to as the asthenosphere. Okay? Asthenosphere. Now, above this asthenosphere, I will come to what is asthenosphere and why it is in semi-molten state. Above this, what do you have? You have the portion of the crust. And can I say above this, you also have the upper solid mantle, isn't it? Upper solid mantle. Both of them are present above asthenosphere. Together, crust and the upper solid mantle, they are known as lithosphere. So lithosphere includes the portion of the crust and the upper solid mantle. Underneath it, you have the region of asthenosphere, which is semi-solid and semi-molten. Now, why is it semi-solid and semi-molten? Because at this particular depth in the interior, you have the presence of radioactive substance, a larger concentration of radioactive substance. Now, which radioactive substances are we talking about? So you basically have in this particular area the increased concentration of materials like uranium and isotopes of potassium, isotopes which are radioactive of potassium. Now you have to understand that as you start going into the depth of the planet Earth, in the interior of the planet Earth, the temperature tends to increase. Oftentimes, the temperature shows an increase of around 20 to 30 degrees Celsius as you move across a depth of 1 kilometer. Right. So you can imagine that as you go to the depth of around 160 to 200 kilometers, where this asthenosphere is present, in fact, around 160 to sometimes even 400 kilometers, that is the depth at which asthenosphere is present, the temperature would be very high. Along with that, the pressure would also be higher. So, under the consequence and under the circumstances of high temperature and high pressure, uranium and these isotopes of potassium, they undergo a thermonuclear reaction. In simple terms, a nuclear reaction. But we know that any nuclear reaction will produce sufficient amount of heat. So that is why it is regarded as thermonuclear reaction. So you basically have, due to high temperature, due to high temperature and high pressure and pressure, they undergo thermonuclear reaction, right? Now, this thermonuclear reaction ends up producing enough amount of heat, right? Enough amount of heat is produced. And that partially melts the materials which are present in the nearby vicinity. And that is why asthenosphere is in semi-molten or semi, not a complete solid, not a complete, somewhere in between. Also, you see, whenever you have volcanic eruption, we have materials, molten materials from the interior which come to the surface. In certain cases, you have materials coming from the lower portion of the mantle. But in majority of the cases, the eruptions that we see, they are from the region of asthenosphere itself. So in majority of the cases, asthenosphere ends up becoming sources of source of volcanic eruptions, magma for volcanic eruption. Okay, that is something which you find in commonality, right? So that is again the case of asthenosphere. Now, underneath it, again, you have the portion of the mantle which is again solid. So, mantle is solid above asthenosphere, mantle is solid below asthenosphere. But after the portion of the mantle comes the region of the, okay. So, when we talk about the portion of the core, you see, core is broadly divided into two parts. You have the outer core and the inner core. Okay. Now, on what basis is the core divided? So basically, you see that when we talk about the interior, the temperature increases, the pressure increases. As you reach the level beyond 2900 kilometers, the temperature and the pressure are very high. Now, owing to that high temperature, outer core is in a molten state. Molten state. Whereas when we talk about inner core, it is in a solid state. Why is it that inner core is in a solid state? A simple case. For example, let's suppose you consider any particular state of matter. Any particular state of matter. Now, this state of matter, if you heat it up, it will get converted into liquid, isn't it? It will melt. Now, liquid will tend to occupy a larger volume. In most of the cases, other than water and ice, almost in all other cases, liquid tends to occupy a larger volume as compared to the solid. So here, if you heat it up, it will get converted into liquid, it will expand in volume. But imagine a situation where you don't allow this solid to expand at all. Apply force and pressure from all sides that this solid is not allowed to expand at all. Then what will happen? Regardless of how much heating you carry out, the solid will remain intact as a solid. It will not get converted into molten state or a liquid state, isn't it? So, because of this, and it is the same property which is experienced in the interior of planet Earth as well as you go into the depth. Basically, as you go into the depth, the pressure increases from all different sides. The pressure is so very high at a depth of around 6,300 kilometers. The pressure is so very high that the inner core has got no scope to expand, right? So, due to a very high pressure exerted from all sides, very high pressure exerted from all different sides, it cannot expand to form liquid, can't melt despite the very high temperature, right? High temperature. Now, core has got the highest density of the all the various different structures in the interior. When you talk about the core, it is largely dominated by elements like iron and nickel. And hence, this is a layer which is also referred to as Nephe, the Nephe layer, as it is referred to. So that is the case of the portion of the core. Okay. So overall, these are the various different layers that we had to take a look into. Okay. Now, a quick recap of all of this. When we talk about the portion of, let's suppose, the crust. So in the portion of the crust, we have seen you have the continental crust and the oceanic crust and the oceanic crust, isn't it? Now, continental crust made out of granitic rocks, oceanic crust rich in iron, magnesium, made out of basaltic rocks. Basaltic rocks. This has got a low density. Granitic rocks have a density of around 2.7 gram per centimeter cube. Basaltic rocks have a density of almost 3 gram per centimeter cube. As you move into the interior of the planet Earth, the temperature witnesses a gradual increase, a regular increase, and that is a property that is also referred to as geothermal gradient, where the temperature increases as you move inside. Okay, that is known as geothermal gradient. Then, after that, basically in the portion of mantle, you have the semi solid, semi molten region of asthenosphere. Asthenosphere is semi-solid and semi-molten because of the presence of radioactive materials. And then you have the portion of the core. The core is divided into the outer core and a distinct inner core as well. Okay? So that constitutes the interior. Now here, basically an interesting fact tends to happen as you go into the interior, in the sense that we know that as you move into the depth, the pressure is different. The pressure keeps on increasing, the temperature keeps on increasing. So after every small distance, there is a change in the material density, change in the kind of particle arrangement. All of these tend to change quite dramatically. So that is a phenomena that you observe. Now, these are known as discontinuities. So when you go into the interior of planet Earth, the material structure, the material density, the material property, all of them, they witness a change. So wherever this change tends to happen, that is known as discontinuity. This is relevant for your prelims exam, where you can get a match the following kind of a question. Okay. So in this particular case, you have the listing of the various different discontinuities. You see, even within the crust, upper portion of the crust, what you see on the surface, the kind of rocks, will that be similar when you go to the depth of 30 kilometers? Obviously not. 30 kilometers, you will have much more compressed rock formations, much higher temperature of rock formation, right? So there is a discontinuity between the upper and the lower crust itself. And that is what is referred to as the Conrad discontinuity. Okay. Then after that, when you move from the crust to the portion of the mantle, now there also material changes. Mantle is made out of more denser materials. So that is what is demarcated by a discontinuity, which is known as Mohorovičić or Moho discontinuity. Okay, this is what is the Moho discontinuity, which differentiates the portion of the crust from the portion of the mantle. Within mantle also, the lower portion of mantle, much higher temperature. Rather than breaking, it will get deformed. Whereas the upper portion of mantle, still slight brittle nature. So there is a discontinuity differentiating the upper and the lower portion of the mantle. And that is a discontinuity which is known as repeti discontinuity. So repeti discontinuity demarcates the upper and the lower mantle. Then, as you move away from the mantle, the outer core basically is a liquid molten state, right? So, in that molten state, again, that indicates a change in the material density and the material state. So, that is demarcated by what is known as the Gutenberg discontinuity. Gutenberg between mantle and core. And between the outer and the inner core, you have the Lehman for your prelims. Out of all of these, the most important ones are Mohorovičić discontinuity, Gutenberg discontinuity, and the Lehman discontinuity. These three are the important ones for the prelims. Keep that in mind. Mohorovičić, mantle and crust. Gutenberg, mantle and core. Lehman, outer core and inner core. Okay, so these discontinuities, keep in mind, match the following kind of question, can easily be framed out of this. Okay, now having said that, another area where UPSC has asked questions previously is the abundance of materials, elements. Which element is the most abundant in the entirety of planet? Which element is most abundant on the surface? Right. So this kind of question has also been framed by UPSC. So here, when you talk about the earth as a whole, this image indicates to you about the abundance of material. Here you can see iron is the most abundant, followed by oxygen, followed by silicon. Now you don't need to ratify all of them. Please don't do that. That calcium also I'm learning, aluminium also I'm learning. Please don't do that. Just keep in mind which is the most dominant if you consider planet Earth as a whole, including the interior. Iron is the most dominant, followed by oxygen. Now, how come oxygen is a dominant element in the interior of planet Earth? After all, oxygen is a gas. So when we say interior of planet Earth consists of oxygen, what is it exactly that we are referring? So basically, we are referring to the presence of oxides like silica, ferric oxide, ferrous oxide, all of those, alumina. So all of them will have oxygen as an element. So that is where oxygen finds its abundance. So again, iron, oxygen, silicon, IOS. Okay. Now, when you consider only the crust, in that particular case, which is the most abundant one? So only the crust, if you consider, the most abundant now becomes followed by silicon. Okay. Keep that. So oxygen followed by silicon is the most abundant. So that talks about the interior structure of planet Earth in detail as much as it is required. Now, owing to the interior, we have another concept. That is the concept of geomagnetism. Now, it has been in increased focus and attention over the past 1 year. So, geomagnetism also becomes relevant for this year's prelims. And if you notice the trend by UPSC, whichever questions are asked generally in the mains examination or in the optional portion, there is a propensity of those questions being repeated in the prelims as well. So, UPSC has been focusing upon geomagnetism since last year. Now, what is geomagnetism? Geomagnetism is the property where Earth starts behaving like a bar magnet. When I say a bar magnet, a distinct north and the south pole. So, planet Earth also ends up behaving like a magnet. And it extends a kind of a magnetic field. And that magnetic field which the planet extends around itself, that is what is referred to as magnetos. I hope till now the portion is being understood and everybody is comfortable, right? See, in case of element is abundant, which element is abundant? Oxygen is abundant in the crust. Iron is abundant in the entire planet. Now, do you need to learn the exact percentage of them? Absolutely not. You don't need to learn the percentage of what is the percentage of iron, what is the percentage of oxygen. These kind of questions UPSC is never going to ask. So please do not end up complicating your task already. Okay? Density increases, tends to increase continuously with depth in most of the cases, barring a few aberrations. Okay? Why oxygen is abundant in the interior? Oxygen is abundant because when you talk about the surface, when you talk about the interior, you have the presence of various different oxides, isn't it? Such as silica. What is silica? SiO2. What is alumina? Al2O3. Isn't this oxygen? Isn't it? So these elements which appear to be present in the solid state, they include oxygen atoms. That is why oxygen appears to be very abundant. Okay? Lalita and all of you who had the doubt, I hope now it is clear. Now coming back to geomagnetism, the concept of geomagnetism. Now you see, in the interior, we have seen that when we talk about the portion of the, let's suppose we talk about the entire planet. Now, in this entire planet, you have the region of the outer core. Now, outer core is in a molten state. Inner core is in a solid state. Now, as the planet tends to rotate from west to east, outer core being liquid, will also tend to rotate. Liquid after all. So imagine a large ball which is rotating, and if you have liquid inside that ball, the liquid will also move. So we know something about the portion of outer core. First of all, liquid. Secondly, high temperature, isn't it? And then rotates, right? This is the property of the region of outer core. Now, due to this high temperature, which is present in the interior and being present in a liquid state, iron and nickel, they tend to lose certain electrons, right? So as a consequence of that, you have presence of charged particles which get created. So imagine an iron atom of iron. If an electron is lost, right? So that electron will be a negative charge, isn't it? So there are presence of these ions in the outer core. So in a way, we can say that these ions, they move in a rotational manner, a spiral manner. Or that rotation ends up generating a magnetic. And this magnetic field which is generated is known as the geomagnetism. That is what we refer to as geomagnetism. Now, the entire magnetic field which is extended, that is also what is referred to as magnetosphere. It protects us from the harsh solar winds which are thrown into the solar system every now and then by the sun. Now, mind you, when the planet was formed initially at that point of time, around 4.5 billion years ago, the solar system was much unstable as compared to what you see today. At that point of time, the frequency with which large amount of solar winds, coronal mass ejections, which would happen from the sun, they would be immense. They would bombard the planet and they basically uprooted the initial primordial atmosphere that we had. The initial atmosphere included only of hydrogen and helium. They were bombarded by the solar particles from the sun and it was eroded. Now, after that, within the next few million years, the Earth developed its magnetosphere as it was getting solidified and as it was evolving. Since that point of time, our atmosphere has been protected from these charged particles coming from the sun. Having said that, when the charged particles come from the sun, you see, the charged particles, they come from the sun. This magnetosphere acts as a shield. But then, some of these charged particles, they tend to penetrate and leak into the areas where the density of the magnetic field lines is the highest. Now, if, in simple terms, if I put two places, 1 and 2, if I ask you very simply, where is it that the density of magnetic field lines is high? Always 1. 1 is where the density of magnetic field lines is very high. So, in these regions of high magnetic field lines, you will find that some of the charged particles, they end up penetrate. As they penetrate, the charged particles from the sun, they interact with the atmospheric particles. Particles from sun, they interact with basically the atmospheric particles like oxygen and nitrogen. Now, when they interact with oxygen and nitrogen, they give them some amount of energy, they get charged, and eventually they end up releasing light. I won't go into the exact depth and detail of it. Basically, what happens is that there is a molecule of oxygen, let's suppose, charged particle comes in and it hits it. Electron jumps the orbit, right? After some time, when the energy is lost, the electron comes back, joins the orbit again. At that point of time, light is now depending upon whether it is the oxygen molecule or whether it is, let's suppose, the case of nitrogen molecule, the energy released is different. So the light released is also different from blue to purple, different to greenish hues. There are different types of light which are emitted. Those kind of lights which are emitted due to the interaction of charged particles from the sun with oxygen and nitrogen, those are known as auroras. Auroras. They are of two types. They are named differently in the northern and the southern hemisphere. So in the northern hemisphere, they are known as aurora borealis or northern light borealis or northern light. And in the southern hemisphere, they are known as aurora australis or southern light. Okay? That is how you'll find the auroras to be created. Now, if a question is asked, in which latitude are the auroras observed? Always in the higher latitude. Always. However, sometimes when the solar action is very high, the energy released by the sun is very, very high. Sometimes what happens is that some of the charged particles, they leak to the lower latitude also. That is why last year, auroras were observed in the regions of Ladakh as well. Last year, you had auroras which were observed in the region of US as well. So when the solar activity is very high, at that point of time, some amount of charged particles, they leak through the magnetosphere in the lower latitude as well. So auroras are produced in lower latitude. Okay. Now, by the way, another interesting concept associated with this. You see, the presence of this magnetosphere is the difference between Earth and Mars. There have been various different missions, space missions launched in Mars. And it has captured the popular imagination as well. That was life ever present in the case of Mars? Or can life be present in the region of the Mars? Presently, it appears to be a red desert, but it appears lifeless, right? In the case of Mars, you don't have this magnetosphere. Why? Because in the case of Mars, around 3.7 billion years ago, you had the solidification and cooling down of the core. As a consequence of that, when the core solidifies, you don't have that magnetic field impact anymore. Because keep it in mind, when we talk about planet Earth, it is the molten outer core which is rotating. And that molten outer core is responsible for the ions, and that is responsible for the generation of magnetic field lines, isn't it? In the case of Mars, the core is complete solid. That happened around 3.7 billion years. That meant what? That you did not have this magnetic lines and the shield provided by the magnetic line. So the charged particles from the sun would completely bombard the region of the Mars atmosphere. So that is where the atmosphere of Mars was completely taken off. And when the atmosphere is taken off, you have very high temperature during the day, very cold conditions during the night. Water will be lost, and all the life providing substances are also lost. So this is the difference. The region of the core, outer core, is the difference why we have life on planet Earth and why we have the barren red planet, which we refer to as Mars. I hope that is understood. Over a period of time, even planet Earth's outer core is going to lose energy, but that will take billions of years, enough for us to see multiple lifetimes, right? Now, here, please keep in mind that when we talk about the interior of planet Earth is very hot, there is a lot of heat in the interior. Where is the heat coming from, by the way? What is the source of heat in the interior of planet Earth? So there are two sources of heat in the interior of planet Earth. Which are those? Sources of heat in the interior. Which are those? There are two of them. One is the case of residual heat. What is residual heat? At the time of formation of planet Earth itself, there was a lot of heat. After all, Earth, when it was formed around 4.5 billion years ago, it was molten liquid, right? A large molten ball of liquid. Now, as it started solidifying from outside, heat was trapped in the interior. That is what was referred to as the residual heat. That is still present. And the other case is the heat due to compaction. Due to compaction. What do we mean by that? Basically, when we talk about the pressure exerted from all different sides, there is enough heat which is produced. Let's suppose we take any matter like this. If I compress it completely from all different sides, there will be some amount of heat produced. So is the case with the entire planet Earth. So that is where these are the two sources why the innermost portion of Earth is very hot. Yes, most of you have written asthenosphere, etc. Asthenosphere provides heat only in that localized region of 160 to 400 kilometers depth. The heat of the asthenosphere does not percolate into the region of outer core. Outer core is much having a much higher temperature as compared to the region of asthenosphere. This is the two sources of heat in the portion around the. Okay. Now, after this, basically, we have taken a look at the portion of the interior, the structure, the case of why there is heat generated, geothermal gradient, density, discontinuities, and geomagnetism, elemental abundance. Okay. Now, after this, we come to another topic, and that is the origin of continents and the ocean. Now, here, we are going to take a look into the continental drift theory, the convection current theory, the seafloor spreading theory, and the plate tectonic theory. Relevant for the examination, we are going to cover them one by one. Starting basically from the case of the continental drift theory. Now, you see, when you take a look at the map of the planet Earth, Geographers had always wondered that why is it that the continents are arranged in the way that we see them to be? Why is it that you have a greater density or greater presence of landmass in the northern hemisphere? And why is it that the continents in the southern hemisphere have a conical shape, etc.? These were the kind of questions which always came into the mind of the geographer. Now, there was never much amount of information which could be provided, or never a concrete theory which could be provided. You had some of the individuals, for example, you had Lothian Green, etc., in the 1800s, who talked about the fact that Earth is contracting, and hence you have the mountains and the ocean. Now, obviously, that was discarded. But then, since the 20th century, the early decades of 20th century, discoveries and more theories began to be postulated and theorized. It was around 1912 when Alfred Wagner, who was a German meteorologist, right? German meteorologist. Meteorologist means specialized in climate studies, that how climate is changing. Now, Alfred Wagner got hold of a world map. In those days, world map was a very rare commodity. Now, it is said that on one fine Christmas Eve, his friend presented him with a world map. Now, when he took a look at the world map, he basically observed certain unique cases. He observed that the shape of the landmass in the eastern part of South America is very similar to the shape of the landmass in the portion of Western Africa. The shape of the landmass across the region of the Arabian Peninsula is very similar to the shape of the landmass in the region of Horn of Africa. Right. So, based upon these, he got an idea that maybe the entire continents were at one point of time together, forming a giant singular landmass. And they have drifted away from each other. So he studied the geological evidences, he studied the meteorological evidences, he studied the paleontological evidences, and based on that, he formulated the continental drift. In a nutshell, what is this continental drift theory? Continental drift theory talks about the fact that at one point of time in the past, you had a giant supercontinent, and that supercontinent was named as Pangea. Was named as Pangea. Now, this Pangea was surrounded by water bodies from all sides, and those water bodies were referred to as Panthalassa. In fact, Wagner went ahead to say that the present day Pacific Ocean that you see is nothing but a remnant of Panthalassa itself. Now, this Pangea broke into two parts. You had the northern part, including the region of North America and the region of Eurasia in presence, and that was named as Laurasia. Whereas you had a distinct southern part, including the region of South America, Africa, Arabian Peninsula, India, Australia, and Antarctica. And that was named as Gondwana land. Gondwana land. Okay. So you had the classification as Laurasia and Gondwana land. Okay. Now, thereby, Wagner said that this Laurasia and Gondwana land then further split. They further and they broke because of two different types of movements which happened. There was a kind of two different movements, type of movements were experienced by the continents. Which were those two movements? You basically had a westward drift of the continents, westward drift of continents, and secondly, you basically had movement away from the poles, which in German he referred to as Polflucht. Okay, so movement away from the pole. So this movement away from the poles is what he accounted as the reason for the split of Gondwana land, right? Where Antarctica, South America, Africa, India, they simply separated from each other, and India, Africa, South America, Australia, they started moving northward. So these were the two movements due to which these continents they split. Now, based upon certain set of evidences is why Wagner said that all the continents were one at one point of time. So, which were those evidence? Starting from a very basic visual evidence, that was the case of the jigsaw fit, where it appeared that all the continents, they have a similar kind of a coastline, particularly the region of eastern part of South America and the portion of western part of Africa. There were geological evidences. When we say geological evidences, what do we mean by geological evidence? So geological evidences were of certain types. First was rock structures. Rock structures. So there were similar rock structures to be found in certain places. Where, for example, in the eastern part of North America, you have the old mountains, residual mountains in the form of Appalachians. Appalachians are also fold mountains, by the way. Now, there was a similarity of the rock structure between Appalachians and the Scottish Highlands. Similarly, there was a similarity of structure of the rocks in the eastern portion of Brazilian highlands with the western portion of Africa. The similarity of rock structures indicated an absolute same age of formation, the same time period, that indicated that these would have been together and the rocks would have been created at the same time. Then, the second set of evidences were basically in the form of placer deposits. What are placer deposits? Placer deposits which are placed at a certain distance. Simple term. For example, let's suppose you consider a mountainous area. Let's suppose on top of this mountainous area in this particular region, let's suppose you have the presence of a material like gold. And let's suppose here you have a river which is moved in this area. Now, gold is insoluble in water. So it cannot be dissolved in water. So slowly and steadily, this gold will be eroded and this gold will be deposited by the river somewhere here. Isn't it? So these are known as deposits, placer deposits. These have been placed at a faraway distance. These are your placer deposits. Generally, gold is found in the form of these placer deposits. And this is your what is known as a source rock. Example in Indian context. Can anybody tell me the example in Indian context where we find these placer deposits? So, in case we are not aware of this, when we talk about, let's suppose the case of when we talk about the region, let's suppose around Chota Nagpur Plateau. In Chota Nagpur Plateau, is the audio not clear? Gyan, Gyan Desikan Sentinathan. Audio is clear for everyone? Okay. So it is clear for everyone, Gyan. So please change the volume settings or the audio auditory settings for some time. It will be better. Right? Now, in Indian context, where can we get the example of this? So, around the region of Chota Nagpur Plateau, you basically have the presence of these some amount of source. Okay. Now, you have rivers such as Subarnarekha. Subarnarekha, the name in itself is derived from gold line, right? If you translate the name Subarnarekha, it comes out to be a line of gold. So you have these rivers which originate from the region of the Ranchi Plateau, and they used to bring up certain particles of gold and deposit them along the river valley itself, along the river channel itself. So that is the example of the placer deposit. Similar kind of placer deposits are to be found in the entirety of the region of Peninsular Plateau. Okay. So here, placer deposits, how can they be an evidence of the theory of continental drift? So basically, you see, in the region of western part of Africa, you have large amount of gold deposit. West Africa, large amount of gold deposit. Okay. Now, these are in the form of placers. But there is no such source rock to be found in any such area. So, Upon greater investigation, it was found out that the source rock for these placer deposits are present where they are present in the region of west or the eastern part of South America, that is in the Brazilian highlands. So the source rock is for these gold deposits is to be found in Brazilian highlands. Okay, so that again indicated that there is or these continents would have been together and then have split. Then you had the third evidence. The third geological evidence is in the form of tillite. What is tillite? So, anywhere where you basically will have the presence of glacial movement, anywhere wherever there is a glacial movement, the glaciers will end up depositing certain sedimentary material. They solidify to form these sedimentary rock parts. So, those are known as tillite. So, tillite is basically your glacial deposit. Anywhere where you find these glacial deposits or tillite, that basically means that region has had a glacial history. Okay, that is a region which has witnessed glacial action going the past. So, for example, when we talk about India, in the region of the Damodar River Valley, which moves through a rift valley in the region of Jharkhand and West Bengal, if you consider the Godavari River Valley. Now, across these river valleys, at a depth, you will find the presence of coal seams, coal beds, right? These are rich coal mining areas. But beneath those coal beds, you will find the presence of tillite, which tells you that at one point of time, the entire region of Indian subcontinent would have witnessed glacial action. Same is the evidence presented in the region of Africa, South America, Australia as well. Now, this could have happened only under two possibilities. Either the climate has changed to such an extent that earlier there used to be frozen conditions in peninsular and central India, or the second condition could have been that these continents would have been present near the South Pole and they have split away. They have moved away. So when they were present near the South Pole, everything would be frozen. And as they have moved away, that is where they basically don't have the glaciers anymore. So these tillite deposits and the glacial striations, linear markings created by the glacial movement, they are the evidence again in the form of the geological evidence of all the continents being together at one point of time. So as you can see that when the glacier moves over a region, it leaves behind a trail of markings on the ground surface. These are the linear markings which are also referred to as the glacial striation. So these glacial striations are to be found on the ground surface, indicating the evidence of past glacier. But also, you had the fossil evidences, paleontological evidences, which are referred to. So when we talk about the paleontological evidence, before that, a replication of the glacial evidence. You see, that glacial evidence has been found in the region of South America, in the region of Africa, and even across the region of Indian subcontinent. We know that in central and southern India, you don't even have ice formation, let alone the glacial formation. Same is the case with Africa also. So it makes sense only if you put all of them together as a part of the massive Gondwana land. They would have been present closer to the region of South Pole. Only then would they have the presence of glaciers, right? Now, the paleontological evidence that is in the form of fossils. Now, some of the species, their fossils are distributed over a large distance. Amongst them, the most interesting of them is the case of Mesosaurus. Now, Mesosaurus is an ancient animal, no longer present anymore, ancient reptile, which would be around 8 to 10 feet in length. And it would be found in fresh water, having a diet of small fishes. Only in freshwater creeks, bogs, marshes, etc. That is where you would find the Mesosaurus. Now, fossils of Mesosaurus are to be found in South America also. Fossils of Mesosaurus are to be found in Africa also. How is it possible that in different regions the same fossils are to be found? So that again indicated to one particular fact that all the continents would have been together when the animals would have come into existence, and later on the continents. Same is the case with the fern species, that is Glossopteris, Listrosaurus, and also Cynognathus. Like that, multiple different species, their fossils are to be found distributed over large continental area, indicating the continents would have been, right? So all these evidences bring to the table the postulation provided by Wagner that there was Pangea, that Pangea split, and that is why you have the different. Now, that is what Wagner proposed, splitting up of Pangea because of the two types of movement. Now, why did the movements happen? For that, Wagner cited certain reasons. So basically, when we talk about the reasons cited, what were the reasons? So, for the westward drift of con, he said, westward drift basically means the continents moving westward. That is North America splitting away from Europe, South America splitting away from Africa. For this, he cited the reason of the tidal force, right? Or the gravitational pull by the earth, by the sun and the moon. Gravitational pull by the sun and moon. What does that mean? That basically means that as the planet is rotating on its axis, you basically have moon and the sun extending so much amount of gravitational force that the continents are not able to move along with. So that is why the continents are basically splitting. So that was the reason cited. Now then, for the flight away from the pole, movement away from the pole, what is the reasons away from or pole flux? So for this, he cited two reasons. Basically, Wagner was a meteorologist. He was not a geologist by profession. His expertise was that of studying the climate. And he did not have any idea about what constitutes the interior of planet Earth. So he borrowed his idea about the interior of planet Earth from different geographers. So earlier you had geographers, a great Austrian geographer with the name of Edward Seuss. Now he had provided the concept of interior, where he said that the crustal layer is made out of silica and aluminium Cl. The portion of mantle is made up of silica and magnesium, that is Sema, and the core is made up of nickel and iron, that is Ni. That is what he said as the interior, right? What constitutes the interior. Wagner straight away borrowed that idea about the interior of planet. But he went ahead in order to basically substantiate his theory. He went ahead in this argument and he said that when we talk about the earth, continents float freely. That was an assumption which was made by Wagner. The assumption was continents are floating, are floating over mantle like boat on water, like boat on water. So basically, anything which floats. So, as a consequence, there is a force of buoyancy which acts from the inside outwards, isn't it? So, he said that there is a force of buoyancy acting upwards for the continent. Force of buoyancy, which is acting upwards for the continents. And along with that, as the planet is consistently rotating on its axis from west to east, there is an outward acting centrifugal force. So, a combination of this force of buoyancy along with the outward acting centrifugal force that basically pulls the continents closer to the equator. A combined action of the force of buoyancy and the centrifugal force is leading the continents to move away from the polar region, come towards the region of equator. So, these were the couple of reasons that he cited. Were these reasons correct? Absolutely not. These were incorrect. Okay. So, because of these reasons, because think about it, if the gravitational pull by the sun and the moon would have been so strong, then the planet would have stopped rotating within the span of 50,000 years. The planet would not have continued to. And if there would be a force of buoyancy which would be acting, then the continents would have simply moved like boats. There would not be any fold mountain formation or anything like that. So obviously, both of his reasons were incorrect, due to which the continental drift theory was junked, right? But then this paved the way for future understanding many decades later, where the basic concept that they can drift, that in itself provided enough information, and that helped in postulation of what is known as the plate tectonic, right? So that is the continental drift theory. In the continental drift theory, what is it that we have studied? We have studied the evidences, right? What is the theory itself? The theory is about Pangea surrounded by Panthalassa. The evidences are visual, the evidences are geological, the evidences are climatological in terms of the glacial presence, climatological, then the evidences are also paleontological, right? Then after that, we studied about the reasons, assumptions undertaken by Wagner, which were the assumptions. Sial floats freely over Sima, or continents are floating freely over the mantle, just like a boat on water. And then the kind of movements, two types of movements, westward drift, as well as movement away from the poles, two types of movements. And then after that, also about the case of why, the reasons for those moves. Okay. So that is all that you have to know for the continental. Okay. Now, then comes the convection current theory. Who provided the convection current theory? Convection current theory was provided a few years later, almost close to a decade later, after the continental drift. This was provided by Arthur Holmes, who was a physicist by profession, by training. Arthur Holmes, a pupil of Rutherford himself. Now, he had made tremendous contribution when it comes to carbon dating, etc. So Arthur Holmes is a very significant contributor in the entirety of geography, be it isostasy, be it mountain formation theories, or be it the convection current theory. Now, what is this convection current theory? Convection current theory talks about that how the heat from the interior of planet Earth escapes to the surface. We have seen that in the interior of planet Earth, there is a lot of heat, isn't it? And there are two reasons for that lot of heat. One reason is the presence of residual heat, and second is due to compaction. Now, that heat which is excessive in the interior, that escapes to the surface. Now, how does that escape? So that is where the convection current theory comes into. So convection current theory says or states that, see, if you consider the portion of the crust to be very thin, then the portion of the mantle, and then the portion of the outer core. Now, heat is generated from the region of Gutenberg discontinuity or from the region of outer core. Now, this heat, when it is generated, the portion of the mantle starts to, as the portion of the mantle starts to melt, this molten portion starts to rise up. It will melt the region above it as well. As the molten layers, basically meaning liquids are lighter, so they will tend to rise up. As they tend to rise up, they will melt the layers above them as well. So in this manner, they will keep on melting the layers above them, and there is a full-fledged generation of a convection current. And in the meanwhile, the portion of the cooled or the solid mantle, that will replace the rising up portion. So you have a full-fledged convection current which is developed. Now, this convection current leads to the distribution of heat from the interior to the exterior surface. That is the convection current. Okay. So, what it can lead to? On the surface, it can lead to volcanic eruptions, the convection current. volcanic eruptions. It can basically lead to you have the land can get uplifted, swollen over, upliftment and subsidence of land, upliftment and subsidence of land. Okay. Then basically, in these areas, there can be subsidence where you have the sinking column of the convection current. It can also lead to the land getting torn away, land getting pulled apart, right? So that is where he said that the convection current is simply the mechanism of heat from the interior getting moved to the exterior. In the process, there can be changes and impact on the surface. That is, in a nutshell, the convection current theory. Okay. Radioactive decay, Krishna, happens only in the region of asthenosphere. That's it. That is where you have the radioactive decay. Okay. Now, process of convection. Process of convection, Atharv, is very simple, where the heat from the region of Gutenberg discontinuity that melts some portion of the mantle, lower mantle. As it gets molten, liquid is lighter, it tends to rise up, melting the portion of the mantle as it moves up. And in the meanwhile, you have the colder portion of the mantle, the supercooled one. They end up filling the gaps created by the rising liquid. So you have a complete cycle where the colder ones come to the bottom, the hotter ones they rise to the surface, and you basically have a convection current. Okay? Now, convection current, Saurabh, is present only in the asthenosphere or the entire magma. You mean entire mantle. It can be present in the region of asthenosphere itself. It can be present in the region of the entire mantle itself. But when the theory was provided, not much information was present about the asthenosphere and so on. So the theory talked about the entirety of the mantle. But presently we know that it can be the convection current can be generated in the region, concise region of asthenosphere as well. Okay. Now, after this, come to the seafloor spreading theory. Now, seafloor spreading theory was provided post Second World War by the naval expeditioner from US with the name Harry Hess. Harry Hess. Now, what is this seafloor spreading theory? So basically, based on the observation that Harry Hess made in the case of the ocean bottoms, he basically observed that ocean bottoms are not flat and featureless that we expect the ocean surface to be. Right? Ocean bottoms basically are very corrugated. They have the presence of abyssal plains, they have the presence of sea mounts, they have the presence of mid oceanic ridges. All of these are present in the region of the ocean. Right? So he looked at the region of the mid ocean. Now, the mid oceanic ridges were the areas of active volcanism, active volcanicity, and the presence of volcanic eruptions would happen in these regions of mid ocean. These are your mid oceanic ridges. Now, he basically said that in these regions of mid oceanic ridges, molten materials they come to the surface as a result of volcanic eruptions. Now, these molten materials they form the newer crust, and the older crust is then pushed to the side. Like that, the seafloor tends to, right? So, seafloor spreading in a very simple nutshell is about creation of newer crust at the region of mid-oceanic ridge. Oceanic ridge. Okay. That is where you basically have the creation of a newer crust. Now, when you talk about the existing seafloor or existing crust, the existing crust in the meanwhile is being continuously pushed to the side, right? So, due to this, you have expansion of the existing of it tends to expand. Now, what about the older crust? The older crust gets consumed in the region of the continent ocean transition around the region of the oceanic trenches. Older crust is consumed in oceanic continental transition boundary at oceanic trenches. Not everywhere, but in few places. Now that means wherever you don't have the oceanic trenches, the sea gets expanded. This is something by which he could postulate that why the Atlantic Ocean is expanding, because at one point of time we have evidences that North America collided with Europe, right? Atlantic is something which is only as recent as 200 million years old. Before that, you did not have the presence of Atlantic Ocean. So Atlantic is getting created, and as Atlantic is getting created, it is expanding because of volcanic eruption which is happening across the region of the mid-Atlantic. Okay, that was the seafloor spreading. Now this he made as a argument, as a theory based upon certain assumptions that were there were basically or based upon certain observations. Rather, observations that he made was basically that nowhere across the oceanic crust or the oceanic flow will you find the case of the deposits which are older than 200 million years, which means that oceanic crust is getting recycled very free. Whereas in the case of continental crust, you have rocks which are more than 3 billion years old, 3.2 billion years. So that means continental rocks are not getting recycled, but the oceanic crust is getting recycled. Then the ocean floor was not plain active volcanism across the mid oceanic ridges. Then, with the help of magnetic anomalies, he observed that there is the older crust which is getting pushed aside, newer crust is getting created in the region of the mid oceanic ridge. So, based upon these observations, these series of observations, he came across what is the seafloor spreading theory. Okay. Now, what you said while where trenches not there, seafloor. So basically, where trenches are there. So think about it. Let's suppose if you consider the continental region, two continental regions. Now, as per the theory, there is a mid oceanic ridge in between. Here you have the volcanic eruption. So newer crust is getting created. The older crust is getting pushed aside. Now, if you have a trench here, so the older crust will get consumed here. But if you don't have a trench in this, that means what? The sea floor will get wider and wider, right? So that is why sea floor spread. The sea floor is spreading. That is where the concept and the name came from. Okay. Why can't we use the term ridge in convection current? You can use the term, but at that point of time, when convection current theory was provided, at that point of time, there was no understanding of what is a mid oceanic ridge. Mid oceanic ridges were discovered much later. That is why it would be improper to use them at the same time. Okay. Can we say Red Sea is the example of in the Red Sea, you have the presence of a mid oceanic. A sea cannot be an example of a ridge. Please understand that. Mid Atlantic ridge, Pacific rise, all of these. So, this is the image of the various different mid oceanic ridges which are there. If you observe this, you will observe the presence of these. This is the mid Atlantic ridge. And here you have the newer crust. And then the older crust is being pushed to the side. That is why the region of Iceland experiences so frequent volcanic eruptions. You have a very large oceanic ridge in this area as well, what is known as the East Pacific Rise or the Chilean Rise, right? Here also you have the presence of these mid oceanic. This is the reason why the Indian plate is continuously being pushed to the north into the Eurasian landmass. Okay? Now, based upon these earlier theories, that is the continental drift theory, based upon the seafloor spreading theory, and based upon the convection current theory, you have the plate tectonic theory. Now, when we talk about the plate tectonic theory, it is very simple in the sense, and one single individual was not responsible for postulation of plate tectonic. Plate tectonic theory was postulated by a group of individuals. from some contribution by Tuzo Wilson, some contribution by Mackenzie, Parker, all of them, they made their contributions, and accordingly, the plate tectonic theory. Now, plate tectonic talks about the fact that the entire lithosphere, remember we have seen just now. What is lithosphere? Crust plus upper solid mantle above the asthenosphere. That is lithosphere. So, lithosphere is broken into small fragments that is known as plate. Now, these plates, they tend to move over the region of asthenosphere. And as they move over the asthenosphere, this movement is driven because of the convection current in the interior. Now, the convection current which is present in asthenosphere also, and in the entirety of mantle as well. So, because of that, you have the plates which are now, as per the plate tectonic theory, the plates basically which were the fragments of the lithosphere. So, these plates were divided into two parts. You had the major plates, and the minor, right? Minor plates. Based upon the size and the size feature. Now, when you talk about these plates, you have to understand that major plates are very large, right? So, major plates, if you can classify the major plates, you have the North American plate, right? Then you have the South American plate. Then, after that, African plate. Then, Eurasian plate. Then, Indo Australian plate, which is now getting broken into Indian plate and Australian plate. So, you have Indo Australian. Then, after that, you basically have the case of Antarctic plate, Antarctic, and Pacific. So these are the seven major plates which are present. Okay? Plate tectonic theory is not the combination of seafloor spreading. See, understand this very clearly. The case of convection current theory was provided in 1918 to 1920. Seafloor spreading theory was provided around 1953. Learnings from all of them were taken, and these were the geographers that I mentioned: Tuzo Wilson, Mackenzie, Parker, all of them. They were basically in the universities in US, Princeton being the hub of them. All of them were presenting their own research papers regarding the occurrence of earthquakes only in certain zones of the world. And based upon those research papers, eventually in the 1960s, late 1960s, and up till around 1974, you had a compilation which was provided. So, plate tectonic theory is not a compilation or a combination of the earlier theories. It is a learning and a progress made from the earlier theory. Now, regarding the term tectonic was coined by Tuzo Wilson. Tuzo Wilson was the one who was attributed for the term used tectonic, which basically meant building, something you build, right? So from that, basically the term plate tectonics was derived. Okay. Now, in all these case of the major plates, you will observe that all of them have both continental as well as the oceanic crust. All of them, both continental and ocean, other than the Pacific and continent. Amongst the major plate, Pacific plate is the only major plate which is completely made up of oceanic. This is the only major plate constituted only of oceanic crust. Right? Now, in this particular case, these are the plate boundary. Jan, sir, consider a case. A person starts to US from India. He boards a flight. The earth rotates continuously. Then the flight should land. What? Then the flight should land in the wrong location. But how does the flight land correctly? My dear Gyan, there is something which is known as relative velocity. You see, when the planet is rotating at a greater speed, you are standing on the planet, you are also moving along with the planet. Or is it the case that Gyan is going to be stable and rest of the planet is going to be moving? Is it the case that no, Gyan is stable, but rest of the planet is moving? Atmosphere is also moving with the same speed, or is it the case the atmosphere is stable? Atmosphere is also moving at the same velocity. If atmosphere would have been stable, then what would be the case? That Delhi today, Delhi's air is polluted. Tomorrow, that polluted air will go over to Pakistan. Then day after tomorrow, that polluted air will go to Europe. Is that the case? No. You have the same polluted air over the region of Delhi continuously. So atmosphere is also moving with respect to that. So the flight that you take is with the relative motion, isn't it? Think about it when you are moving in a bus. Now, is it the case that you are standing in some place so you should start falling behind in the bus? No. Even if you are standing in the bus, for someone standing from the ground, you will be moving at a speed. Or is it the case that Gyan is standing in one place, so automatically he's moving behind in the bus? Can that be the case, my dear? It is a very simple case of relative velocity. Okay? So don't bother that much about it. Please concentrate on this particular portion. These are the ones which are relevant for the examination, my dear. Please pay attention there. So this is the case of the major various different plates. You have minor plates as well, the smaller plates. For example, if you consider the Cocos plate, the Philippine Sea plate, the Caroline plate, the Burmese plate, the Nazca plate, the Caribbean plate, the Yuan de Fuca plate, all these are minor plates. There are multiple smaller minor plates. You don't need to remember all of them. Now, these plates are continuously in movement with respect to each other. Okay. So here, when these plates end up moving with respect to each other, the question arises, why do they move with respect to each other? And the answer to that is the case of the convection current. The convection current which is present in the interior, right? Now, this convection current, where it is present? So, convection current can be present in the region of asthenosphere, and the convection current is also to be found in the entirety of mantle. So basically, just like the simple example that you can take of a kind of a beaker or a utensil where you have boiled water, milk, anything. So let's suppose you are boiling water. Now, before the boiling tends to happen, let's suppose you have placed two wooden blocks close to each other. Wooden, thermocol, any of those. Name them A and B. Do this. You can do this on your own as well. When you start heating it up, there is a kind of a movement that you will observe in the case of A and B. A and B will tend to move. And that is because of the fact that you have a convection current which is generated in the interior, due to which A and B tend to move away from. So that is the case of why the movement tends to happen in the case of the plate, right? The plates move purely because of the convection. Earlier, let's suppose even if the convection current is present inside the case of a continent, first the crustal portion will thin out due to the heat, and eventually it will get stretched over, and eventually it will tend to move away. Now, these plates, they can move only in certain ways. The plates can either move towards each other, the plates can move away from each other, or the plates can move parallel to each other. When the plates, they tend to move towards each other, they are known as the convergent plate, right? Now, in the case when the plates tend to move towards each other, one plate gets subducted underneath. So, some part of the existing plate gets destroyed. So, that is why these convergent plates, they are also known as destructive plate margins. Destructive plate margin. Okay? Then, when the plates move away from each other, Whenever you have the case that the plates can move away from each other, volcanic eruption will create a newer crust. And that means a newer crust gets created, right? Or constructed. That is why it is also what is referred to as a constructive plate margin. It Then you also have the condition where the plates tend to move parallel with respect to each other, parallel to each. So when the plates tend to move parallel to each other, then they are known as transform plate. But in this case, neither a plate gets destroyed nor a new region gets created. So these are also what are referred to as conservative plate mark. It Okay. So these are the three types of plate move. In the case of convergent, when the plates are moving towards each other, you'll find that always the heavier plate tends to undergo some amount of subduction. There is some amount of subduction in the case of the heavier or the denser. Now, there can only be three types of convergences which can happen. You can have continental convergence, you can have oceanic continental convergence, or you can have oceanic convergence, right? That is, continental crust combines with continental crust, oceanic crust with continental crust, and so on. So here, as soon as one particular plate, the heavier one, that starts getting subducted. Why is there the case that the heavier one will undergo subduction? Because of the force of gravity. Force of gravity is the one which pulls it downwards. So you basically have the force of gravity which pulls them downwards. Once the plate starts moving downwards, that is when it tends to pull the rest of the plate along with it. Okay. Any portion which starts to undergo subduction, it will tend to pull the rest of the plate because of the component of gravitational force. So this is what is also termed as slab pull. Slab pull is basically the case of accelerated movement of the plates due to the subduction which is happening. Now, the examples of them: oceanic plate and the continental convergence. Here, you can take the case of the Pacific plate with the Eurasian plate, or the case of the Nazca plate and the South American plate, isn't it? So, let's suppose you take the case of Nazca plate and the South American. How does that happen? So, here, let's suppose you have the oceanic crust and you have the continental margin. Now, as this undergoes subduction here, there's a slight deformation observed in the case of the continental margin. It gets highly deformed due to the frictional. So here you will find a kind of a deformation. Materials tend to accumulate here, right? This is obviously the oceanic area. So here you also have the creation of fold mountains. Example, Andes, right? Now you also have the case of trenches. Example, Peru Chile trench, which is at the boundary of western part of South America. Now, as this plate undergoes subduction, it goes to the lower portion. It starts to melt ever so slowly. And that is when the molten materials being lighter, they start to rise up. As they start to rise up, they emerge to the surface and create volcanoes. Example, Mount Cotopaxi. Right, Mount Fuji, Mount Cotopaxi. These are the cases of examples of the oceanic continental volcanic eruption. Okay. Now, always remember that it is the oceanic plate which is heavier. Continental plate is not heavier because we have seen just now oceanic crust is made out of basaltic rocks with a density of 3 gram per centimeter cube. continental crust is made up of lighter granitic rocks with a density of 2.7 gram per centimeter cube. So always the oceanic crust is going to be heavier, will undergo subduction. Now, in the case when there is convergence between the two oceanic plates, which will undergo subduction, the older oceanic plate. Older oceanic plate is always going to be heavier. Why? Because over a period of millions of years, there is going to be formation of oxides, deposits, etc. The older oceanic plate is heavier. And that older oceanic plate undergoes subduction. Subduction. Okay? Now, in this particular case, the example Pacific plate and the Philippine Sea plate or the Caroline plate, in that particular case, what happens? You have the oceanic plate which undergoes subduction. There's a deformity which happens with the other oceanic plate, creating a deep ocean trench. There is no fold mountain created because the oceanic crust is very, very thin. The continental crust is thick. So, fold mountain formation will happen in the continental crust, but you won't have any folding in the case of the oceanic. Now, here, as the materials they subduct, they will again start to melt. And that is when the molten materials will tend to rise up and give rise to volcanic eruptions. This volcanic eruption eventually can grow larger and larger and can give rise to islands, volcanic islands. Example, the case of Indonesian and the Philippine archipelago that you have. They have been created as a kind of convergence or a subduction of the Pacific plate. Pacific plate being the older one is the heavier one which undergoes subduction. Now, in the case of continental convergence, what happens when you have continental? In this particular case, slight subduction will happen. Very little amount of subduction will. Take the case of Indian plate and the Eurasian landmass. So basically, slight subduction will happen. There will be heavy deformation because both of them are lighter, and there will be crustal thickening. Some amount of subduction, large amount of crustal thickening, and the formation of fold. Example, Alps, Appalachians, Himalayas, all of these, they have been created as a consequence. Ural, Pyrenees, they have been created as a consequence of continental convergence. Right? So here the example can be Himalayas. In the case of this continental convergence, no volcanic eruption is observed. No volcanic eruption. Only in the case of oceanic subduction will you observe volcanic eruption, not in the case of continental convergence. Only seismicity and high magnitude earthquake. Yes. Right? Why lighter subduction, sir? Lighter subduction does not mean lighter materials will sub. Lighter subduction here indicates very little amount of subduction will happen. Okay. In this, for example, take the case of Indian and the Eurasian landmass. Now, Indian landmass is much more denser owing to the volcanic eruptions which have happened in India over the past few million years. So, some portion of the Indian plate that undergoes subduction at the region of the convergence zone. Whereas the Eurasian plate being lighter, even though it is larger, but it is lighter, it stays on top. So, that is why some subduction does tend to happen. Okay. Now, the divergent plate boundary. The divergent plate boundaries are present where there is a lot of convection current. You have the movement away from each. A lot of convection current is present. Now, this ends up creating the cases of mid-oceanic ridges, rift valleys. All of them are created. So, rift valleys, a valley created due to the tensional force. So, ends up creating mid-oceanic ridges, right? Rift valleys. For example, if you consider the case of East African Rift Valley, the region where you have all those, the region of Lake Victoria. Then you have the case of Mount Kilimanjaro. So all those volcanic peaks which are there, they are present across the region of East African Rift Valley. So there's a convection current in the interior that is going to split the African landmass into two parts. So that is why you have the presence of rift valleys. Rift valleys created due to divergence. Okay. In the meanwhile, newer crust is created in the region between. That is why constructive plate margin. For example, take the case of the Arabian Peninsula and the Horn of Africa. If you consider the region of Horn of Africa, basically you have the Nubian plate on one side, Arabian plate. So Arabian plate is drifting away, right? So you have the zone of divergence. That is why in the coming future, Red Sea will expand furthermore. Across the regions of all the mid-oceanic ridges present across the world, you have these divergences which are happening. The fastest rate of divergence is happening in which part of the world? Yes, you will observe fissure volcano. Fastest rate of divergence is happening in which part of the world? Are we aware? That fastest rate of divergence is happening in the region here. That is the Nazca and the Pacific plate. Okay. So this is where you basically have the divergence at the rate of around 10 to 15 centimeter every year. This is your East Pacific rise or the Chilean rise. Pacific rise, or what is also known as the Chilean rise. Okay. That is the case of divergence. Now, here, as you can see, this is where the divergence tends to happen. This is the indication of the region of the mid-Atlantic ridge. Okay. Now, generally what happens wherever that zone of divergence tends to happen, not the entire plate is able to move at the same speed. The entire plate cannot move at the same, right? For example, if I give you the case of this one. Now, this entire region is moving east, and the North and South American plate are moving. Now, the Europe and the African region cannot move at the same. So, oftentimes there is a transform fault, a parallel fault which is, and that is known as the transform. Okay. So, in most of the cases, you will find that there is a transform fault which is perpendicular to the zone of divergence always. Right. So, transform plate boundaries, movement parallel to each. Okay. Now, in most of the cases, mostly perpendicular to the zone of divergence. Okay. Now, when you have the transform movement which is parallel to each. Now, in that case, oftentimes you will find that due to the friction force which is present, yes, Pooja, divergence happens because of the case of convection. Okay. Turkey earthquake is an example of the Anatolian plate having a transform. Yes. Okay. So basically, whenever you have the kind of transform movement or a parallel movement, you will observe there's so much of friction which is experienced in between them that oftentimes there's a large crack which appears. Now, these cracks, they become the zones of seismicity or earthquakes. So that is why in these areas you have very frequent earthquakes or seisms. Example, you can take the case around La Palma in the western part of Africa. You can take the case of San Andreas Fault in the region of California, right? So San Andreas fault is a large crack where there is a respective movement of the rocks with respect to each other. Okay? Now, these are the examples of the transform movement. So we have seen convergence, we have seen divergence, we have seen transform movement, we we have seen the entirety of plate tectonics. So fold mountains are created. Why? Because of continental convergence. Continental ocean, or continental continent. That is what will lead to fold mountain. Trenches are created. Why? Oceanic subduction. Oceanic, oceanic continent. Example, Mariana Trench, oceanic subduction. Peru-Chile Trench, the oceanic continental subduction. Then the Japan and Kuril Trench, oceanic continental subduction. Right? So, for example, the Andaman Trench, oceanic subduction. Volcanoes happen. Why? The case of oceanic subduction. That is why volcanoes occur. Mid-oceanic ridges due to divergence. That is why you have the mid-oceanic. Okay? Now, why there is no oceanic continental divergence? Because even if, let's suppose, there is the case of a convection current in the interior, the creation of a newer seafloor will happen. And eventually it will lead to an oceanic divergence itself. Because when you have the convection current from the interior providing that heat, molten materials will come out. So that is when there will be basaltic materials which will come out as a creation of the volcanic eruption. So always there will be oceanic divergence. The continental crust can drift apart, but eventually, like we see in the case of the Red Sea, right? As it drifts, water body gets created. Now the further divergence will always be the case of. Okay? Yes, Shripad, correct. These are your major plates. Now, something which has been mentioned frequently, even while we were discussing places in news, even in the current affairs always, this is the region of the East African Rift Valley. This is the portion which is drifting to the portion of the east, and this is the portion which is drifting to the north. That is the East African Rift Valley. Okay? Now, why no volcano in continental convergence? Because you don't have, unlike in the case of oceanic convergence, whenever you have oceanic convergence, some amount of molten materials they go into the interior. Some amount of, let's suppose, even when you consider the water from the ocean goes into the interior, that forms steam, provides the pressure to the molten materials, and you have volcanic eruption. But in the case of continental convergence, the crust is thickened, compressed, and as a consequence, even the slight amount of subduction which is happening, it won't be able to break through the thickened crust. So rate of subduction is less in the case of continental convergence, and also slight amount of molten materials, they won't be able to break through that thickened crust. We have talked about the fact that in the case of the Himalayas, the crustal thickness can be as high as 70 kilometers. Okay? Now, yes, Mitali, correct. After this, let's take a look at the question and let's see. This is the MCQ. I hope we will be able to mark this correctly. Now, here, the discontinuity and the location. Match the following in a correct manner. Tell me what is the correct answer. So, Conrad discontinuity between the upper and the lower crust. Moho discontinuity between the outer and the inner core. Repeti discontinuity between the upper and the lower mantle. And Gutenberg discontinuity between the crust and the mantle. Which of them are correctly matched? Do let me know. What is the correct answer in this? Beautiful. D. How come D? Correct answer. Conrad discontinuity is correctly matched, isn't it? Between the upper and the lower crust. Moho is incorrectly matched. Outer core and the inner core. No, outer core and inner core is a Lehmann discontinuity. Repeti discontinuity is correctly matched. Gutenberg is incorrectly matched. Crust and mantle is Moho, not Gutenberg. So here the correct answer is A, 1 and 3. Okay. This was a PYQ. I hope this everybody is able to solve. Which of the following phenomena might have influenced the evolution of organisms? So when we talk about evolution of organism, how do the organisms evolve? Organisms end up evolving as they experience different climatic conditions, as they experience different physiography. That is when the organisms evolve. So both continental drift as well as the glacial cycles, they help in evolution of organisms. Correct answer in this case is going to be C, both 1 and 2. This is another question associated, the PYQ, which are correctly matched in terms of the theory and the associated scientists. Continental drift, expansion of universe, and photoelectric effect. Now, in this particular case, continental drift was provided by Alfred Wagner. So even if you know this, you know that second one is not provided in a correct manner. So theory of expanding universe was provided by Edwin Hubble. So both of them are incorrectly matched. Photoelectric effect, Albert Einstein. This is basically three. B is the correct answer in this. Okay. Now, a simple question like this can also be thrown at you. Please don't get very surprised that how come this is this good fortune. But simple questions like this are also thrown at. So, in the structure of planet Earth, below the mantle, the core is essentially made up of which of the following? Please don't do mistakes in these kind of questions, right? So here, iron. Okay. Now, what is it that we have seen till now? Interior, structure, the geomagnetism, discontinuities, and all the theories. Now we come to the portion of earthquakes and volcanoes. What do we understand when we talk about an earth? Earthquake, in simplest of the terms, is the shaking of the earth's surface. The earth's surface, when it shakes, right, when it tends to move, that is an earthquake. Now, whenever there is a relative movement of rocks with regards to each other, with respect to each other, they experience a lot of resistance with respect to each other. Eventually, as they overcome that resistance, that is when you basically have the creation of the earth, occurrence of these earth. Okay. So when we talk about an earthquake, basically associated with the movement across, right? Let's suppose you consider this case of the rocks. If there is a movement here, let's suppose there is a resistance which is overcome here, that will generate or release a lot of energy. Now, that energy which is released, right, will hit the surface. That is what we experience in the form of earth. Okay. So, the point where the energy is released in the interior, that is known as the focus of the earth. The point perpendicular to the focus on the surface used for reference that where the earthquake has originated, that is what is referred to as the epicenter of an earth. Now, earthquakes are classified based upon the depth of the focus as well. So you have the shallow focus earthquake, where the depth is almost around 60 to 100 kilometers from the surface. You have the intermediate focus earthquake, that is up till a depth of almost 100 to 300 kilometers. And then you have the deep focus earthquake, where the depth is from 300 to 700 kilometers. Okay, so these are basically the three classifications based upon that the earthquake, where does it happen, right? So you have shallow focus, shallow focus, that is up till around 0 to 60 or 100 kilometer depth. Intermediate focus, that is 100 to 300 kilometers. And then you have deep focus, that is 300 to 700 kilometers. What happens underneath that? What happens beyond that depth? Can we have the portion of earthquake beyond this depth? We don't have. Because greater than this depth, you don't have the occurrence of earthquake. Why? Because as you move into the greater depth, beyond this, the materials get deformed rather than generating that friction or generating that amount of energy. So earthquake is restricted only up till around 700 kilometers from the surface. Okay, it is not necessarily molten, no. Beyond 700 kilometer, is the material molten, Mitali? Absolutely not. And Rahul, it is not molten. So please don't have that wrong idea. Okay. Molten material starts where? At a depth beyond 2900 kilometers. Beyond 2900 kilometers is where the material start getting molten. Okay. So the earthquake beyond 700 kilometer does not happen because at that particular depth, materials, rather than rubbing against each other and generating that energy, the materials will get deformed. Okay. Now, earthquake, how is it measured? Earthquake is measured in two different ways. One is the impact on the surface. Classification of earthquake based upon the impact and the destruction which is caused. Now, this is what is referred to as the intensity of an earthquake. Intensity of an earthquake is measured with the help of what we refer to as the Mercalli scale. You have the modified Mercalli scale as well, based upon what is the damage or what is the impact that you feel in the case of the shaking of the surface and so. And then, second, energy release, the amount of energy which is released. So, based upon that, you have the magnitude, which is measured on the Richter scale. Okay. Based upon the magnitude, you measure that on the Richter scale. Richter scale is logarithmic in nature. Okay. So, based upon the classification you have or the measurement, you have the Mercalli scale and the Richter scale. Mercalli represents the intensity, Richter scale represents the amount of energy or the magnitude of an earthquake. It is logarithmic. Logarithmic means what? Logarithmic. It means what? It basically means that an earthquake of magnitude 6 is 10 times, releases 10 times more energy as compared to earthquake of magnitude 5, compared to earthquake of magnitude 5. Okay. So that is what represents the logarithmic nature of it. That is the case of the Richter scale. This is your Mercalli scale, where depending upon how do you experience this, so no one feels that sometimes the shaking happens, which is not so intense, so nobody will even feel that. That is level 1. Accordingly, you have the 12 levels. 12th level means so much amount of shaking of the surface has happened that it has led to complete annihilation. Buildings have fallen, gotten destroyed, and so on and so forth. Okay? Now, whenever an earthquake does occur, it is not exponential, it is logarithmic. Richter scale is not exponential. There's a difference between logarithmic and exponential. Please don't get confused in that. Okay? Now, Amrendra Pratap Singh, why there is no zone 1 in the classification of earthquake distribution of India? This is something which happened as a change in terms of our classification of earthquake zones post the Latur earthquake in Maharashtra. Latur does not lie across a region of convergence or a plate margin. So Latur was not expected to experience an earthquake. But then when the Latur earthquake did occur, where you had a large amount of casualty in the terms of thousands, that is when the geologists, they wondered and they investigated and they found the presence of a fault line in that area, a crack which existed. So like that, people came to know that, or people came to a conclusion that there can never truly be a zone of no earthquake probability. There can be a zone where there will be less earthquake or less probability of earthquake, but it can always happen. Hence, there is no zone 1, zone 2 to zone 5 is the classification of the earthquake zone, right? India uses Richter scale. Everybody uses Richter scale. Everybody uses Richter scale for magnitude. Everybody uses Mercalli scale for intensity. Okay? If we create a dam on Indus River, it will create pressure on Indian plate. So, construction of dams in the region of the mountains always has got the danger of seismicity associated. Okay? Now, seismic waves. Whenever an earthquake does occur, there is a release of energy which tends to happen. Now that those are known as seismic. Now seismic waves basically are classified into two types based upon where do they happen. So for example, let's suppose you consider the interior of planet Earth. Let's suppose there is an earthquake which has occurred here. Now the energy will be released in this manner, will travel in all directions, isn't it? It will travel in all directions. Now these are the seismic waves which are traveling through the interior of planet Earth. So they are known as body waves. Okay, they are your body waves. Then when these seismic waves hit the surface, they will disturb the surface as well. So once they disturb the surface, that is when on the surface the waves travel. They are the ones which cause maximum destruction. They are known as surface. Okay. Now, furthermore, the classification is you basically have the P waves and you have the S wave, right? And surface waves, they are classified as L waves, Love waves, and Rayleigh wave, R wave. Now, where do the body waves originate from? What do you think? Where do the body waves originate? Body waves will always end up originating from the region of the focus. Originate from focus. Okay. But what about the surface wave? Where do the surface waves originate? Surface waves will always originate from epicenter, isn't it? Surface waves will originate from the epicenter because the seismic waves, the body waves will first hit the epicenter, they will disturb the surface, and then it will be generated. So here, originate from epicenter. Okay, so this is a significant classification. Now, when we talk about the P and the S wave, in the case of the P waves, you generally have the case where, let's suppose, if you consider the particles, right? Let's suppose here the focus tests. This is your focus. Now, when there is the occurrence of earthquake, this is the direction of wave propagation, direction of wave move, direction of wave. Now, how will they disturb the particles? Each of the particles, they are disturbed in the same direction as the wave motion. This particle will move to and fro. This particle will move to and fro. Like that, the particles, they are disturbed in the same direction as the direction of the wave motion. So that is where you will observe that the wave speed is very high. The P waves, they are amongst the fastest moving seismic waves. They move almost 1.5 to 1.7 times the speed of the S wave. And because the direction of particle motion is same as the direction of the wave motion, they will be able to move then through liquids as well as gases. So here, basically, you have the case of the direction of particle motion, direction of particles motion is same as direction of wave motion of. Okay. So as a consequence of that, you will basically observe that the wave speed is very, very fast, right? Now, then when we talk about the S waves, this is for the P wave. In the case of S waves, what do you have? In the case of S waves, if this is the focus, if these are the particles, then basically this is the direction of the wave, direction of wave. This is your focus. So here, the particles end up getting disturbed in a perpendicular manner. So that generates a wave, somewhat a sinusoid. So in this case, direction of wave motion is perpendicular to the direction of the particle motion. Hence, they are slow in velocity and hence they cannot move through liquids and gas. Because if a particle is moving like this in a liquid, a faraway particle might not be disturbed at all. Whereas in the case of P waves, if even if the particles are far away, if one particle moves like this, it will disturb the second particle automatically. That is why P waves are able to transition. So in this case, direction of particle motion is perpendicular of particle motion is perpendicular the direction of wave. This was a direct question which was asked last year in the prelims. Okay. Now, here, basically, the classification P waves or the difference P waves are the first waves to hit the surface. S waves, they arrive later. P waves have a speed which is around 4.5 to around 13 kilometer per second. S waves, they are around 1.7 to 2 times slower as compared to the P wave. When we talk about the P waves, these waves travel in a very linear direction as a result of compression expansion, right? Whereas S waves, they travel in a transverse direction. P waves can travel through solid, liquids, and gas. S waves will travel only through solids. Then, when we talk about the surface waves are the disturbances created on the surface, and they are the ones responsible for maximum amount of destruction, right? Now, they are classified based upon once the epicenter gets disturbed, that is when you have the wave motion on the surface. Now, on the surface, how is the disturbance happening? Is the disturbance happening in a horizontal manner or is a disturbance happening in a vertical manner? Right. So, accordingly, you have the classification into love and Rayleigh. Regarding the speed, P wave is the fastest, followed by S wave, followed by love wave, and that is followed by Rayleigh wave. So, P wave is the fastest. The surface waves are much slower as compared to the body wave. Now, what is the basic difference? In the case of love waves, you have a horizontal shaking of the ground surface. In the case of R waves, you have a wave-like motion which is generated in the case of the wave. So here you have the motion which is generated like this. Okay? So love waves, they are faster as compared to the Rayleigh. I hope till now we are able to understand, right? I hope this is clear. Yes, Ilma, that is correct. So P waves, they move like the sound waves in terms of motion, in terms of the particle motion. S waves, they tend to move like the case of light wave, right? Everybody is comfortable. We move ahead. Okay. Then the concept of the shadow zone. You see, when we talk about shadow zone, why can't move in water? Who can't move in water? S waves. Because the direction of particle motion is different from the case of the direction of the wave move. In liquids, particles are far away from each other. So if this one moves like this, the second one might not get disturbed. If it is disturbed slightly, the third one might not get disturbed at all. So how is it that the entire wave will propagate? That is why in liquids you won't observe the movement of the S wave. Now the concept of shadow zone. Which one is disruptive? Disruptive or destructive? Surface waves are always more destructive. Surface wave, always more destructive. Now, after this, we come to the shadow zone. What is a shadow zone? So basically, and why is it a shadow zone is created? So very simple, from the concept of refraction. All of you would have studied refraction in your childhood days, right? So when light enters the case of a different medium, it tends to refract. It tends to bend, isn't it? So basically, when energy waves travel through different medium, they tend to bend. Similarly, when you consider the interior of planet Earth, let's suppose there is occurrence of earthquake somewhere here. The energy waves will travel throughout the interior of the body, but they will encounter materials of different density. As they encounter materials of different density, they will tend to bend. Now, due to this bending, there will be certain locations where these body waves won't be felt or cannot be observed by seismograph. So, those regions where the body waves they are not to be observed, those are known as the shadow zone, right? So, when you consider the case of the P waves and the S wave from the same focus, both of them will originate simultaneously. Now, observe the bending which is happening. Now, here in this particular area, P waves cannot be observed because of the bending, because of the kind of refractive movement, so to say, on both the sides. But then in the case of S waves, there is a large area from 105-degree on one side to 105-degree on the other side with respect to focus, where you can't experience these S waves at all. So that is why. Why is it that S waves can't be observed in these areas? Because as the S waves will move, they will encounter the molten outer core. Molten outer core won't allow the S waves to pass through at all because S waves cannot travel through liquid, right? But the P waves can. So always, this is your shadow zone. So shadow zone of S wave is always greater, is always greater as compared to shadow zone of P as compared to shadow zone of. Okay, that is the case of these shadow zone. Okay, now then when you have an earthquake underwater in the region of the oceans, whenever you have an earthquake underwater in the region of the ocean, that earthquake underwater disturbs the entire oceanic system to such an extent it generates very large waves, and those large waves are known as tsunamis. So why do tsunamis occur? Due to earthquakes underwater. Okay, that is what generates tsunamis. Seismicity, which happens underneath the oceans, that is what generates the tsunamis. Be it the tsunami on 26th of December 2004, when it happened across the region of Indian Ocean, or be it the tsunami in the case of the Pacific Ocean impacting the region of Japan. Now, this is the global distribution of earthquakes. Now, where do earthquakes occur? In the zones of convergence, high magnitude earthquakes will occur. In the transform plate boundaries, high magnitude earthquakes will occur. In the zones of divergence, little earthquakes or shallow magnitude earthquakes will tend to occur. So these are your zones of earthquake. Then the Pacific Ring of Fire is one of those zones where frequent earthquakes will occur. Along with that, you have the Himalayan subduction zone. Frequent earthquakes will occur along with the Mediterranean region as well. That is the Italian peninsula. There also frequent earthquakes will occur. Okay. Now, earthquake zones of India. When we talk about the earthquake zones of India, so India is classified based upon the probability of earthquakes happening from zone 2 to zone 5. Zone 2, where the probability is very less. Now, in India, the most probable zones of earthquake are the Himalayan zones of convergence and the region of Gujarat. Why Gujarat? Because Gujarat lies at the boundary junction between three plates. That is, when we talk about Gujarat, Gujarat lies at the boundary zone of three plates, junction of three. Which are those three? So you have the Indian plate, you have the Eurasian plate, and you also have the Arabian. So because Gujarat lies at these boundary zone. That is why Gujarat experiences wind. Okay? Any movement across any of these plates will lead to earthquakes in. Now, then we will come to the portion of volcanoes or volcanic eruption. Now, volcanic eruption is basically when the materials from the interior of planet Earth, they basically come out to the surface. That is the case of volcanic eruption, right? Again, I have the same question, Elias. Why not zone one? I have already replied to this particular thing. Why don't we have zone one in the case of earthquake? We don't have the zone one in the case of earthquake classification of India because there is no place where you can say that there is very little probability of earthquake happening. There's always a greater probability, right? So that is why there is no basically zone one. You don't need to learn zone 2, zone 3, zone 4, which are the zones in terms of the case of where there is a high probability of earthquake. Just understand that which are the areas which are more probable in terms of occurrence of earthquake. Which are those zones? So the most probable areas are the regions of the Himalayan subduction, where there is a continental convergence, and the region where there is a kind of a plate margin in terms of multiple plates being together. Okay, I hope that is clear. Do we have well developed accurate system? Nobody can predict earthquake. Earthquakes cannot be predicted. Earthquakes cannot be predicted. Okay, you can have the case where you can understand or triangulate the zone where the earthquake can occur, but you cannot predict the exact timing of the earthquake, right? Okay, fair enough. Now we come to the portion of volcanoes. Volcanoes basically, could we go slightly faster? Would appreciate more focus on landform and Indian geography. Antara, is that the consensus of everyone? Are you representing everybody's intention here, or it is your own consensus that you're representing? So that is why we will go for comprehensive revision. Okay, everything will be covered, right? Because there were many who talked about the revision of this part. You would prefer something else. Someone would prefer climatology. So that is why everything will be covered. Okay, so please play along. Now, volcanoes, they are classified based upon the frequency of the eruption into active, dormant, and extinct. Active, magma chamber is full. There can be eruption which can happen or which has happened in the recent past. Eruption can happen again. Example, in India, the Barren Islands volcano. Barren Islands in Islands volcano. After this, we'll take a break before landforms. Don't worry. Okay. Now, dormant, where the eruption has happened long time back, can happen in the in the future again. That is dormant. And extinct, no longer any possibility of any further eruption at all. So that is the case of the active, dormant, and the extinct volcano. Now, when we have the volcanic eruption, you have various different types of landforms which are created as a consequence of volcanic eruption. You have the cinder cone volcano, which are not very large, which are small in size, almost up till a height of around 1,000 feet, and that's it, right? So, this is basically a conical shape, small kind of landform. That is the case of a cinder cone. The example Mount Tal in Philippines can be taken as an example of cinder cone. Then you have the largest of the volcanic eruption in the form of composite, what are also known as stratovolcano. Stratovolcano. So here you have multiple layers of these eruptions which have created a layer of ash, a layer of solidified magma. So you have these multiple layers which are created. Some of the largest landforms created by volcanoes are basically composite volcanoes. Example, you have the case of basically Mount Fuji, right? All of the Mount Pinatubo, all of them can be example of stratovolcano. Then you have the shield volcano. Shield volcanoes are the ones which are also known as the Hawaiian eruption. So basically, in this case, what happens is that fluidic magma emerges out and spreads over a larger area. Right? For example, flood basalt provinces are created in this. Example, Deccan Traps, Deccan Traps, Canadian Shield, etc. So here, a kind of a uniform topography land feature gets created. So in this case, you have fluidic magma which emerges, fluidic lava spreads. Now this fluidic lava basically will be made out of what? This will be your mafic lava. Mafic is the one which is fluid. So that would be inclusive of iron and magnesium. The density will be very high. It will have very low or basically high fluidity, hence fluid. Okay, that is the case of shield volcano. You have the lava domes which are created, very viscous material. Okay, very high viscosity. So here you have the eruption, and that ends up creating a kind of a lava dome. Very small features which are associated with that. For example, Lassen Peak in the region of California. That is the example of a lava dome. Very small relative feature which is created. Okay. In terms of the size, the altitude, composite volcanoes will be larger, Kunal. In terms of the aerial spread, shield volcanoes can be much. Okay. Fissure volcanoes. Fissure volcanoes are when you have large cracks which open up on the Earth's surface and molten materials start to emerge out of these large cracks. Those are your fissure volcanoes. Okay. So here you have the case of generally observed in the zones of divergence. For example, you can take the case of two examples. Laki eruption, Iceland. That is the case of a fissure eruption. And then after that, you also have the case of, for example, when we consider the Travera eruption in the region of New Zealand. So there, in the zones of divergence, you have the fissure eruption. This is also what is referred to as Icelandic kind of eruption. This is what happens in the region of Iceland as well. So this is also what is referred to as Icelandic eruption. Okay, non-explosive eruption, fluidic lava comes out and spreads over a large distance. Then you have what is referred to as a caldera. So when we have a caldera is what? Caldera is a kind of a landform created during very explosive eruptions where the central portion simply caves in. And that happens because of the emptying of the magma chamber. Okay. So here what happens is that you have the emptying of the magma chamber. So let's suppose you have a volcanic eruption like this, right? Now, the magma chamber during one of the eruptions becomes empty. And if the eruption is very explosive, then there will be a crack which will appear across this region. And the central portion might cave in altogether. So the landform that you will have will be a remnant like, because the central portion has caved in as the magma chamber is empty. This creates a caldera. So calderas are created when the magma chamber is empty and the eruption has been so explosive that the central portion has caved. Now, in the case of caldera, can there be a future eruption which can happen in this area? In the case of a caldera, what do you think? Can the calderas experience future eruption or no? Always. Always, calderas can have a future eruption, provided that there is fresh recharge of the magma chamber, so it can always lead to fresh eruption. Okay? Now, then comes the portion of mantle plume. What is mantle plume? So, in the region of the mantle, we have seen that due to the convection current, that you have the rising molten portion. Molten portion of the mantle rises up like a bulb like an arrowhead upward. And that can generate a convection current that can initiate a plate movement, and those are known as mantle plume. Mantle plumes basically can be present in two different places, can be generated from two different places. Can be generated from where? Can be generated from Gutenberg discontinuity, Gutenberg discontinuity, and secondly, can be generated from asthenosphere. Okay? So in both these areas, from both these areas, mantle plumes can be generated. Okay, once the mantle plume is generated, it can lead to volcanic eruption. It can lead to plate movement with respect to each other as well. So mantle plume is a convection of magma in a narrow column in an upward direction from the core mantle boundary, forming a mushroom-shaped cap to the plume. Now, in regions where you have the mantle plume, those regions experience volcanicity for a long duration of more than millions of years, maybe 100 million years, maybe 200 million years, like that. So, those areas which experience frequent volcanicity over a long period of time by virtue of lying over the mantle plumes, those are known as volcanic hotspots. Example, you have the Hawaiian hotspot in the region of the Pacific Island, in the Pacific Ocean. You have the case of the Reunion Island hotspot in the region of Indian Ocean. So those are your hotspots. So hotspot is a volcanic area on the Earth, exists over the mantle. So here you have the Hawaiian hotspot example. Hawaiian hotspot. Viscosity means ability to flow. Take the case of honey and water. You pour them together, water flows easily. Honey does not flow easily. Honey is viscous. Water is not viscous. That is viscosity. So here, example, Reunion Islands in the region of Indian Ocean. Okay. And then Hawaiian Islands. Both of them are example of hotspot. Okay. Now, after this, the intrusive volcanic landforms. What are intrusive volcanic landforms? Whenever you have molten materials which solidify in the interior itself without coming to the surface, they form what is known as the intrusive volcanic landform. Now, intrusive volcanic landforms are classified based upon the shape in which they solidify. They are visible to us when the upper portion above it gets eroded, gets withered, or gets removed. So, that is the case of the intrusive volcanic landform. They are classified into batholith, phacolith, laccolith, lopolith, sills, dike, sheets, etc., based upon the shape in which they have solidified. In case the entire magma chamber in itself solidifies, then it is referred to as batholith. It forms a kind of a dome shape formation when the upper areas are removed. So batholiths are formed by the solidification of the entire magma chamber. Solidification of entire magma chamber. Okay. That is what forms the batholiths. Right? Example in India, Ranchi batholith, where you have the presence of the famous rock garden. So Ranchi batholith is an example of. Okay. Now, then you have the laccolith. Laccolith is where the solidification happens in such a way that the molten material forms a kind of a dome. It might have been connected to the underlying magma chamber, but it is flat from underneath and a dome-like shape above. That is laccolith. But in case you have a flat top and a concave bottom. So here, in the case of a laccolith, you have flat bottom and a kind of a convex kind of a top. This is the shape of a laccolith. But if you have a flat top and a kind of a concave bottom, this kind of a solidified structure, That is known as flow pullets. Okay. So flat top and a shallow convex base. Now, if you have a solidification which happens across the anticline and the synclines of the folded structure, forming saucer-like shapes, those are known as facalith. Okay. So here, now you will have the presence of the facalith. So here, solidification has happened across the anticline and the syncline of the folded structure. Now, sills and sheets. So basically, many of the times the molten materials, they end up solidifying in the horizontal structure. Now, if they solidify in very thin parts, if they are thin, then they are known as sheets. If they are thick, solidified portions, then they are known as sills. When the solidification happens in a horizontal manner. So this is basically your sill that you see. Okay, that is your sills. Then after that, when the solidification happens in a kind of a vertical manner, that is when it is referred to as a dike. When you have a vertical solidification, that is known as a dike. So these are your various intrusive landforms. Then basically you have the classification of magma or lava based upon the chemical composition. So based upon the chemical composition, you have felsic and mafic. Mafic is what? Mafic, the name in itself, is derived from a rich constitution of magnesium and iron. That is mafic. So this is basically high density, high density, dark colored, dark colored. This basically will have greater fluidity, fluidic. Okay. Whereas when we talk about felsic, feldspar and silica, silica is high, right? It will have low density, then light appearance, light color upon solidification, colored, viscous, doesn't flow easy. Okay, so mafic is generally associated with non-explosive eruption, and felsic is associated with explosive. This is the general classification. Okay, now this is the table associated with the mafic and the felsic. You can see mafic one, non-explosive, gas content is low, viscosity is low. That means it tends to flow easily. Felsic, explosive, gas content is high, viscosity is also very, very high. Now, these are the regions where generally volcanoes are experienced. So, volcanic eruption is experienced in two of the main zones. One is the Ring of Fire. Why do we experience volcanoes in Ring of Fire? Because of oceanic subduction, which is happening from all sides. The second is in the region of basically Mediterranean. So around the Italian peninsula, again because of oceanic subduction which is happening as the African plate is moving north. But you also have this in the zones of divergence. Zones of divergence, for example, in the mid-oceanic ridges, in the region of even the volcanic hotspots, these are the areas where the volcanic eruptions will tend to occur. Okay? Now we will come to the portion of the landforms and important landforms associated. Before that, we will take a break. We'll take a break for 30 minutes. So till now, everybody is comfortable. Any issue in understanding the portion till now? Mafic is less viscous, yes. Why do mantle plumes cause different volcanic features compared to the subduction zone? Because mantle plume will provide molten materials for a much longer duration and at a much higher temperature as well. Yes, Pranay. Mediterranean Sea is going to disappear. Types of rock, no. Types of rock basically If you consider the case of igneous rock, intrusive, extrusive, or if you have to further classify felsic, mafic, ultramafic, sedimentary, clastic, organic, chemical, metamorphic, you have the foliated, non-foliated. Types of rock are very simple, not required to be covered. Material released from a volcano. So in that case, you have the case of gases which are released. Uh, in the gases, you have methane, carbon dioxide. The most dominant gas is water vapor. Then you have pyroclastic materials and the molten material. Okay. You want me to put this particular slide on? Okay. Fair enough. After this, so basically here, we take a break and we take a break for 30 minutes. Why the mafic is less viscous? Because it is made out of the denser materials which don't have the gas trapped in them. So that is why they flow easily. It is not buffering as of now. I'm able to see it with on my end as well. So break. Come back after 30 minutes. We will start with landform and go into climatology. Okay. So we will come back at 5:10. At 5:10. Okay, so welcome back after the break. So now we continue with the discussion of the various important landforms. Now, this can be vital for your prelims in the sense that here you can have a question associated with which agent of nature has created which kind of landform, agent of nature, which has created a certain type of landform. And when I say agent of nature, here basically referring to the case of rivers, which ends up forming fluvial landforms. Then the case of underground landforms created due to the impact of water. That is also what is referred to as the karst topography. Karst topography. Then the glacial landforms which get created. Then the landforms which are created as a result of the action of the seawater, right? So you have the coastal landforms, and then you also have the case of aeolian landform. That is the landforms which are created as a consequence of wind action. So these are the different agents of nature which end up creating landforms. So you can have a question which can be framed in a manner that, for example, you have the listing of uvalas. Now, uvalas are created by the action of A, river, B, glacier, C, underground, or D, coastal. Like that, this can be a kind of a question frame. Other framing of the question can be that whether any particular landform is erosional or depositional. Erosional or deposition. Okay. So that can be another classification of the landforms as well. It can be erosional or deposition. Now, in this particular case, you have to understand and keep one thing in mind. It is not buffering. I have opened up the stream alongside me as well. So it is not buffering. It's absolutely clear, right? Please check the connection at your end. Now, basically, we have to keep in mind that the landforms which get created, the landforms are created as a consequence of the process of gradation. Gradation. Now, when we talk about gradation, gradation is a combined action of degradation or erosion, transportation, and deposition. Transportation and then deposition. Okay. Now, what will be the erosional capability by any agent of nature? How do you decide whether any agent of nature will be able to erode more or whether it will be able to erode less? So, that is something which is decided based upon the speed. For example, when the river is moving at a very high speed, it is able to erode and carry more materials along with it. So that is where erosion will be high. If a river is moving at a lesser velocity, lesser speed, then it won't be able to carry those many substances along with it. So it will start dumping them. And hence you have the formation or the creation of depositional landform. So there, a very important concept works, and that is the carrying capacity by any agent of nature, be it wind, glacier, river, anything. Carrying capacity is always going to be directly proportional to the speed of move of the agent of nature. So if the speed of movement of nature is high, the carrying capacity will also be high. If the speed of movement is less, then basically there will be deposition. So always, if speed is high, whenever the speed is high, it will lead to erosion. Whenever the speed lowers, speed is less, it will always lead to deposition. Okay. Now, we will take a look at the landforms created by these individual uh, agents of nature as well. Okay, so here, when we talk about the agents of nature. For example, the rivers. Rivers end up creating what are referred to as the fluvial landform. These are your fluvial landform. Now, when we talk about fluvial landforms, understand this. Basically, they can be erosional or depositional in nature, right? Now, majority of these erosional landforms that you see, they will be when the river speed is very high. River speed is very high when? In the youthful stage. So almost all of these that you see, they will be created in the youthful stage of the river movement. Youthful stage of the river movement. Incised or entrenched meanders, as well as the river terraces. River terraces and the incised entrenched meanders, these are the only two ones which are formed during the mature and the late mature phase. River terraces. These are formed in the mature or the late mature. Okay. Then, when we talk about the depositional, they will be created when the speed lowers down. That is in the case of the mature and the old stage. So almost all of them that you see, all these landforms that you see, will be created in the mature or old stage, barring one exception. That is the alluvial fan. Alluvial fans are the only landforms which are created while the river is still in its youthful stage. Youthful stage. Okay. One by one, let us take a look at each one of them and let us try to understand that how do they get created? How do they come into existence? Okay. Now, starting with the valleys and the gorges. Now, valleys, basically, if you observe, this is the image of a valley. And this is the image, what you associate with a gorge. So, valleys, you will observe they have a wider bottom, a broad base, right? And a gentler incline. Okay. So, that is the case of a valley. Whereas when you talk about a gorge, gorges will be almost steep, narrow bottom. Okay. That is something you will observe in the case of a gorge. So, this is the basic difference between the valleys and the gorge. Over a period of time, a gorge can always get converted into a valley. How? That is over a period of time. Let's suppose there is weathering which occurs across this entire area. The materials break down into smaller particles. And then you will find that those materials, as a result of mass wasting and mass movement, they are brought down at the bottom of the valley. So, in that case, the gorge ends up getting converted into a gentler gradient, broader bottom, what is referred to as a valley. Okay. Now, then you have the case of the potholes and plunge pools. So, how are potholes created? Potholes are also created in the case of the youthful stage. Now, these are small, narrow depressions which are created on the river bed. Now, this tends to happen when, if you consider the river movement, let's suppose in the youthful stage, this is the river movement. Now, the river will be able to carry and bring with it large stones and the large rocky pieces. Now, these stones and rocky pieces will drop on the riverbed and will be dragged across the riverbed. As and when they hit, they will create a slight depression. Now, the smaller stones and pebbles, they will eventually end up widening that depression. And that is how you have the formation of what is referred to as a pothole. Okay. That is how potholes get created. So, riverbed at the youthful stage. Okay. The youthful. Then you have the plunge pool. Now, when we say a plunge pool, so how is a plunge pool created? So, plunge pools are created at the base of a waterfall. Now, when you consider a waterfall anywhere, waterfall mostly is present in the youthful age. But if you consider a waterfall, now as the river water drains into this area, it falls over an elevation and then drains away. slowly and steadily the velocity and the force of water will end up creating a kind of a depression here. Will end up creating a kind of a depression here. And that is where the deeper formations will be observed. And these are known as plunge pool. Plunge pool. Okay. So that is how basically plunge pools are observed and have been found to be created. Again, typically in the youthful stage of the river move. Now, here basically you will observe that how generally a waterfall ends up getting converted into a type of a plunge pool. So in this particular animation, what you will be able to observe is that as the water flows in the region of the softer rock, they will continue to erode it. That leads to the creation of a waterfall. Over a period of time, the velocity of water and the force indicated by water, that ends up creating a kind of a depression. I hope everybody is able to take a look at this animation. So there at the base of the waterfall is where you will observe the formation of these plunge pools. This is where it gets very deep all of a sudden. Then you have the formation of incised meanders. Now, incised meanders, they get created in either the mature, late mature phase also. Now, whenever the river forms a kind of a meander, in those particular areas, if let's suppose due to endogenic activities, there is an upliftment of landmass. Now, that upliftment of landmass, it will ensure that the water keeps on carrying a vertical erosion in the same area. To simplify it further, let's suppose you consider a region. Let's suppose you consider a region here like this. Now let's assume that here you have a river flow forming a meander. Now, if in this particular location you have the upliftment of land due to the endogenic processes which are happening, there is a kind of a general upliftment of land. Now, in this particular case, where the river is flowing, that riverbed will also get uplifted at a small rate. It will not be massive. The rate of upliftment is generally around 1 centimeter every year, or maybe 1 millimeter every year, or even slower than that, 1 millimeter every decade. So, like that, the rate of upliftment is very slow. So, the riverbed will be continuously eroded by the river action. But surrounding the riverbed in these areas, there is nothing to erode the uplifted portion. That is why, after a while, you will observe that the surrounding regions have risen up. The surrounding regions have risen up, whereas the river will maintain its original course. So, here, which kind of erosion is observed? You basically have vertical erosion on the riverbed carried by the river. Vertical erosion on the riverbed. On the riverbed. Okay? Is there an issue with the buffering? Is the audio and the video not clear? Any issue with that? How many of us are facing this? And how many of us are finding the video to be uninterrupted? Do let me know. Okay, if I can take a look at it's perfect. It's fine now. Microseconds once in a while. So in the case of microsecond kind of buffering, is that disturbing the entire flow? Is it? Pranay, what is the need for pole in this? If it is buffering, it is buffering. If it is not buffering, it is not buffering. No buffer at all. Okay, it happened at intrusive landform. Okay. Is that required? So from our side, everything is streaming perfectly well. Try to take a look into it for a brief moment. If it is still very disturbing, do let me know in the comment section. In that case, we will end the stream and we will restart the stream again. But I hope it doesn't come to that. Okay? Because from our end, everything is showing fine. There is no tech issue whatsoever. So do take a look at it again. Most of you are saying it is not buffering. Most of you are saying it is fine. Okay. So please do refresh at your end. Please check the Wi-Fi connection at your end, internet connection at your end, and it should be fine. It is clear now. Okay. Adjust the resolution also if required. Okay. So now, basically, we come to some of the depositional landform. So when we talk about the depositional landform, so here in the youthful stage, you have a depositional landform, which is referred to as an alluvial fan. So when we say an alluvial fan, what is it? So basically, as the river comes down the mountains, it brings along with it large amount of materials, right? Larger rocks, boulders, etc. Now, as long as it is coming down the mountain slope, it is having a very high speed. So because of the high speed, the river is able to, or the stream is able to carry all those materials along with them. But the moment it hits the plains, at that point of time, you will observe that basically the materials are not being able or are not able carried by the river anymore. And the river is unable to carry them. The river dumps all of them at the base of the mountain, at the base of the hill. So this is what forms the alluvial fans. Now, in many of the areas, particularly the Himalayan rivers, you will find large alluvial fans which are created. Oftentimes, now the name is given owing to the shape of the deposit. The shape of the deposit is typically in that of a semicircle, and that is made out of larger materials, larger particles. Okay. Now, then you have an erosional cum depositional feature, which is known as a river meander. So when we talk about meander, a river meander, it is a result of both erosion as well as depositional feature. Okay. So here, basically what tends to happen is it is present or it is to be found in the mature stage, mature and sometimes old stage, sometimes old stage. So here, as the flow speed is reduced in the mature or the old stage, the river tries to find a path of least resistance. And in that process, it ends up forming a wavy striated path or a wavy pattern, which is referred to as the kind of the meander. Okay, right. Is it buffering again? See, I am having it live in front of me. It is not as if I am simply opening up the stream. I'm having it live in front of me. I have opened up the stream in front of me. It is not buffering at all. So that is why I am saying it is not buffering from my end. Okay. It's clear, right? Perfect. Right. Okay. So basically, a meander is formed in the mature and sometimes in the old stage. That is where a meander is created. Now, a meander generally is created as a consequence of a slow speed where the river tries to find a path of least resistance. It will deposit materials at those ends where the speed is slow. That is why it gains a wavy meandering pattern or a pathway. Also, along with that, you will observe that there is a kind of a general movement, a curvilinear movement in the case of large rivers. In the case of large rivers, Coriolis force also plays a minor role. But in the case of smaller streams, Coriolis force does not come into play. In the case of very large river, that circular movement associated or the bending movement associated with the water flow, that also comes into. Okay. Now, here, when you have a meander which is significantly exaggerated. Sometimes what happens is that the river tries to find a shortcut. The water finds a shortcut and a shorter path to move. And as a consequence, it ends up separating one portion of the meander. Now, when that portion of the meander is separated, that is what is referred to as an oxbow lake. So, oxbow lake is a cut-off portion of the meander which has been cut off as a result of deposits. Okay, as the water forms a shorter way of movement. That is the case of the oxbow. Almost in all the various different types of uh, rivers moving through the plain areas. For example, if you consider the Indus River system, if you consider the Ganga River system, if you consider the tributaries of them, they will have these oxbow lakes and the meanders as well. For example, the Kanwar Lake in, or what is referred to as a Kanwartal in Bihar, which is an important Ramsar site as well. So there also you will find the presence or the predominance of a kind of an oxbow lake. Okay. Now, this is what you have as the case of an oxbow. Okay. Now we see what we have seen till now is that when the speed is slow, when the speed is very, very slow, this will automatically lead to what? High deposition, higher deposition, isn't it? The amount of deposition will be very, very high. Now, when is it that the speed will be very low? Speed will be very low in the late mature or the old stage of the river movement or the old stage of river movement. So, when you are basically in the older stage or when you observe the older stage of the river movement or the late mature stage of river movement, let's suppose this is a river which is moving like this. This is the stream. Now, if the speed is very slow, you will observe that deposits will start to happen within the river channel itself. In the pathway of the river flow itself, you will have various different deposits of silt, sediments, etc., which will happen. As a consequence of this, the flow will be reduced to small channels rather than one large channel having a river flow. So these are what are referred to as the case of braided channels or braided streams. So these braided streams are generally observed in the late mature or the old stage of the river move. Okay, so here you won't be able to distinguish which is the main stream of flow. All these are deposited sediments, deposits within the river channel. River channel, where the main stream appears to have many such small subsections, isn't it? Many such small subsections. So these are known as what you see in the image here. These are known as braided streams or braided channels. So when we talk about the Ganga river system, the Brahmaputra river system, particularly in the area of Bangladesh, they end up creating large amount of these braided channels. Then one of the final depositional feature, which is created as a consequence of deposition as the river meets the sea, that is the delta. Delta will consist of the finest particles of sediment, because this is where, as the river meets the sea, the speed almost reduces to zero. So whatever amount of material that the river was carrying, it will be dumped here. So as a consequence, you will have these delta-like formation. The name delta is associated owing to the triangular shape in most of the cases that they end up creating. These are very fertile, finest of materials, because larger materials will be dumped earliest. As soon as the speed reduces, larger materials will be dumped. But as the river flows, finest materials will be carried by the river, will be dumped at the end. So here, very fertile, finest materials, finer materials. Now, depending upon where, or basically what is the property of the river, what is the property of the nearby larger sea or the ocean, these deltas, they are of different types. They can be classified as the arcuate, cuspate, bird foot delta. All of this is a classification of delta, not required to go into detail for the GS. So all these basically that you observe is where the river flow is determining the shape of the deposit. For example, if let's suppose you consider a river which is coming like this, and the stream is very, very fast. This is the land area, and this is the region of the sea. Now, here, the deposits which will be created, if the speed is very high, the deposits which will be created will be slightly linear, extended because of high speed of the river flow. So the delta which will be created appears like the shape of the bird foot, and hence the name bird foot delta. So like that, the delta also has got various different shapes, but primarily created why? When you have the case of the stream meeting the sea and the speed almost reduced to zero. Example, Sundarbans delta, Krishna Godavari delta, Mahanadi delta, all of these are examples of large deltas. Now, then, what is an estuary? So, estuary is basically those kind of features where the sea water comes inland. As the river meets the sea, if this is the sea, this is the land, and this is the river. So, in certain low lying areas, the sea water comes in, okay, as the river is draining. So, this particular extent, this is an estuary. Estuary can have deposits, but delta is the name of the deposit. Okay, so this is your estuary. Okay, that is what you have as the cases of estuary, right? I hope that is clear. And so estuaries basically are also ecotones. Ecotones in the sense that here you have the mix of the saline water of the sea with the fresh water from the river. So that is where they are very vital regions of biodiversity. Will have large abundance of biodiversity in this particular. Okay. Now, just a moment. So, just a moment. Can this? So now, just let me know if I can take a look at the comments. Is it still buffering? We have restarted the stream now. So we have stopped the stream and we have restarted the stream. Is it okay now? Any issues by anyone? All good? It's fine. It's clear? Okay, fair enough. So now I hope we can continue without interruption. Bunny, we have restarted the stream again. We have stopped the stream. We have restarted the stream again. Yes, Prabhat, it is visible. We have restarted the stream, Neeraj. Thank you for the technical inputs that all of you are providing, but we have restarted the stream again. Okay? Now, so estuaries are regions of ecotones, ecological abundance. Very high amount of biodiversity is to be found in the region of estuaries. Deltas are your deposits. Okay? So that is the case of the basic aspect of deltas and estuaries. Okay? Now, then we come to the landforms which are developed by the underground water. That is what is also referred to as the case of karst topography. Karst topography. Now, here what tends to happen is that when we talk about water or in the underground region, wherever you have water soluble rocks or water soluble minerals, in those areas, there is a kind of a chemical erosion, right? So, there you have a case of chemical erosion by water. Now, wherever there is erosion, there will be creation of these erosional landforms. You have erosional landforms like sinkholes, uvalas or valley sinks. Then you have poliers. Then you have lapis, dolines. All of these are examples of erosional landforms. Now, in certain cases, the chemical solution which is created as a consequence of erosion, they then get deposited as a consequence of that solution evaporating. Water tends to evaporate, leaving behind those condensates. So that is what leads to formation of depositional features like stalactites, stalagmites, columns, pillars, etc. So that is the case in between basically erosional landform and depositional landform. So here, when we talk about the erosional and the depositional landform, so you see the in the case, as you can see here, the water is moving wherever it finds water soluble rocks. There, the water is able to percolate and end up eroding all the materials underground, creating a large area of erosional caves and such erosional structure altogether. Okay, so here basically, initially, when you have the impact of the water and the role of the water, in that particular case, when you have the role of the water, in that case, the water starts to, the water begins to basically dissolve certain materials. Now, as the water dissolves certain materials, eventually you have large sinkholes which get created. Right. So that is where you have very large depressions which are known as sinkholes. So these sinkholes they get created. Continued erosional process, what it leads to is that these sinkholes they can join together. As the sinkholes they join together, they end up forming a continued valley of erosional landform. Those are known as the valley sinks, or those are what are also known as uvalas. So uvalas can be referred to as a combination of multiple of these sinkholes. You also have what is referred to as the lapis. What are lapis? So again, in water soluble structure, when you consider a kind of landform which is made out of, let's suppose, limestone, etc., where calcium and other minerals and materials can be dissolved in water. So, in those water soluble structures, due to excess rainfall or due to excessive flow of water down the slope, oftentimes the soluble materials they get eroded. So the soluble materials, as they get eroded, they end up carving a kind of a depressed feature, a depression like feature. So those are what are referred to as lapis. So here, basically, lapis are corrugated or rough surfaces formed in the limestone bedrock with low ridges and very little amount of pinnacles. Okay. Okay, we'll do one thing. We will, right. It is getting interrupted, is it? Lot of interruption is happening in this. Let me see. See, most of you are saying it is fine. Few of you are saying that it is not good. You are basically vehemently associated with the fact that it is not fine. So it's all good from my side. Before this, it was buffering. Now it is not buffering. Great. Now, okay, fine. It's fine. Not able to watch even 5 minutes. Stopped once, but then I refreshed and it is running smooth. After refreshing, it is working. Please continue. It is manageable. From phone, it was buffering. Okay. Sometimes it is buffering. Manageable. Just a moment. Let us see. Take a break of 5 minutes. Let's see. I hope it is fine now. Do take a look. I hope everything is fine. Fair enough. Right? Okay, perfect. So now basically, we were talking about the sinkholes. Sinkholes initially get created when you have the rainfall which falls on a region, or let's suppose a water flow in a region that dissolves the soluble rocks. Rocks such as, for example, limestone rocks or any of those materials which can be dissolved in water. So, as a consequence of that, the sinkholes they tend to get created. Over a period of time, these sinkholes can get merged together, and that ends up forming a continued valley sink. And that valley sink is what is referred to as an uvala. So an uvala is a combination of multiple different sinkholes together that forms a continuity, right? Now, after this, we come to the lapis. So in the limestone beds, basically the frequent occurrences of rainfall ends up eroding the portion of those limestones. And as a consequence, you have a corrugated rough patch which is available with corrugated ridges and sorts. Those are known as lapis. Now, these kind of karst topography you will find in India in the region of Meghalaya. You will also find it in the region of Karnataka, particularly around the region of the Yana caves. So these are where the limestone rock beds are to be found. Other areas in South Asia, for example, Thailand, you will find a lot of them. Scottish Highlands, you will find those. So wherever you have the limestone rock beds and the availability of water in abundance, these kind of karst topographies are created. You also have what are referred to as the dolines and the poliers. So basically, dolines are what? So when we talk about a doline, as you can see in the image here, the dolines are basically enclosed depression of soil. That is what a doline is. So that is what basically refers to or is referred to as a doline. Uvala, we have seen coalescence and convergence of multiple sinkholes forming a kind of a valley sink, right? Multiple dolines and sinkholes get together to form an uvala. Then you have what is known as a polye. Now, in the case of a polye, elongated basin having a flat floor and steep walls on the sides. Elongated basin having steep walls. So there's a kind of a depression in between and the coalescence of several sinkholes, right? So those are your kind of erosional features, erosional landforms which get created. In the meanwhile, when we talk about the depositional landforms, you see, one of the erosional landform is that of a cave. Okay, caves get created. Now, let's suppose you consider a kind of a cave-like structure. Okay. Now, in this, as water, let's suppose there is rainwater which percolates through rainwater, which tends to move through like this, dissolving the limestone-based rocks, etc. The limestone rocks they get dissolved. Eventually, the water forms droplets on the roof of the cave. Right. Now, from here itself, water can get evaporated. As the water gets evaporated, it leaves behind a series of deposits which appear to be hanging like icicles from the top of the cave. And those are known as stalactites. Okay. So, stalactites basically are the perpendicularly present, the kind of structures which are protruding from the roof of the cave. Always remember that. So, stalactite, vertical suspended structures from the roof. Vertically suspended structures from the roof. Okay, of the cave. Those are stalactites. Now, if the water basically falls on the ground, on the surface, and after that, the water evaporates. Now, as the water evaporates thereafter, it leaves behind some of the materials, right? So these materials, they accumulate, they build up. These materials, they build up, and those are what are known as stalagmites. So stalagmites are perpendicular structures from the surface. Stalactites, they are suspended from the roof. Stalactites, they emerge from the ground. Both the stalactites and stalagmites can combine together to form what is known as a kind of, basically, a pillar. Okay. So that is what is known as a pillar or a column. So a pillar or a column is a combination of both stalactites and stalagmites. Now we come to the glacial landform. Now, when we say a glacial landform, salt chimneys are not karst topography. No, Mitali. Salt chimneys, they are basically what you find in the case of the Dead Sea. Now, there you have the condensation of, or the precipitation of the excessive salt in that region. So they cannot be regarded or categorized into the portion of karst topography. Okay. Um, then the water evaporation happens from the underground surface. It also adds to the salinity level of the soil. Yes, it can. It can impact the salinity level of the soil as well. Dolines MK are basically, think about it, a slightly longer depression, in the same manner as sinkholes are created, slightly larger. That is what dolines are. Okay. Backwaters and lagoons, lying areas of the coastal ecosystem where the seawater enters inland, those are your backwaters. Okay. Right. Um, I hope that is clear. Any other doubts that we have up till now? Any other doubt? Kavi, it appears to be similar, but it is not same. In the case of blind valleys, the elevation is much higher. But in the case of polges, that elevation change is not very high. Estuaries sometimes can form backwater, yes. Canyons are much smaller, formed in the mature stage due to the elevation of the land. Gorges are always found in the youthful stage. Okay? Yes, Manisha, that is correct. Okay. I hope the doubts are also resolved. Perfect. Now, Uvalas are the largest. Ramaraju. Uvalas are largest. Dolines and polges are basically smaller. Okay? Right. Estuary is not a landform. Estuary is where the water flows backwards from the sea. The water tends to flow backwards. That is an estuary. Estuaries are not landform. Landform means what? A kind of the one created by deposits or erosion, right? That is not something that you will find in the case of estuary. Now, the landforms developed by glacial action. Now, glaciers are basically moving mass of ice down the slope. That is what glaciers are. Now, glaciers are of two types. You have the case of continental glaciers and alpine glaciers. Continental glaciers. Continental glaciers are the one which move over flattish areas, which have been present in regions where you have a kind of, let's suppose, the continents or flattish regions around ice ages. Okay. So presently, if you observe the glacial movement in certain areas of Greenland, that is where you have the continental glaciers, right? In certain areas of Antarctica, also, you will find the presence of continental glaciers. Whereas you have what is referred to as the alpine glacier. Alpine glaciers are the ones which come down from the mountain top. Mountain, originate from the mountain. Now, these end up creating a large amount of erosional and depositional landform as well. Erosional in the sense because the weight of these glaciers is so very high. The weight imposed by the ice in the glacier is so very high that it ends up scooping out the surface itself. So you have cirques, arêtes, horns, glacial lakes. All of them are created as a result of the erosional action of the glacier. So here, when you take a look at the case of the cirques, so here, this is a cirque, an amphitheater-like eroded, scooped-up portion of a mountain. That is a cirque. So at one point of time, a glacier would have moved from this particular region downslope. So this is what you refer to as a cirque, right? Now here you will observe that in certain regions, what happens is that as the slope, let's suppose, is like this. Okay. Now it can happen that as the glacier is moving, it can erode certain areas to such a great extent that eventually there will be a small depression which gets created. Those are what later on form the glacial lakes. For example, what you see here is an example of a glacial lake. Okay. What you observe here is the example of a glacial lake. So that is how the cirques basically are the erosional landform created by the glacier. Now, it can happen that in the case of this particular mountain itself, let's suppose there is a glacial action on both sides of the mountain. If there's a glacial action on both sides of the mountain, then you will have the formation of what are referred to as the case of arêtes. So when you have the glacial erosion on both sides of the mountain, you have a narrow ridge-like cape, a narrow ridge-like formation, narrow ridge-like land, okay, landform. As the glacier erodes from both sides, both ends. That is the case of an arête. Now, in case, let's suppose you have the erosion from all different sides as a consequence of the glacial action. In that particular case, you have a leftover peak, isolated peak, which is left over, and that is what is regarded as a horn. Okay, so that is what is regarded as a horn. Okay, so that is the case of arêtes, cirques, and horn. Right? Is it still buffering? Is there still an issue? Or is it fine now? Let me check the comment section once. Most of you are saying it's fine. The part before the break isn't available. That is the problem. Other than that, presently, whatever is being spoken, is that being heard? Is that being heard? Recorded video is not showing. Fair enough. It will be made available. It will be available. The present portion which is being said, which is being talked about, is that being heard? Buffering. One of you, Ranjit Kumar Sahu, is the only one who has written it is buffering of all the various comments. So, Supriya. Rest of you, you find it absolutely fine. The present stream is clear. No issues. It's buffering for many, fine for few. Most of you, in fact, Ashwin, most of them are saying it is fine. No issues. Sometimes it is buffering due to network issues. Fair enough. Horns formed by erosion from all sides of the mountain. Yes. The part before the break is not available. When the final video will be available, even that will be available. Don't worry about it. The recorded video soon and fast will be made available from the portion right now, is it something which is audible or not? That is the question. The question is not what are the troubles in life in general. Right now, what is the problem that you are facing? Bar before the break is not available. Right now, is it something which is audible? It's fine. Okay, perfect. So basically, we were talking about the case of the cirques, arêtes, and horns. So when we talk about the cirques are created when you have a kind of an erosion from one side of the mountain where everything is eroded like an amphitheater eroded structure gets created. That is a cirque. Now, sometimes what tends to happen is that basically you will observe that in a case of a mountain system, if there is erosion at both ends, it leaves behind a ridge like structure, and that is what is referred to as an arête. Now, if in the case of a mountain, the glacial action happens from all different sides, it leaves behind an isolated peak like structure, and that is what is referred to as a horn. Okay? Now, after this, we come to the portion that is fjords. So, when we talk about fjords, fjords are erosional structure created in the regions of higher latitude, particularly in the regions around Norway, etc., in the coastal area, right? So, these were the large glacial valleys which were created during the last ice age. So, here, the glacial erosion, particularly during ice age, erosion during ice age, it created a valley, created a glacial valley in the coastline, valley in coastal areas. Now, eventually, what would happen is that after the ice age, when the ice starts to melt, water level in the sea would increase, isn't it? The water level in the sea would increase. As the water level in the sea would increase, the sea would ingress. That is, in the interglacial period, you will observe ingression of the sea into the valley. Ingression of sea, water into the valley. Now, this ingression of seawater into that eroded region, that is what is referred to as, okay, that is what we regard as the case of, okay. I hope that is clear. So, this is the erosional structures which are created. Now, when we take a look at depositional structure, you have certain depositional structures which are created as the glacier moves. Wherever the speed slows down, that is when it will start depositing materials, isn't it? So, wherever the speed slows down, for example, here you see the case of the glacial movement. Wherever the speed slows down, there will be deposition which will happen, right? Now, many of the times the depositions happen immediately in the pathway of the glacier or immediately at the end of the glacier as well. Those are known as moraines. So, those are what are referred to as moraines. So, moraines are named according to where the deposition has happened. So basically, for example, if the deposition has happened on the sides, it is referred to as lateral moraine. Lateral, okay. If the deposition has happened in between, it is referred to as what? Medial moraine. That is what is medial moraine. Okay. If let's suppose here you observe some amount of deposits at the end of the glacier, they are known as terminal moraine or end moraine. Terminal moraine or end moraine. So, like that, depending upon where the deposition has happened, the moraines are named accordingly. Okay. Now, generally, the moraine deposits you will find in the pathway of the glacier as well. Many of the times, it also happens. Even in when the glacier eventually disappears, then after that, you have the evidence of these deposits. So, moraines oftentimes end up getting found out after the glacier has disappeared as well. Okay. Now, then you have what is referred to as a drumlin. Drumlins are created in the case of most of the continental glaciers. So that is why drumlins are something that you will find in those areas where you have a glacial history, where in the past there was a kind of a glacial movement. So those are the areas where you will find the presence of drumlins. So for example, when we talk about the case of Western Europe, right? In those areas during the Ice Age, there was a large scale glacial movement. Now, in those cases, oftentimes you will find that you have the deposits which are created like this in the direction of the glacial move. If you take a look at the cross section of it, the deposits end up occurring somewhat like this. These are what are known as drumlins. Now, taken a look from above, these drumlins they appear as if you have kept the eggs horizontally when viewed from above. So that is why they are also what are referred to as the basket of eggs topography. Basket of eggs topography. They can appear at the same time or in the same region in large numbers. In the same region, you will observe multiple of them getting created as a result of the deposition. Generally, in the continental areas where the glacier would have moved, they would have basically deposited these. And that is why they would have created these kind of drumlins. Okay. Then you also have similar longitudinal deposits created by continental glaciers, and those are referred to as eskers. So, when we talk about eskers are again longitudinal deposits that you observe. Longitudinal deposits. Now, again, here you can imagine that you would have had a movement of a continental glacier. The continental glacier would have deposited materials as it would have moved, right? And the glacier would have eroded and created a lot of these lakes as well, the kettle lakes and the glacial lakes, the tarns, etc. But in the meanwhile, it would have deposited some amount of fine particles. These are fertile features, fertile land areas. These are known as eskers. So longitudinal deposits created by longitudinal deposits created by continental glaciers. Okay, these are fertile deposits, very fertile. Okay, glacial tillites, they are the fine particles, Noor. So basically, they are very fine particles. Moraines, they will have the presence of till. The till in large deposits, when they form the sedimentary rocks, that is what we refer to as tillite. Okay. Now, then we come to the aeolian landforms, the landforms which are developed by winds. So winds end up carrying a lot of materials along with them. Now, again, the finer particles are carried closer to the ground. Finer particles are carried at a greater elevation. Larger particles are carried closer to the ground surface. So, because of the weight, because of the speed of the wind. So, landforms developed by the wind, which are the aeolian landforms, are typically to be found in arid and semi-arid areas. Why? Because that is where the wind speed is going to be so high and so substantial in order to be able to create landform. So here you will find them to be present in arid and semi-arid regions. semi-arid regions. Okay. Now here, as I told you, when the wind will blow in any particular place, as the wind will blow, it will basically carry the finer particles up top and the heavier particles closer to the surface. Right. If let's suppose you have a particular rock, the heavier particles will chip at the bottom of the rock, whereas the upper portion will be polished. This ends up creating a kind of a mushroom rock like structure. So that is where you have the case of mushroom rock. Mushroom rock. Okay. Where the bottom portion has been eroded by the wind action and the top portion is polished, is being rubbed by the finer particles. Now, the wind erosion also erodes materials differently. If in a region you have a combination of hard and soft rock structure, the erosion is different. So, the soft rock structures oftentimes are eroded, leaving behind the hard rock outcrop. Those hard rock outcrops which are left behind as the soft rock is removed, that is what is referred to as a yardang. So, when you hear about yardang, yardangs are basically created in those areas where you have a combination of hard and soft rock structures. Combination of hard and soft rock structure. Okay. So in this case, the softer rocks are eroded, and hard rocks are left behind. Harder rocks are left behind. Now, these harder rocks, which are left almost intact, appear as outcrops. They are known as yardang. Okay? So that is the case of yardang. Then you also have what is known as a deflation hollow, where in certain areas the wind simply erodes the region of fine particles. So in areas where, let's suppose, the ground surface is such that you have larger particles as well, right? Very large particles as well. And you have the presence of fine particles also, right? You have the presence of very fine particles as well. Now, as the wind comes in with full flow, the wind won't be able to carry the larger particles, but will nonetheless be able to erode the smaller particles. So that is where it creates a kind of a depression. It creates a kind of a depressed portion where there is a kind of a erosion of these finer particles. Okay. So that is what is referred to as a deflation hollow. When you have erosion of the softer particles or the smaller particles, these are known as deflation hollow. You just need to know the name associated with which agent of nature and whether it is erosional or depositional. That is all that is required for your prelims. If you know the name, if you are able to recall the images that I am indicating here, then there is no probability of you getting a negative marks or committing mistake come the time of the prelims paper. Okay. Now, after this, we also have the case of the sand dune. The dunes are basically deposited as and when the wind speed slows down. All the carried over materials are deposited by the wind to form these dunes. Now, depending upon the direction of the wind, the dunes they end up gaining different shape. Now, let's suppose the wind is coming from both the sides, it will end up accumulating materials in between. And then you have the case of a longitudinal dune. Have the case of a longitudinal dune. Let's suppose the wind is unidirectional, right? Let's suppose the wind is unidirectional. It will end up creating dune like structures parallel to each other. And that is what is referred to as the transformed dune. Distribution of the landform is not at all asked, never. Okay. So, see, Muzammil, regarding the Inselberg, Demoiselles, and Zeugen, again, not required for your GS. So, Inselberg's, the very idea of it is associated with the cycle of erosion. In the cycle of erosion, you have the leftover remnant portion, which are known as monadnocks as per the Division School of Geography. Inselberg, if you follow the Penck School of Geography, so those are after a particular region has been completely degraded, you basically have those leftover portions. Those are known as Inselberg. Zeugens or the tricanthers, they are when the erosion happens from all sides where the hard rock remains intact and the soft rock structure from all around is eroded, and you have almost a monument-like shape. That is the case of a Zeugen. Again, not relevant for your GS portion. Okay. Yes, Mitali, that is something which is associated with the case of peneplain and the aspect of the cycle of erosion. Yes, MK, correct. Now, depending, as I told you, depending upon the direction of the wind motion, the speed of the wind, the dunes, they get created in different shape. If the winds converge in a certain area from all different direction, let's suppose a region is at an elevation. Now the dunes will basically accumulate in the same place from all directions, forming a star-shaped dune. But these dunes, they are non-permanent in nature. That is, they can shift. Non-permanent in nature. Okay, that is, can shift from one place to another. So as they will shift from one place to another, that is why also referred to as shifting. Right? Now, here, then we come to, in the case of the shifting dunes, by the way, sometimes if you observe this particular image, it can happen that a dune is created in such a way that the central portion of the dune, after all, it is made out of sand, the central portion of the dune simply slips over. That creates a kind of a crescent lake like shape of the dune. A crescent shaped dune is created, and that crescent shaped dune is what is referred to as a barchan. So that is how the barchans get created. Barchans are basically a crescent shaped dune where there is a slip in the central portion with the two protruding ends in the direction of the wind, right? So crescent shaped dune with slip the central portion, creating a slip face, creates a slip face and two horns protruding horns. So basically, when you talk about a barchan will be a kind of a crescent shape. So these are your horns. Okay. Generally found in the horns are shaped in the direction of the wind motion. Okay. Now, after this, the coastal landforms. Coastal landforms are created again both by erosional action or the physical erosion by the sea waves as well as the activity of chemical erosion. Both of them end up creating these coastal landforms. So, for example, you have the formation of cliffs. Cliffs are created when in the coastline you have a kind of a shape like this, and slowly and steadily this portion gets eroded. As this portion gets eroded, you have the formation of these. In India, sea cliffs are to be found in the region of Kerala, where you have sedimentary rocks in the region of Varkala, which creates these sea. Otherwise, in Scottish Highlands, you will find the presence of these. Similarly, terrace a kind of a graded structure is created. Many of the times you have the case where caves are created due to both chemical as well as physical erosion in the coastal rocks, particularly in the Mediterranean coastline of Europe. You will find that. And similarly, you have the stacks and stumps. We'll take a look at the image also. Now, many of the time across the coastal land, if you take a look at the cross section, let's suppose this is the land area, or if I can reduce the gradient, and let's suppose this is the sea. Now, the sea action, many of the times, what it will do, it will end up depositing some materials. You would have seen, if you have been to a coastal area, it will not always indicate a similar gradient. Now, this indicates a series of deposits. Now, those series of deposits, sometimes they are created, if you take a look at the top view, the deposits are created parallel to the coastline. They don't touch the coastline. They are created parallel to the coastline. And those deposits, they are known as bars. Those deposits are known as bars. Okay. Now, across the coastal area, what also tends to happen is that you have the influence of the winds which are parallel to the coastline. And that is when oftentimes the deposits which are happening across the coastline, they get elongated in the direction of the coast itself. And those are known as spits. So when we talk about spits, spits are basically coastal deposition, coastal deposition attached to the coastline, attached to the coast, okay, and then parallel to the coast under the influence of the longshore winds, the winds which are parallel, right, parallel to the coast, under the influence of the longshore wind of wind. Okay, so that is what we have as a case of coastal deposit, right? Now, here these are your spits. Sometimes what also tends to happen is that there are certain islands very close to the coastline. Now, the deposits, they end up connecting the island to the mainland. Now, those deposits which will connect the island to the mainland, they are known as tombolo. Tombolo. That is what is referred to as a tombolo, right? And the island which is basically joined to the mainland now, they are known as tide island. They are tied to the mainland. That is what we regard as the case of tide island. Okay? Now, that is the case of spits and tombolos. Now, here you can see a combination of these different features. So basically, you will observe that as you have the erosion by the sea, so here you can have the presence of a cliff. This is what you regard as a case of a sea cliff. Sea cliff. Then, sometimes due to chemical erosion, basically ends up creating a large cave-like feature. Now, if the water penetrates and passes through the cave, comes out the other side, then all that you have left behind is a kind of a roof above, which is known as an arch. So you have the case of an arch, right? Now, this roof obviously is unstable. So the central portion will immediately tend to sink. As the central portion collapses, what you have left over is the case of a stack, okay, a kind of a leftover pillar, that is a stack. Now, as that gets eroded further, its size is further reduced, and that is what you have as a case of a stump. So, like that, you have these as the erosional and the deposition. Okay. Now, Animesh, is the Western continental shelf wider or the Eastern? Western continental shelf is wider. Always. Western continental shelf is wider. Eastern continental shelf is narrower. Why? Because western coast in India is a submergent coast, eastern coast is an emergent. Terraces are created due to graded kind of erosion and the kind of combination of mass wasting and mass movement. Okay. Now, after this, the case of the question, right? So, for prelims, just the type, whether it is erosional, depositional, or this kind of a question, right? Cirques, arêtes, horns, and drumlins represent which kind of topography? Okay. Cirques, arêtes, horns, and drumlins. And I hope nobody gets it incorrect. So here, the correct answer is the glacial landform. All of these, they represent the presence of or the existence of a glacial landform. That brings us to the end of geomorphology. And now we initiate the portion of climatology. But before initiating the portion of climatology, an announcement for all those who are appearing in the examination this year. So, in order to ensure that you are well attuned to be concentrative enough during the timing of the examination so that you don't commit silly mistakes due to lack of concentration, we have the prelims mock drill. Now, this prelims mock drill is to ensure that you are able to set your biological clock with respect to this particular time period. Also, with regard to practice, that you are able to practice the question with the case of CSAT, with the case of GS as well. So that is where 13th to 15th of May, you have the GS tests at 9:30 a.m. 16th and 17th, you have the CSAT test at 2:30 p.m. at the exact time when you need to be alert. And 18th of May, you have the full test, GS plus CSAT. So do take these full length tests. You will get an all India ranking. Don't get worried by the rank, but to understand where you actually stand in the entire group, right? Many people will take this test. So this is a kind of a real term assessment for you, right? So do take the test and do enroll for these tests. Now coming to the portion of climatology, very, very relevant for your prelims, very important portion for the aspect of prelims examination and MCQ. Now you see, we start with the portion of atmosphere. So when we talk about the case of atmosphere, atmosphere is basically something that we see in the presence of the gases that we have, from oxygen to carbon dioxide to nitrogen, argon, all of them are present. But all of these were not always present since the time of formation of planet Earth. At the time around 4.5 billion years ago, when the planet Earth was created, at that point of time, the atmosphere was constituted only of hydrogen and helium. So that is what was referred to as the primordial atmosphere, or what was regarded as the primitive atmosphere. Chemical erosion is basically as a result of chemical action, chemical reaction. You have, for example, calcium getting dissolved in water. So in a calcium based rock, water will dissolve calcium. So that is the chemical based erosion. Right. Now, primordial atmosphere. So primordial atmosphere basically is the atmosphere which was present in at the case of the protoplanet, when the planet was just getting created. So at that point of time, the atmosphere was having the presence of only hydrogen and helium. Okay. Now, after that, the planet entered into a phase of degasification. The phase of degasification is also regarded in the planet's evolutionary cycle, when you had hundreds and thousands of volcanoes erupting across the surface almost on a daily basis. This happened somewhere around 4 billion years ago, right? So at that point of time, you had introduction of newer gases in the atmosphere. Which were the gases? You had ammonia, NH3, CO2, CO, CH4, SO2, vapor, water vapor. All of these were the newer gases which were introduced into the atmosphere. So that is how the newer gases came into existence. And then eventually, with the evolution of plants and the quick growth of plants due to abundance of carbon dioxide, that is when the modification of atmosphere happened. This happened with the evolution of plants. with evolution of plants. Now, the plants carried out large scale photosynthesis, consuming carbon dioxide and enriching the planet's atmosphere with oxygen. So, during this phase, oxygen concentration increased. Now, UPSC had asked a question in 2018, that is, oxygen has been present in the atmosphere ever since the formation of planet Earth. That was a question which was asked by UPSC, right? So, here, these kind of questions you have to expect. That most of us, when we think about oxygen, we think that planet Earth was created with oxygen. But is it the case that oxygen was present ever since the formation of planet Earth? No, that is not the case. Okay. So oxygen came much later. Okay. So these kind of questions is something you have to be aware of. Right. Now, then the composition of atmosphere. You have the various gases, water vapor, as well as the dust particles. These are the major components of the atmosphere. What are the role of the gases? What is it that you can think about as a role of the gases? So gases basically providers of life support, and these gases, they also help in greenhouse effect. Now, greenhouse effect primarily is good or bad? Is greenhouse effect good or bad for the planet Earth? Primarily, in itself, greenhouse effect is good. Why? Because it helps in maintenance of the temperature. Even during night time, it does not allow the temperature to plummet. Okay. Otherwise, in the case of Mars, in the case of Moon, where you don't have the gases in the atmosphere, nighttime temperature becomes very low. But it is because of the greenhouse effect that the nighttime temperature is trapped. So that is where the greenhouse effect is productive. It is helpful. Okay. But with the increased concentration of gases like CO2, methane, water vapor, nitrous oxide, etc., that is when the heating is very high. Trapping of heat is very high. Only then the greenhouse effect becomes dangerous. It leads to global warming. Okay. But excess of anything is bad. So, if you don't have enough pollutants, greenhouse gas is very good. But excessive greenhouse effect leads to warming. Okay. Now, after this, water vapor. Now, water vapor is also important greenhouse gas, very vital greenhouse gas, right? And when we talk about water vapor, it influences the climate across the globe in terms of humidity, in terms of rainfall, cloud formation, everything. It leads to the influence on climate, right? Dust particles. Dust particles have also got a role to play in the atmosphere. What is the role? So, when we talk about dust particles, basically, it will form the nuclei for the formation of clouds. So hygroscopic nuclei for cloud formation, and then they also trap heat, scatter the light rays. So by scattering effect, they will in a way trap heat in themselves, and they will emanate that heat during night time in the form of diffused light, which allows you to see even during night time, right? So scatter and emanate heat, or simply emit light during night time, right? In the form of diffused light. So dust particles also have got a role to play. Okay. Now, these are the gases in terms of the proportion. You don't have to remember the percentage, but you do need to know about the order of it. nitrogen, oxygen, argon, carbon dioxide. This basically you have to remember: nitrogen, oxygen, argon, carbon dioxide. Okay? Majority of the students, they think carbon dioxide is the third most dominant gas, which is not the case. So that is where you have to ensure nitrogen, oxygen, argon, carbon dioxide. Right? Now, then we come to the concept of lapse rate. So when we talk about lapse rate, basically what is it? It is the rate at which the temperature changes with increase in height. That is lapse rate. The change of temperature as one moves up in altitude. That is lapse rate. So when we talk about lapse rate basically has got three different types. You have the case of positive lapse rate, positive lapse rate, negative lapse rate, and zero lapse rate. Okay. So you have these three different types of lapse rate, right? The categorization. Now, positive lapse rate means what? Temperature reduces with height, reduces with height. Negative lapse rate means what? Temperature increases, increase in temperature. Zero lapse rate means what? Consistent temperature. Okay. Now, in the case of troposphere, that is the layer closest to the surface, we will experience what? We will experience positive lapse. Why? Because of two reasons. Which are those two reasons? The first reason being that the density of the particles reduces as you move from the surface upward. That means what? Wherever greater particles are present, greater trapping of heat. So as you move upwards, the trapping of heat reduces. Right? So particle density reduces with height. Density reduces with height. With height. Second reason. What is the second reason? Very good. The source of heat basically is from the surface. Surface is the source of heat. So as you move higher up away from the surface, the amount of heat experienced will reduce, right? Source of heat for the atmosphere is the surface. The- Okay. So that is basically the reason why in troposphere, as you move higher up, the temperature tends to reduce. It tends to reduce at a rate of around 6.5 degrees Celsius per kilometer, or 1 degree per 165 meters in height. So this is what is also referred to as the normal lapse rate or environmental lapse rate. Okay. That is the rate of reduction is 6.5 degrees Celsius per kilometer. However, the rate of change of temperature varies when you consider humid condition, moist condition, or when you consider dry condition. In the case when you have the conditions which are very dry, what is also known as the dry adiabatic lapse rate, in that case, the lapse rate can be 10 degrees Celsius per kilometer. But when the moisture presence is very high, it is humid. In that case, the lapse rate is less, 5 degrees Celsius per kilometer. So that is where it can always end up varying. Please keep that in mind that in the case of moist condition, the lapse rate is less. In the case of dry condition, lapse rate is always very. Okay. So lapse rate, I hope we know positive, zero, negative, right? In the case of troposphere, positive lapse rate. The reasons we have seen. Normal lapse rate is 6.5 degrees Celsius per kilometer. As you move higher up, the lapse rate keeps on changing. The moist conditions, lapse rate is less. Why? Because water vapor is able to trap heat. That is why the lapse rate is less in moist conditions, right? Because it is able to retain heat. So temperature will not fall to such a great extent. So moist lapse rate, 5 degrees Celsius per kilometer. Dry, 10 degrees Celsius per kilometer. Okay. Now, the adiabatic process. Adiabatic process, when there is a change in temperature without any change in the case of volume. That is, without any external source of heat. Change in temperature purely due to the change in volume. That is the adiabatic heating or adiabatic cooling. Okay. So there is no external source of heat, right? So if an air parcel, which is like this, if it tends to contract or is compressed due to external forces, that means what? The particles which are present here, they will undergo greater number of collisions. The particles will undergo higher and greater number of collisions. And as a consequence, the temperature will increase. So this is what is also referred to as adiabatic compression or adiabatic heating. Adiabatic increases the temperature. This is at play when you talk about local winds such as Chinook and Fohn. In those areas, you will observe a greater role to be played by adiabatic compression. Similarly, when we talk about subsidence inversion, where the sinking of the air mass creates a warmer air above, that also is the case of adiabatic compression. Okay? Yes, Manisha, that is correct. So when you have the mountain valleys, in this case, the region of the mountain valleys, you have the air which sinks from above, it gets compressed. Right. Okay. Now, if this, let's suppose, air parcel tends to expand, if it tends to expand, then what? The number of collisions will reduce. That means the temperature will not be very high, temperature will reduce. So that is where it is adiabatic expansion. Adiabatic expansion or adiabatic cooling. So expansion leads to cooling, contraction leads to heating. Simple. Very simple, no complications involved. Expansion of air will lead to cooling, compression of air will always lead to warming or okay. Now the structure of the atmosphere, the layers of atmosphere which are present. So when you take a look at the layers from the ground surface, in the near the ground surface, you have the troposphere. Above it, you have the stratosphere. Above it, you have the mesosphere. Above it, thermosphere and exosphere. Now, all of them, they have different property in terms of temperature. But as you move closer to the ground surface, the pressure tends to density of the gases, the particles, everything is maximum in the region of troposphere. As you move higher up, the number of particles keep on reducing. Okay. So here, up till the region of mesosphere, up till this area, mesosphere, you will still experience homogeneous distribution of gases, the gases that we studied, nitrogen, oxygen, argon, carbon. So that kind of distribution is still present. So this is what is referred to as the homogeneous layer of the atmosphere or the homosphere. Beyond the region of mesosphere, you will find that nitrogen is concentrated in some area, oxygen is present somewhere else. So, beyond that, there's a heterogeneous mixture of the gases which are present or which are to be found in the exosphere and thermosphere. And that is why this is also what is referred to as the heterosphere. Heterosphere. Okay. It is in this region of thermosphere basically where you have the unfiltered rays of the sun. including X-rays, ultraviolet rays, etc. All of them bombard this region of the portion immediately above mesopause. Now, as they bombard this region of thermosphere, they end up creating the presence of charged particles. And that is where, in the region of thermosphere, you have got the formation of what is referred to as ionosphere. Ionosphere. Now, this ionosphere helps in re-radiating back the radio wave and establish radio communication there. So that is why radio communication, which is released from the Earth's surface, is established because of the fact that the ions present in ionosphere, they are able to reflect it back. Ionosphere also has got various different other layers as well, or various different other classification, D layer, E layer, EF layer, etc. But not required for your exam in this particular case. Just understand the presence of ions is helpful in re-radiating back the rays of the radio waves in general. Okay. Now, in the case of troposphere, you will experience a kind of positive lapse rate. That is, temperature reduces as you move higher up. So that is why in troposphere you observe positive lapse rate. But in stratosphere, you have the concentration of the ozone layer. Now, because of the concentration of the ozone layer or the presence of ozonosphere in stratosphere, that is where a lot of ultraviolet rays are trapped and reflected back. That is why, in the case of stratosphere, the temperature starts increasing with height. So, in the case of stratosphere, you have the presence of negative lapse rate. Temperature increases with height. Okay. Now, here, in between the troposphere and stratosphere, you have the differentiating region, that is the tropopause. So, in the tropopause, you have colder conditions from below, warmer conditions from stratosphere. So, neither does the temperature increase or reduce. So, when you talk about the region of, let's suppose, the various different layers, let me finalize here. So, troposphere, you have troposphere. Then above it, you have tropopause. Then above it, you have stratosphere, which has got the ozone layer. Then above it, you have the stratopause. Then above it, you have mesosphere. Then above it, you have the mesopause. Then you have the thermosphere, right? Now, in the case of troposphere, positive lapse rate, that is, temperature reduces with height. In the case of tropopause, zero lapse rate, temperature is consistent, right? Stratosphere, negative lapse rate, temperature increases with height because of the presence of ozone layer or ozonosphere. Then in the case of stratopause, zero lapse rate again, temperature does not indicate much of a change. Mesosphere, again, you are moving away from the heated portion of the stratosphere. So again, a positive lapse rate. Temperature reduces up to the range of minus 100 degrees Celsius, minus 80 degrees Celsius. Mesopause, zero lapse rate. Thermosphere, negative lapse. That is, temperature increases with height. There is no end point of thermosphere or exosphere. Like we have the end point in troposphere, that troposphere is thickest at the region of the equator and basically more compressed at the region of the poles owing to the air movement. Then stratosphere extends up till 50 kilometers. So you don't have that upper ceiling in the case of thermosphere. Okay, I hope this is understood. Now, this tropopause, mesopause, and stratopause, all these indicate the end of a particular layer, right? And a zone of transition before you begin the next layer. Just like what we saw in the case of discontinuities earlier today. Something very similar is there in the case of these pauses as well. So here, because generally above each of these, you will find different kind of lapse rate, heating or cooling. That is why almost all of these will have consistent temperature in that zone of transition. Exosphere, again, negative lapse rate, but exosphere, see, if you are standing or if you are measuring just on the exosphere on the outside, you will not be able to measure that temperature because gases are almost absent. You have certain pockets, certain chunks where air is present, having a distance of, let's suppose in this pocket there is air particles. Move away 100 kilometers away, another bunch of air particles. So in between those 100 kilometers, you won't be able to measure the temperature. But in those particular chunks, the temperature will be high because they will be impacted by the solar rays. So in the case of exosphere, again, negative lapse rate only. Okay. I hope that is clear. Right. Magnetosphere extends sometimes beyond that also. Magnetosphere extends beyond the thermosphere as well, beyond the ionosphere. Okay. Now, then we come to insolation and the factors which end up influencing insolation. Insolation is what? The amount of solar rays. Yes, stratosphere experiences negative lapse rate due to ozonosphere, ozone layer. Now, when we talk about insolation, solar insolation, what is solar insolation? The amount of solar energy received in a small unit area, right? So that is what is the solar insolation. Now, this solar insolation is variable, it is not fixed, right? So, which are the factors on which the solar insolation is dependent? So, solar insolation basically is dependent on the angle of inclination of planet Earth. At what angle is the planet Earth inclined? Right. And also the fact that planet Earth is curved in shape. So basically, in the higher latitudes, you have reduced amount of solar insolation. Higher insolation in lower latitudes, insolation in lower latitudes. Till here, is it being understood? And is the session being followed from geomorphology up till here? Anyone finding any portion very difficult, do let me know. In lower latitudes and lower insolation in high latitude. Equatorial regions receive more, it is not insulation. Equatorial regions receive more insolation or subtropical region. What do you think? Always subtropical region will and the tropical region will receive higher amount of solar insolation. Why? The reason being that in the region of equator, you will frequently have the cloud formations. So if you consider the long term average, tropics will generally have a kind of a higher okay, in that particular, right? But if you consider across, let's suppose, uh, over a very, very large period, then depending upon which tropical region are you talking about. Okay, thick clouds in equator, cumulonimbus clouds in equator, hence they will block out the solar. Okay. Why different lapse rate? Lalita, we have discussed about the positive lapse rate in troposphere. I hope that is something which is understood, that why there is positive lapse rate in the region of equator, in the region of troposphere. Now, then we have discussed that why you have negative lapse rate in stratosphere, because of the presence of ozone layer. They will trap the ultraviolet rays, right? Then in mesosphere, as you move away from stratosphere, you're moving away from the source of heat. So that again, the temperature will reduce with height. And hence, we have discussed that we reach up to a temperature of minus 100 degrees Celsius as you move to the top of mesosphere. So again, you have a kind of a positive lapse rate. So it is because of differential amount of factors which lead to heating or cooling of the layer. That is what leads to a different lapse rate in all of these. Okay, Lalita, that is the question that I am asking. that I was answering. If you have not listened to it, rewind it right now again and listen to it again. Okay? Right. Now, the revolution of planet Earth. When we talk about revolution of planet Earth, so this also influences basically the amount of insolation. How? So when the planet tends to move in the orbit, you have different positions of planet Earth. For example, on 4th of July, planet Earth is far away from the sun. And that is a position which is referred to as aphelion, where the distance from the sun is roughly around how much? 150 million kilometer. Million kilometer. Right. Now, then on 4th of January, around that time, the planet is closest to the sun. And that is the condition of perihelion. So, in the condition of perihelion, the distance is 147 million kilometers. So, what it will do is it will influence the amount of heating and cooling, right? So, basic amount of insolation, not so much heating and cooling, but the amount of insolation because the distance changes by almost 5 million kilometers. So, that again influences the insolation factor. Then you have the configuration, the direction in which the land is facing. So, for example, when you take a look at southern slope of the Himalayas, they receive direct rays of the sun as compared to the northern slope, isn't it? Because the sun is to the south of the Himalayas always. So that is another factor. Altitude. Higher the altitude, greater is the insolation. Why? Because the solar rays have to pass through lesser amount of atmosphere. So greater the altitude, higher the altitude, greater solar insolation. Okay, I hope that is clear. Configuration of the land basically talks about the direction in which the land is facing. If the land is facing towards the sun, it will receive greater solar insolation. If the land is not facing the sun, lesser amount of solar insolation. Now, then we come to the factor of albedo. Albedo basically is the case of the reflective coefficient of the surface. It is a surface property. It is a surface phenomenon. So when we talk about albedo, so it tends to vary from 0 to 1. Okay, it indicates the reflective coefficient of the surface. So it is a surface phenomenon. So in a particular area, albedo gives you an idea about what amount or what proportion of solar rays are reflected, what amount of solar rays are absorbed by the surface. Right. So if you have an albedo of 0, means what? Complete absorption, zero reflection. Absorption, zero reflection. Right. A case of a perfect black body. And if you have an albedo of 1, complete reflection, zero absorption. Okay. So that is basically the case of albedo. In the case of ice covered surfaces, the albedo is generally in the range of 0.8 to 0.85, which indicates that 80 to 85% of the solar rays are reflected from the surface. But when you talk about marshy land, floodplains, etc., albedo is around 0.2. Only 20% is reflected, rest is absorbed. Now, when you talk about planet Earth, what is the albedo of planet Earth? Albedo of planet Earth is around 0 point. Okay, that is the case of albedo. right? Now, this albedo also influences the amount of melting that you observe in the polar areas, or what is also referred to as the case of Arctic amplification, where the region of the Arctic is basically melting or heating almost at twice the rate as compared to rest of the planet, right? So what tends to happen is that due to global warming, you will observe that due to the case of the global warming, after this we will take a break, don't worry. After this, we will take a break. Again, I will give you a break of around 30 minutes, 25, 30 minutes, and then we will continue. Global warming, melting of ice in the region of Arctic, melting of ice. So that means thinner ice is exposed and water is exposed, which basically means what? Greater solar absorption, lower albedo, greater solar absorption. When you have greater solar absorption, that means what? Increase in temperature. When you have increase in temperature, it will lead to what? Further melting of ice. So this is where there is a feedback cycle, due to which there is a kind of a continued melting of the ice in the region of Arctic. Okay? Short wavelength is absorbed or long wavelength from sunlight is absorbed. Sunlight is associated with short waves, Rookie. Okay. Okay, is there some excitement regarding the admit card? Admit card is out. Did we not have the kind of belief that UPSC will give us admit card, or is it the case that suddenly there has been a surprise that admit card is there? Is that the case? Were we not having the belief or the kind of hope that UPSC will give you admit card? Is that the case? Why are we surprised then? Okay, right. See, generally the case is how UPSC works. For those of you who are very excited about admit card, how UPSC tends to work is you apply when the notification is released, you apply for it, and your application is accepted. Then they will release admit card. Admit card does not mean you have succeeded in the prelims or you have succeeded in the mains or you have qualified the exam. Admit card, you will simply get your name and the center. It is the prelims that you have to prepare for. Okay, everybody gets admit card. There is no achievement in getting admit card. So all those who are getting very happy with the admit card, tone down the happiness ever so slightly. After 25th, if UPSC allows you to be happy and cheerful, that is the day to celebrate, not the day that UPSC has released admit cards. What a good day it is. Okay, so tone down the happiness slightly. I know it is a big deal. Uh, Admit card, those who have not applied for UPSC, they also did not get the admit card. You got the admit card. I understand that. But then many of them would have got it. Okay, right. Now, after this, we will move ahead with the case of isotherms and the heating of land and water. So before that, we take a break and we will come back after the break. So till that point of time, let the news of admit card sink in further. Okay, let that excitement die out. So we will give 20 minutes break this time, or should I go for 25 minutes? 25 minutes. It is 7:15 as of now, so we will meet at 7:40. Okay, heat budget not very important. Zero albedo is not possible unless and until you have a complete black body. Okay, right. So see you in 25 minutes and we will resume. Okay, welcome back, everyone. Now, regarding the kind of some amount of anticipation and some amount of curiosity which is there with the students and the aspirants who have joined in between, they are unable to scroll back to the 5 hours and the portion of geomorphology. Don't worry about it. We had restarted the stream in between. That is why you are unable to scroll back to the initiation portion of that. Once the entire stream is done, once the entire session is done, you will be able to take a look at the entire video. Okay. So don't worry about it. Just concentrate on the portions which are being covered now. Okay. So I hope that assuages the general amount of curiosity and some amount of restlessness which was growing. It is absolutely fine. That tends to happen when you stop the stream and restart the stream in between. Okay. Now, after this, we come to the portion of heating and the heating in terms of land and water. So basically, when we talk about heating of land and water, so you see, land and water, they get heated at a differential rate. Because when we talk about the region of the land and you compare it, let's suppose, to a water body, right? Now, in that particular case, when there is heat which is being received, now in the case of land, all that heat is restricted only to the surface, few inches on the surface itself. It is because of that that the temperature tends to increase very quickly. Whereas in the case of the water body, that heat is dissipated, is distributed rather, right? Because water is partially transparent. So that is why the heat is distributed. Now, it will take much greater amount of time for the water body to indicate a rise by 1 degree Celsius as compared to the land. During the night time, on the other hand, when you consider the night time, during the night time, it is the time when the heat is lost from the surface. So during the night time, as all the heat on the land was restricted only to the surface, few centimeters of the surface. So during the night time, land will lose heat much quicker because land has got all the heat restricted to the surface. Whereas in the case of water body, as heat had been distributed to the depth of the water body as well, it will take a greater amount of time for the water body to lose heat. Okay? So land heats up quickly, cools down quickly as well. Whereas in the case of water body, the rate of heating is also slow, rate of cooling is also very slow. Now, what is it that you can draw out of it as a conclusion? So basically, we can say that land gains and loses heat at a faster rate as compared to the oceans or the water body. Okay. Now, this indicates a variation on a daily basis as well. That during the day, you will always have the case where the land is warmer. Whereas during the night, the land will be colder as it would have lost heat very, very quickly. Right? Now, during the summer season, there is a prolonged duration for which the heat is received or the heat is basically gained. So during summer, in those entire months where you have surplus amount of heat, land becomes warmer as it gains heat much quicker. Whereas in the case of the winters, winters basically mean heat deficit. So the heat is lost from the surface in the form of long wave terrestrial radiation. So that is why during winters, you will always find the case where the land is cold. Okay, I'll repeat, land is hotter during the day, hotter during summer. Land is colder during the night, colder during the winter. Okay, now in this particular case, that is indicated when you talk about the isotherms and the movement of the isotherms. How? We'll take a look at it with the help of the thermal image as well as the isothermal maps. So basically, in the case of this thermal image during the month of July, you will observe that it is a summer months in the northern hemisphere. July is summer in the northern hemisphere, isn't it? Northern hemisphere, summer, and southern hemisphere, winter. Now, if you observe this particular thermal image, you will observe what we have discussed just now. Observe that how the land areas experience a higher temperature. During the summer, water is comparatively cooler. Land areas experience a higher temperature, water is comparatively cooler. Whereas in the case of the southern hemisphere, you will observe a very uniform distribution of temperature, almost to the parallel of the latitude. The reason being very simple, that when we talk about the southern hemisphere, it is also known as the water hemisphere, dominated by the water body. So that is why the transition of temperature is very uniform. Okay, the transition is slow and uniform. That is why the temperature changes almost parallel to the latitude. Now, when we talk about the month of January, in the month of January, you have the case of winters in the northern hemisphere. To observe how the land is very, very cold and the water is comparatively much warm. Water is very cold. So, at the same latitude, water is much warmer as compared to the land in the same latitude. That is something which is indicated by the isothermal maps and the isothermal image. So, if you take a look at the isotherm in the month of January, take any particular latitude. Okay, let's suppose we take this latitude. Now, if you observe the temperature here over land area at this place A, the temperature is how much? Temperature is almost minus 25 degrees Celsius, isn't it? Whereas if you compare the temperature here, P over the water body, is almost 10 degrees Celsius. So here, what do you observe? Temperature at A is minus 25. Temperature at B is 0. Now, over the water body, if you have to experience minus 25 degrees Celsius, do you have to move towards equator or towards the region of the poles? What do you think? Over the water body, you will have to move towards the region of the poles, isn't it? That is when you will experience colder temperatures. Towards equator, you will experience warmer temperatures. So that is why you come across a conclusion that during winters, as one moves from continents to the oceans, isotherms bend poleward. From continents to oceans, isotherm bend polewards. In order to experience the same lower temperature, you have to go towards the pole. Now, what about the summer condition? What is the behavior of isotherms during the summer? So, during summers, you will experience something which is quite the opposite of it. So, when we talk about the summer season, you will basically observe with the help of this thermal image. Let's suppose if I again consider this region as A and this region as B at the same latitude, let's suppose. Now, you will always come across a case that temperature at A will be greater than temperature at B because during summer, land gains temperature faster. So, temperature at A will be higher as compared to the temperature at B, isn't it? Now, if you have to experience the same temperature in the ocean as you observe over the land areas, where do you have to move? At higher temperature, if you have to experience, you have to move towards the region of equator. Only then will you experience higher temperature, isn't it? So that is where during summers, from continents to oceans, isotherms bend towards equator. Towards- Okay, this is basically the change, the shift that you will observe in the isotherm in between the summer and the winter month. I hope that is clear. Now, when we talk about the properties of isotherms in southern hemisphere, isotherms in southern hemisphere, what can we conclude regarding them? They are parallel to the latitudes in most of the cases because of the predominance of water body. That is why they are almost parallel to the latitude, because with the change in latitude, there is decrease in the solar insolation. As you move towards the poles, temperature decreases very gradually in a homogeneous manner. So in the southern hemisphere, you will observe that generally the isotherms are parallel to the latitude. Okay, they are generally parallel to the latitude. That is something that you will find as a kind of a direct implication. This is something that UPSC has been concentrating upon for the past couple of years. So, not to say that UPSC will repeat the question this year as well, but I hope if a question comes from this particular portion, we are in a position to answer that emphatically well. Okay. Now, this is the previous year question. I want you to take a look at that. So, which of the following is or are the correct inference or inferences from the isothermal maps in the month of January? The isotherms deviate to the north over the ocean and towards the south over the continent. The presence of cold ocean currents, Gulf Stream, and North Atlantic drift make the North Atlantic Ocean colder and the isotherms bend towards the north. So, select the correct answer in this. What do you think? Now, in this particular case, isotherms deviate to the north over the ocean and towards the south over the continent. This is correct. We have seen that during the month of January, over the oceans, they will deviate northwards, right? Now, presence of cold ocean currents, Gulf Stream and North Atlantic drift, these are basically warm ocean currents. So, North Atlantic Ocean is not colder, it is in fact warmer. So, this will go as incorrect, right? So, the correct answer in this case is going to be A. That is one only, right? Now we come to the portion of temperature inversion. What is temperature inversion? Prerak, regarding isotherm during monsoons in India, do they show a sudden equator shift over land due to immediate cooling effect following or during the monsoon? No, it is not the case. Isotherms, they will not dip towards the equator because please understand, during the summer months, Prerak, when the monsoon season arrives, where do you find a higher temperature? To the south of India over Indian Ocean in equator or north region of India? Always higher temperature will be observed in the northern part of India. So isotherms will never bend towards the region of equator in that particular case. Okay. Now, what is temperature inversion? So we have seen that under normal situations, under normal circumstances, normal conditions, in the region of troposphere, that is the air which is closest to the ground surface, right? So in that particular case, you have the condition of a positive lapse rate. Positive lapse rate. That means what? That as you move higher up, the temperature tends to reduces. Okay, the temperature tends to reduce, right? Now, due to certain climatological conditions, you have the fact that you basically have, so in normal conditions, you have colder air above, cold air above. warm air closer to the surface. So warm air will have a tendency to rise up, cold air will have a tendency to sink, isn't it? Now, under certain climatological conditions, what you experience is the case where the warm air lies above, and cold air lies below. So this is a condition of a negative lapse rate. Now, in this particular case, you don't have mixing of air anymore. Why? Because the warm air already is above. Warm air has got a tendency to rise up. It is already above. Cold air, it is heavier. It is already below. It has got a tendency to sink down, but it is already near the ground surface. So this is the condition which is referred to as the condition of temperature inversion. Temperature. So that is what you have as the case of normal conditions and the condition of temperature inversion. During the condition of temperature inversion, you basically have lack of mixing of air. Lack of mixing of air. So problems of pollution, etc., get exaggerated because there is no mixing of air which tends to happen. This is what is also referred to as the condition of a stable air mass. Stable air mass. Okay. So that is the condition of a temperature inversion. Right? Now, when we talk about temperature inversion, it is classified based upon how and where the temperature inversion has happened. Okay. How and where the temperature inversion has happened. So basically, it is divided into when the surface cools down immediately, there will be cold air immediately closer to the surface. That is your surface inversion. Then you have what is known as upper air inversion. Now, upper air inversion is what? Inversion happening at the top of troposphere, at the upper extent of troposphere. So, in the case of upper air inversion, you have two cases: upper air thermal inversion, and upper air mechanical inversion. Now, what are these? So, when you talk about thermal inversion, it is basically at the boundary of troposphere and stratosphere. So, basically, the top of troposphere is cold and the bottom of stratosphere starts to get warmer. So, that is the case of a thermal inversion, thermal upper air inversion. That is from troposphere to stratosphere. There is a negative lapse rate, troposphere to stratosphere. Okay. That is the case of the upper air thermal inversion. This is the reason why the air circulation never exceeds beyond the region of troposphere. The air circulation is limited to the region of troposphere because beyond troposphere, you again have a negative lapse rate, that is stable air condition. So vertical air rise does not happen. Mechanical inversion in the upper air is created due to the sinking air column. We will talk about it. Then you have what is known as the case of frontal inversion. Due to the formation of fronts, the warm air tends to climb up over the region of the cold air. So that is what you have as the frontal inversion. And then you also have what is referred to as valley inversion. Valley. Okay. So these are the basic classifications of temperature inversion. In India, you will observe the surface inversion, thermal inversion, upper air thermal inversion is experienced everywhere. And in India, you will also experience valley inversion, right? Frontal inversion and the upper air mechanical inversion generally experienced in the mid latitudes to higher latitude. Okay. Now, one by one, if we take a look at it, what is surface inversion? So surface inversion is basically when the surface cools down at a very fast rate. And when will the surface cool down at a very fast rate? When you have long winter nights, clear sky, because clouds will trap the heat. So you need to have clear sky. Okay. In that case, the heat lost will be substantial. So during the night, what happens is that the surface cools down rapidly. As the surface cools down rapidly, the air in contact with the surface that will also lose temperature very quickly. Cools down very quickly. Okay. And then as you move higher up, the air temperature above is not so low, because the air parcel which is higher up is not going to lose heat at such a great pace. So that is why here you will still have warm. Now, this inversion is created because of sudden and excessive cooling of the surface. And that is why this is known as the case of surface inversion. Okay? And a negative lapse rate. Correct. Perfect. I hope this is understood. Now, subsidence inversion, upper air subsidence inversion. Now, in the case of this occurs, this is generally observed in the region of mid latitudes, when during winters. Now, in the case of the mid latitude during winters, the ground surface is very cold. Okay. So the ground is very cold. So as the ground surface is very cold, the air above it is also very cold. Now, let's suppose due to the influence of jet stream, anticyclonic conditions, or anything like that, if you have a sinking air parcel here, if let's suppose you have the sinking air parcel, now this air parcel will undergo a kind of an adiabatic compression. As a consequence, this will get warmed up. So this air parcel is getting compressed, right? So you have adiabatic compression, which leads to heating. Now, oftentimes, this creates a parcel of warm air which is above the very cold air on the ground. And that again creates a kind of subsidence. For example, when we talk about the case of London smog, which happened in the 1950s, that was the case of subsidence inversion, where all the pollutants they remained closer to the ground surface, influencing air pollution related diseases in large sections of the population. And methane poisoning, carbon monoxide poisoning was what caused large amount of casualties in the region. Then you have what is referred to as a frontal inversion. Now, when you talk about the frontal inversion, so how is it that frontal inversion gets? Again, in the case of be it a cold front or a warm front, if you have a cold front, as the cold air proceeds further, the warm air which is present, the warm air is lifted vertically upwards, isn't it? So, in a particular region, if you consider, there will be warm air above, cold air on the ground, right? So, a negative lapse rate, right? Or if you consider the case of a warm front, in the warm front, what happens? The warm air is the one which is active. So, in the case of the warm front, the cold air retains its position and the warm air starts to climb up very gradually. So, that is where you will have the condition of warm air, right? And here you have cold. So, again, the condition of a temperature invert. Again, observed in the region of mid latitude. The middle latitudes around 35 to 55 or 60 degrees, that is where you will find it. What about the polar region, by the way? When we talk about the polar region will always experience a condition of surface inversion, right? So when you talk about the surface inversion, it is present almost throughout the year in the region of the pole, because the polar region, the ground is always going to be very cold, isn't it? Present almost throughout the year in the poles. Yeah, the poles. Okay. Now, after this, we also have what is referred to as the valley inversion. In cold front, the warm air rises vertically and rapidly. Yes. Thermal inversion is when you consider the region of the top of tropopause and you compare it to the region of stratosphere. So there you have a kind of a negative lapse rate. So that is the condition of upper air thermal inversion. How such adiabatic conditions arrive during upper air subsidence? Basically, when you have a sinking air, let's suppose, Manisha, you have a region of anticyclonic condition, or you have sinking air created due to jet stream move. Now, in any of the cases, the air is being pushed down. Now, that will lead to the air getting compressed and air being forced into the regions of high air density. As a consequence, there will be a slight amount of warming. Let's suppose there is a gain of temperature of that sinking air even by 1 degree Celsius or 2 degrees Celsius. If that becomes warmer as compared to the ground surface, a condition of inversion, right? I hope that is understood. Now, valley inversion. Valley inversion, particularly in the region of the small valleys, in this case of the narrow valleys, if you consider a mountain and a valley, particularly during the nights. Now, during the nights, you will observe cold air above and that will be present on the mountain tops during the night. Whereas the valley bottom will still have a comparable warmer air. Now, this cold air is always heavier. So, as the cold air is heavier, it will tend to sink. Gravity will take over, will tend to sink. It will replace the warm air from the bottom of the valley. So, at the valley bottom, now you have the case of the cold air, warm air rises up. So, it is a case of valley inversion. That creates the condition of a valley fog as well, right? So, due to this, the temperature in the valley bottoms suddenly plummets during the nights. That is why it is advisable never to live or never to take shelter at the valley bottom, particularly when you talk about the narrow valleys, right? And this is where even the plants they suffer from frost conditions. Okay. While the cold air is sinking down the mountain, it will also experience adiabatic warmth. But then the differential between or the temperature difference between the cold and the warm air generally is so high that even if the cold air warms up ever so slightly, it is still colder than the warm air. That is why it is still colder. Okay. Now, frontal inversion, Gyan, is basically wherever you have the conditions or the presence of a front, warm air rises up, cold air retains the ground surface, and that is why you have the frontal inversion. Now, take the question. Normally, the temperature decreases with the increase in height from the Earth's surface. Why? The atmosphere can be heated upwards only from the Earth's surface. There is more moisture in the upper atmosphere. Air is less dense in the upper atmosphere. So, select the correct answer. What do you think is the reason why temperature decreases with the increase in height? So, here, first option or the first statement. Atmosphere can be heated upwards only from the Earth's surface. This is correct. Atmosphere is heated from the ground up. There is more moisture in the upper atmosphere. Absolutely no. And then the air is less dense in the upper atmosphere. That is correct, due to which the air is unable to trap that much amount of heat. So this is also correct. So the correct answer in this case is going to be right? Moisture decreases as you move from the ground upwards. Moisture decreases as you move from equator towards the poles. That is the variation in terms of moisture. Now we come to the portion of circulation, air circulation. Now you see, when we talk about air circulation, we know about the pressure systems, the pressure belts, air pressure. Now, air pressure, what do we know about air pressure? Wherever you have rising air is always associated with conditions of low pressure. Wherever you have sinking air is always associated with high pressure, isn't it? Now, basically, this rising and sinking air, why can and how can they be created? So, basically, they can be created due to thermal factors, that is, heating and cooling, and they can also be created due to dynamic factors, the movement, the convergence, and the divergence of wind. Okay, so when we talk about thermal factors, in this particular case, heating creates low pressure. Cooling always creates high pressure, right? This is something we observe at the region of equator, and this is something we observe at the region of pole. Whereas when we talk about the dynamic, so here you have the kind of convergence of winds on the ground surface pushes the winds upward. So convergence leads to rise of air, convergence leads to rise of air, right? And it will create low pressure. Whereas on the surface, divergence is associated with sinking or air, gets divergence, and that is also associated with high pressure. Okay. Now, this gives rise to various different types of winds, permanent wind systems in general, across the entirety of the planet. That is something which is now here. If you take a look at the various different factors which will influence the velocity and the direction of the wind, there are certain factors which will always influence what is the wind movement, what is the speed of the wind, and so on. So, amongst them, you have the important ones like the pressure gradient force. What is the pressure gradient force? The difference or the rate of change between high to low pressure. Always keep in mind that winds will always blow from a high pressure to a low pressure. Regardless of whatever conditions prevail, winds will always blow from a high pressure to low pressure. Now, greater the difference between high pressure and low pressure, stronger will be the wind. Lesser the difference between high pressure and low pressure, weaker will be the wind. Okay, so if pressure gradient force is high, wind velocity will be high. I will write this down as well. Frictional force. Frictional force is a kind of force of resistance. Force of resistance, as the wind moves on the surface, it encounters resistance in the form of the trees, in the form of the mountains, etc. So that is why on the surface, the wind tends to slow down. The wind factor tends to slow down. And then you have the Coriolis force. Coriolis force is basically what? It's an apparent force, aided because of the rotation of planets uh, on its axis. As the planet rotates on its axis, the speed of rotation is different at different places. Equator, the speed of rotation is the highest. Poles, speed of rotation is the minimal. So, when you move between the latitude, you experience a different speed of rotation in different places, due to which there is bending. Bending in the right in the northern hemisphere, bending to the left, the southern hemisphere. And then you have the gravitational force. gravitational force always acts downwards, keeping the winds closer to the surface. Now, pressure gradient force is what? Difference between rate of change between high pressure to low pressure. High pressure to low pressure. Okay? That is the rate of change which is associated. Now, if the pressure, it is the pressure gradient force which is responsible for initial movement of wind. If there is no pressure gradient, you will not have initial movement of wind at all. So pressure gradient force is responsible for the initial movement of the wind. Now, if the pressure gradient force is high, speed of the wind will be high. So speed is directly proportional to the pressure gradient. Okay, keep that in mind. Winds always blow from a high to a low, right? Now, then you have the Coriolis force. Coriolis force, why does it act? If the planet would not be rotating, would the Coriolis force still be acting? Then Coriolis force would not be acting. The reason the Coriolis force acts is because that as the planet rotates, different areas have different rotational speed. So as you move from one region to another, you experience that different rotational speed. That is why the objects tend to fall ahead or the object tends to fall behind. Now, in the case of Coriolis force, it deflects the winds to the right in the northern hemisphere and deflects the wind to the left in the southern hemisphere. Greater the velocity of the wind, more will be the Coriolis bending. Lesser the velocity of the wind, lesser will be the bending due to Coriolis. Okay? Now, think about it when you consider the region of northern hemisphere, right? Let's suppose you have the condition of high pressure somewhere. Let's suppose you have the condition of low pressure somewhere. So what will be the direction of the wind? High pressure to low pressure. So can I say direction of pressure gradient force will be somewhat like this? But will the wind be able to directly reach there? No, the wind will have a motion somewhat like this. It will bend to the right. Why? Because the Coriolis force is acting rightwards. Isn't it? The Coriolis force is acting rightward. So that is why you say that Coriolis force always acts perpendicular to the pressure gradient force. Always. Right? Now, when the planet rotates, the speed of rotation at the region of the poles is zero. Speed of rotation at the region of equator is very high, around 1600 km per hour. So, at the region of poles, that difference in velocity appears to be very heightened. That is why Coriolis force is maximum at the region of the poles and is zero at the region of equator. That is the case of Coriolis force. So, maximum at the poles and is absent at equator. Coriolis force acts perpendicular to the pressure gradient. Now we know that when you have the wind speed which is higher, the deflection will be more. Now think about it. If I consider the surface and if I talk about the winds on the surface, there will be a lot of frictional force. The speed will reduce. But if I talk about winds at a greater altitude of, let's say, 8 kilometers, 10 kilometers, it will be very high. Deflection will be very high. Isn't it? So that is why the bending due to the Coriolis force is also going to be very high. That is why at higher elevations, you will find the winds deflecting to such an extent that they become almost parallel to the latitude at a great height, right? So those are known as geostrophic winds. Geostrophic winds, almost parallel the latitude, almost parallel the latitude. Okay. Now, then we have the case of as you can see the Coriolis force, the speed of rotation here is minimal. Speed of rotation is zero, equals zero. Speed of rotation is maximum. Of rotation is maximum. Right? So that is why, as this region is moving very fast, if let's suppose any object tends to move from this point to the region of equator, by that point of time, equator would have moved ahead, right? So if you have to implement it on a static image, you will implement, let's suppose you consider this region as B, you consider this region as A. Let's suppose an object is trying to move from B to A. Now, B is moving slowly, A is moving faster. So by the time that it reaches equator, A would have reached ahead. So if you have to represent it in the case of the diagram, you will indicate the image like this because the wind will reach somewhere behind A, the rightward bend, isn't it? So like that, you have the rightward bend in the northern hemisphere, leftward bend in the southern hemisphere. Then you have the frictional force. Frictional force lowers the speed of the wind. It says the force of resistance. This is basically the force of resistance. Okay. Now, closer to the surface, speed will be slow. Upper altitude, greater height, speed is very high. Speed is very, very high. Okay. Also, over seas, over water bodies, that is the seas and the oceans, the speed will be very high. Right. That is why, if you even talk about the permanent wind system, like the westerlies, the westerlies will be stronger in the northern hemisphere or will they be stronger in the southern hemisphere? They will always be stronger in the southern hemisphere because southern hemisphere is dominated by water bodies. In the northern hemisphere, dominated over land areas. So that is why the speed will reduce. That is why the westerlies, they are known by various names in the southern hemisphere, right? Furious 40s, Fury 50s, Shrieking 60s. That is the name associated because they have such a high velocity, they emanate that roaring sound. Okay. Now, that is the case of the frictional force. Now we come to the air circulation as per the tricellular model of air. So basically, you have a combined effect of the thermal and the dynamic pressure zones, which lead to the air circulation across both the hemisphere. And this generates the permanent wind systems on the surface, which are also known as the planetary winds, because they are prevalent all across the planet. They are prevalent all across the or all throughout the year. Now, what happens and how is it that this kind of a circulation is generated if we talk about it very briefly? So at the region of equator, due to intense amount of insolation, the temperature gets very high. So the air warms up and air tends to rise up. The air will rise up, form convective clouds, cause a lot of rain. Now eventually the air will divert, isn't it? The air will tend to divert. As the air moves further northwards, it cannot move because of the Coriolis bending beyond a certain point, right? The upper, if you consider, let's suppose, the upper air movement from the region of equator. Now the winds will be bending in upper air to the right. So it cannot move north beyond a certain point. So all the air will tend to accumulate in this region and then it will sink. Not because of the temperature on the ground, but because of the air accumulation. It will sink, will divert. One portion goes towards the region of the ITCZ or the equatorial low, other portion goes northward. In the meanwhile, the thermal high pressure which is created at the poles generates winds which move to the south. Now these winds will interact and as a consequence, there will be rise in the air column. This rise in the air column will create a kind of a low pressure, will lead to the formation of clouds, and eventually again a circulation. So, like that, you have the entire tricellular circulation. These are named as the Hadley cell, the Ferrel cell, and the polar cell. And it creates various different pressure systems. For example, here at the region of equatorial low, it ends up creating a thermal low pressure. Here it is, thermal low pressure. Okay. At the region of the poles, you have a thermal high pressure. Thermal high pressure. At the region of the subtropics, you have the subtropical high pressure. Tropical high pressure. At the region of the subpolar area, you have the dynamic low pressure. Subpolar. So these two are the pressure zones created due to the dynamic effect. These are dynamic pressure. Whereas the thermal and the or the case of the equatorial low and the polar high, they are the thermal. Okay. Now, that is the case of the tricellular model of circulation, which gives rise to the various wind systems. Now, these pressure systems shift to the north and to the south with the heating of the sun and with the change in the position of the sun. For example, here in this map, you would see the kind of isobaric representation in the month of January. You will observe that you have the kind of low pressure around the region of equator. Low pressure around the region of equator. What is also being referred to as the equatorial trough. Low pressure around the region of equator. Okay. Now observe that the ITCZ, as this equatorial low is also referred to, it bends over to the region of Australia, because during the summer months in southern hemisphere, Australia will be much warmer as compared to the region of equator. Okay, so that is the case of the equatorial low pressure, equatorial trough, or the ITC. Now, subtropical high pressure develops over Siberia, Siberian high, the region around Azores high, around Azores Island, Hawaiian high. These are created. These are subtropical or the dynamic high pressure. Then you basically have the subpolar low around Icelandic low, which gets created. Aleutian Islands, you have the Aleutian low also getting created. In the southern hemisphere, however, you will find a kind of a very uniform pressure distribution. Why? That is because, again, dominated by water body, temperature will change very gradually. Hence, the pressure systems will also be changing very, very gradually. Okay? Now, again, you will see that when we talk about the summer season in the northern hemisphere in the month of July, look at the low pressure ITCZ. The ITCZ transitions north. So the Siberian high disappears, right? The Azores high shifts around the region of Bermuda Islands, becomes Bermuda high. Hawaiian high again shifts slightly to the west, right? But in the southern hemisphere, again, a kind of a uniform distribution. That is something. Okay. So this is the case of the permanent wind systems and the case of the pressure systems. Now we come to the portion of the trade local wind. Now, local winds basically is restricted into certain areas. Okay. Restricted into the certain areas. Close proximity of isobars signifies a steep pressure gradient here. Local winds, these are those kind of wind systems which are restricted into a certain area and which are also temporary in nature. Very temporary in nature. Permanent wind systems, they last throughout the year. They are present across the planet. Hence, planetary winds or permanent wind. But when we talk about the local winds, restricted in a small portion. So those are your local wind systems. So here, local winds are of various different categories. You have the classification as seasonal local winds, which occur for one particular season. For example, if you consider Lu, Lu is the case of warm advection, which happens during the summer. You take the case of Phone, Chinook, Mistral, right? Sirocco, all of these. Then Blizzard, these are seasonal in nature. But then you also have some of the local winds which are daily in occurrence due to the differential heating and cooling. For example, you have the case of land and sea breeze and sea. Then you have the case of mountain and valley breeze and valley breeze. Okay. So these local winds are also subcategorized. I have put here and I will give you the entire list of the local winds. I hope you will be able to understand this and you will be able to revise that as well. Right? All the PDF collectors out there. So get the antlers up in order. So you will get that PDF tomorrow. You will get that PDF. You can basically rectify from the list. All that you need to do is basically look at the location, whether the wind is cold or warm. That is all that you have to do. We have to understand this map or learn also? No. You have to keep in mind that there is something known as the Azores High or Bermuda High. There is something known as the Hawaiian High. There is something known as the Siberian High. There is something known as Icelandic Low, and there is something known as Aleutian Low. That is something that you have to be aware of. Okay? Now, after this, basically, the land and the sea breeze. Where can I get the PPT? Here comes the basic question, the most important question. Where can I get the PPT? How can I download the PDF? It will be available in the Telegram group that I have indicated tomorrow. Okay. So tomorrow, regardless of how many messages you send today, regarding of how many question marks, regardless of how many question marks you put it today, it will be available tomorrow. Okay. Right. Now, land and sea breeze. So basically, when we talk about the land and the sea, they get heated at differential rates. Okay. So during the daytime, the land gets heated much faster. So as the land gets heated much faster, you basically have the low pressure, the land, right? Because it is heated. And water is comparatively cooler because water will take more time to get heated up. So you have a comparative high pressure over the water body. So winds will always blow from a high to a low. The winds will blow from the high pressure or the water, sea to the land, right? So the winds are named from the region where they originate. So that is basically what is referred to as the sea. So sea breeze will blow when? During the daytime. Now, during the nighttime, what happens? Land will cool down with a very fast pace. So it will be colder. So it will have a high pressure. Water will take more time to lose heat. So water will be warmer, a kind of a low pressure. So that is where the winds will blow from a high to a low. They are coming from land to the sea. So hence, during night, you basically have land breeze. Okay. Similarly, you basically have the case of the mountain and the valley breeze. Now, when we talk about the mountain and the valley breeze, again, there's differential heating of the mountain tops and the valley bottoms in terms of the amount of or the temperature that is recorded at the mountain tops and the valley bottom. Now, during the case of the or when you consider the mountain top, now during the daytime, what happens? So during the day, the hilltops will always get greater amount of insolation. So they will always end up experiencing a slightly warmer temperature. Valley bottoms comparatively will be cooler. So there will be basically a low pressure on top of the mountain and a comparative high pressure at the valley bottom, right? So the winds will blow from a high pressure to a low pressure. The winds will blow like this, right? And that is what is referred to as valley breeze. So valley breeze observed during the day, during day. During night time, mountain top will get much colder because the air density is less. There is nothing to trap that heat. So mountain top will lose heat very quickly. So here you will have cold air, high pressure condition, high pressure, whereas the valley bottoms will be much warmer in comparison. So here you have a comparative low pressure. So that is where the winds will blow from the mountain top to the valley bottom. That is what even causes valley inversion. So this is what leads to the mountain breeze during night time. Okay? During night. Then you have some of the regional local winds too, which blows over the region of northern part of India, which is very dry, warm advection from a general direction of west to east, raises the temperature to around 40-45 degrees Celsius, can end up creating heat waves as well. So that is basically the case of Lu, generally observed in the central and the northern part of India. Now, this wind system, when it moves over the region of Thar Desert, that is when it becomes very, very dry and very hot as well. So, Thar Desert also plays a substantial role in warming up and drying up the Lu. Now, this is observed in India. Now, in the region of western part of North America, where you have the presence of the Rockies, there on the leeward side of the Rockies, you basically have a wind system which is blowing. So the winds, when they approach so this is the western part and the eastern part of the Rockies. So across the western part, as the wind systems approach, they will rise up. They will rise up, they will be forced to expand. Not forced to expand, they will naturally expand, lead to the formation of clouds. And that will cause sufficient amount of rainfall. Now, the same wind systems, when they will cross the mountain, now these winds are dry. The moisture has been drained out of them. And as the winds then move downhill, downslope, they basically will start warming up. Why? Due to adiabatic compression. There is that adiabatic heating. Now, due to which the temperature increases ever so slightly. 4 degree, 5 degree, 7 degree temperature is what happens, right? So this air becomes warm and dry. Now, this will be able to melt the snow in this particular region on the foothills of the mountain. And that is where it is basically also referred to as snow eater, because it will melt the snow. Something very, very similar is also observed in the case of cone. Cone is observed. So Chinook is observed where? In the case of the Rocky Mountains, right? I hope everybody is aware about the location of the Rockies. Rockies are situated in the in the western and northwestern part of North America. Now, cone is experienced in the case of Alps, alpine mountain range. It has got the same phenomena as that of Chinook. Again, on the leeward side, it ends up warming up the region. So that is basically across the northern slope of the Alps mountain. Okay. If you consider the Alps mountain, which will have more insolation, northern slope or the southern slope? Let me know. Which will have a warmer or more insolation, southern slope of Alps or northern slope of Alps? What do you think? Very good. Always southern slope of Alps will have higher amount of insolation. Northern slope will have indirect insolation, right? That is the factor associated with insolation that we covered, where the configuration of the land was talked about. Okay. Now, cone also warms up the region of the Swiss Alps and creates a kind of a climatic oasis, early sowing season of grapes, etc., in the region of Swiss Alps. Then you have during the winters a cold local wind which blows from the region of France and Spain. Now, this is what is referred to as Mistral. It is very cold. Why? Because during winters, the land becomes very cold. So the land ends up becoming a condition of a high pressure. From here, the winds will move towards the warmer region of the Mediterranean. And that is why these are the cold winds. That is Mistral. Okay. Then you have blizzard. What is blizzard? Blizzards are basically very cold winds which move in the polar areas, right? So they come from the poles southwards, the region of Siberia, Eurasia, and so on. So they will hit the region of Canada, Northern Europe, as well as the region of northern part of Asia. Now, because they are the cold winds coming from the region of the poles, they will always be able to carry a lot of snow and the powdery particles along with them. They move at a speed of 80 to 90 km per hour. And that is why they will always cause very cold conditions. They will lower the temperature in the region all of a sudden. So that is the condition of a blizzard. Okay. Violent, stormy, cold, and powdery polar wind laden with dry snow. That is the case of blizzard. I hope this is something which is understood now. Right? Now, then you have Sirocco. Sirocco is associated with the arrival of blood rain. What is this blood rain? So Sirocco, which originates from the region of the Sahara, there it picks up the red particles or the red sand, which is rich in iron. After that, it crosses the region of the Mediterranean where it picks up a lot of moisture. And then it moves to the southern slope or the southern coast of the Italian peninsula and southern Europe. And there it dumps that moisture along with the red sand. And that appears in the form of red droplets. That is why it is regarded as blood rain. So red sand from the Sahara, moisture from Mediterranean dumped over the region of southern Europe and the Italian peninsula. These are some of the winds that you can take a look at it in the sense of the location, and then on the basis of the continents, which are the winds, where they are present, warm or cold, will be provided in the PDF. You can revise it, ratify it, understand it. That is something which can be done. Okay. Now, this is consisting of all the various different continents that you can come across. Right. I hope till now everybody is comfortable. Now, after this, we come to the portion of humidity, clouds, and precipitation or rain. Now, you see, what is humidity? Amount of moisture which is present in the air parcel, that is what is regarded as humidity, isn't it? Now, this humidity, basically, what is the amount of moisture which is present in the. So, at any given temperature, air will have a certain capacity to carry moisture. That is what is referred to as carrying capacity of the air. Now, this carrying capacity of air, that is something which is proportional to the temperature. If the temperature increases, the air is able to carry more amount of water vapor. Why? Because if there is an increase in temperature, there is a larger gap between the particles. More water vapor can be accommodated in between. If the temperature reduces, there is less gap between the gaseous particles. Less water vapor will be accommodated. So if I ask you to compare between the region of the poles and the region of equator, where do you think there will be more amount of water vapor which can be present? What do you think? At equator or at the region of the poles? Where will there be a greater amount of moisture? Always at the region of equator, right? So basically, at the region of equator, greater moisture. Why? Because the temperature is high. So its ability to carry that moisture is much higher. Whereas in the poles, the temperature is very low, so it won't be able to carry that much amount of moisture anymore. Okay? So that is the case of humidity. Now, if Let's suppose any air parcel is having as much amount of moisture as is the carrying capacity. Then that is referred to as the point of saturation. When vapor present in the air equals carrying capacity, that means what? That indicates that air is saturated. Now, if the air is cooled further, then it will lead to condensation. Cooling will lead to condensation. But if you warm up this saturated air, again it will become unsaturated. Okay? Now, humidity is basically measured in different ways and mechanisms. One is the manner in which per unit volume of air parcel, you measure the weight of the water vapor. So, for example, in 1 meter cube of air parcel, what is the amount of water vapor? So, that is something which is regarded as absolute humidity. So, absolute humidity expressed in gram per meter cube. That is, if you consider an air parcel of 1 meter cube, right? Let's suppose in this you have 5 grams of moisture. So, that basically comes out to be 5 gram per meter cube. Okay? Now, as you move from equator to the poles, absolute humidity tends to decrease. Why? Because the carrying capacity of air in itself tends to decrease with the decrease in temperature. Then you have what is referred to as specific humidity. What is specific humidity? In that, rather than 1 meter cube of air, you consider 1 kg of air. 1 kg of air, whatever might be the volume. In that, you measure what is the amount of vapor which is. If the amount of vapor present in that is 5 grams, so the specific humidity is 5 parts per thousand. Okay. You see, absolute humidity can change if the temperature changes, if the volume changes, etc. But specific humidity is very consistent. It does not change often with the change of the various other factors. So, specific humidity is used for scientific measurements of climatic conditions. Then you have what is known as relative humidity. When you talk about relative humidity, it is basically the amount of water vapor that is present in the air to what it can hold. So, in general, in simple terms, vapor present by carrying capacity divided by carrying capacity into 100. That is relative humidity. Okay. Now, any air parcel, if it is cooled, then what will that mean? That carrying capacity will reduce. That is, the denominator in this case will reduce. If the carrying capacity will reduce, that means what? Basically, relative humidity. Okay. Any air parcel, when it is heated, when it is warmed, then carrying capacity will increase. That means what? Relative humidity will reduce. So, relative humidity is also influenced by temperature, right? When relative humidity is 100%, that is when we say to have saturated air. Saturated. Okay. That is when you have saturated air. So, any cooling beyond when the air has reached 100% relative humidity, if there is any cooling beyond that, that is when you have condensation, be it cloud formation higher up, near the surface, fog formation, on the surface, dew formation, and frost formation. That is going to be possible only if the air is cooled beyond the point of saturation or beyond the point of 100% relative. Okay. Now, after this, the case of the cloud formation. Cloud formation is very simple. You see, in the case or near the ground surface, as the air tends to rise up, it will expand, it will lose temperature. As it tends to lose temperature, the relative humidity will keep on increasing. A point will come when the relative humidity reaches 100%. Okay? If it rises further, that is when it will condense in the form of small droplets or particles of ice, and that leads to formation. By the way, when the relative humidity reaches 100%, can the air rise up any further? Or will the rise of air stop when the relative humidity reaches 100? What do you think? When the air rises up and relative humidity of 100% is achieved, will the air rise up further or won't it rise further? Will stop. Very good. Anirudh. Manikandan. Very good. Rajesh. All of you. Correct. The air will continue to rise up as long as it is warmer than the surrounding, independent of the factor of relative humidity. The air will continue to rise up as long as it is warmer than the surrounding. Clouds will tend to keep, or the cloud will be pulled higher up and higher up. Okay, so it is not something which will be determined by relative humidity. Now, these clouds will be created. Now, in these clouds, you have the ice particles, water droplets, etc. Now, eventually, as these water droplets, ice particles, etc., they become heavy, they will start falling down. As they start falling down, there will be partial melting, and that is when they will get converted into liquid water droplets. And that is when the ground will receive, on the ground surface, you will end up receiving rainfall. However, let's suppose the ground temperature is very low. Let's suppose. In case the ground temperature is very low, freezing. In that case, as the ice particles fall, they will initially melt into liquid water droplets. But as the ground temperature is very low, then it will reef and you will receive. So snowfall will be received only when you have the ground temperature, which is very, very. Only in that case will you have the snow. Otherwise, you have the case of rainfall. Okay? Now, the classification of clouds. You see, clouds are classified based upon the altitude where they are formed and based upon the shape that they have. So, in the case of clouds, when they are in an accumulated shape, like heaps of cotton, cumulus, if they have a layered formation, strata, stratus, right? If they are very high altitude, feathery, wispy, then you have cirrus. If they are multi layered, then you have the nimbus, cumulonimbus, and nimbostratus. That is the generic classification. Okay, so accordingly, whatever is the height, you attach it in the prefix, and the nature of the cloud, you attach it in the suffix. Okay, that is how basically you can talk about or you can classify the clouds in. Now, here, one thing, some or one particular portion that many of you have a doubt regarding the high altitude clouds, low altitude clouds, and the concept of heating and cooling. You see, high altitude clouds like cirrus clouds, will they be very dense? Never. High altitude, high altitude clouds will be having very low density, very thin in nature. So, will they be able to prevent the solar rays from coming down? The solar rays will simply penetrate through, right? But when you talk about the long wave terrestrial radiation, that will be blocked by the high level. So, they will cause warming, okay? Because they cannot prevent the solar rays and they will re radiate back the terrestrial radiation. So, high level clouds are always associated with Clouds always associated with. But what about the low altitude? Low altitude clouds can also reflect the terrestrial radiation. But more important than that, when you consider a low altitude cloud, let's suppose a cumulonimbus or a cumulus or a stratocumulus, etc. In this case, they will be blocking the solar radiation itself. They will not allow the solar insolation to come down. So that is where on the ground surface, comparatively, there will be cooler conditions, right? After all, we have seen in the case of the heat budget, I hope we are aware that almost 27% of the solar radiation is reflected back from the clouds itself. They never reach the ground surface. Almost 27% of. Okay, so they are reflected back from the top of the clouds itself. So low level clouds are always associated with. Okay, I hope this is also a concept which is. Cirro always means high altitude, formed at an altitude of 10 to 12 kilometers from the surface. They will never be associated with rainfall. They don't bring rainfall. Okay, even if the rain droplets they start to fall, they will re-evaporate up again. Okay, won't the thicker clouds reflect the heat released? But then the heat won't reach the surface, Athar. The heat won't even reach the surface. They can reflect that heat from the surface, but for that, the surface needs to be heated up. So, for the surface to be heated up, you need the solar rays. The solar rays in itself are reflected by the low level cloud. Okay. Will the high level clouds have an even lower albedo than old snow? Not always. Depends on the density of the cloud. Okay. That depends on the density of the cloud form. Now, while nimbus always signifies rain and instability in atmosphere, because these are multi-layered, so you will have the formation of multiple droplets, ice particles, etc. Now, why it re-radiate long wave terrestrial radiation? Because long wave terrestrial radiation is the one having lower amount of energy, so that is why it will immediately be reflected back. Why no cumulus clouds at the poles? Because cumulus clouds are created generally as a consequence of evaporation or rising air parcel. Now, at the region of poles, neither do you have evaporation nor do you have the rising air parcel. That is why no cumulus clouds are created. Okay? Now, the event of a cloudburst. Cloudburst is caused when the clouds are unable to hold all the moisture that they have. All the moisture that they have, when it is suddenly dumped, that is when we refer to it as a cloudburst. Now, cloudburst mostly occurs where? Mostly the region of hilly area, hilly region. However, sometimes in the plain areas also, in the region of intense low pressure over plain. There also, you will experience the occurrence of these cloudburst events, right? So, what tends to happen is that in the mountainous areas, you basically have, if you have continued winds which are moist, the moist winds are continuous, they continue to rise up, right? Now, these moist winds, they will end up creating clouds, and because they are continuous, the clouds tend to grow larger and larger. The movement of these winds will keep these large clouds afloat. The moment this wind system becomes absent or weak, all of that suddenly brings copious amount of high amount of, and that is cloudburst. So cloudburst is when rainfall of 10 centimeter or more in an hour over 10 by 10 area that occurs. That is the case of a cloudburst. Okay. However, in the plains, intense low pressure also creates the same condition, right? Why intense low pressure over the plains? Because you have the case of excessive heating in certain areas. That can happen due to the upper air movement. A region can get heated up much more. It can have moist winds coming from the nearby water bodies. The moist wind will rise up and it will form the clouds. which will be much larger as compared to what the sustainable size is. Okay? Right. Now, after this, we come to hailstorm. What is a hailstorm? Hailstorm is a case where, due to intense low pressure condition on the ground surface, you have a very strong updraft of wind. And that updraft of wind creates a condition of multiple to and fro movement of the ice particles where they melt, refreeze, etc. And they get larger in size. Eventually, the ice particles become so large that they simply dump themselves on the ground surface. Excuse me. They dump themselves on the ground surface, and that is what is referred to as a hailstorm. And those ice chunks which fall on the ground, that is what is referred to as a hailstone. So, for the hailstorm to occur, you need two primary criteria to be fulfilled. One is the criteria of cumulonimbus clouds. Okay, cumulonimbus clouds. So that you can have multiple upward and downward movement within the cumulonimbus cloud. Then, strong updraft of updraft is vertical motion. There has to be a kind of vertical motion. So basically, let's suppose you consider a very thick cloud. Now, on the ground surface, if you have an intense low pressure, so what it will do, it will attract winds and the winds will rise up. Now, if there is an ice particle which is heavy, which starts to fall, it is impacted by the wind and the wind throws it back up. That is when whatever portion had been melted, it will refreeze. It will accumulate more particles from around it. It will grow larger in size. As it grows larger, it will again have a tendency to fall. Again, it is pushed up by the wind. It grows larger as it accumulates more materials as it refreezes again. Now, the ice particle is so large that despite the wind, it will fall on the ground in the form of large ice chunks. That is what is referred to as a hail. Okay? So, hailstorms will occur when you have cumulonimbus clouds and strong updraft of wind due to intense low pressure. Intense low pressure on the ground. Okay? The ground, the surface. That is the case of the hailstorm. I hope this is clear, right? Yes, multiple cooling cycles are to be observed. In India, snowfall is to be witnessed in the region only around Jammu Kashmir, Himachal Pradesh, Ladakh, then the region of Uttarakhand, Sikkim, Arunachal Pradesh. Rest of the country, we receive hailstorms. Okay, particularly during the summers, in the afternoons, in this particular month, you will experience a lot of these hailstorm events. Now, take a look at this question, previous year question here. Which one of the following statements is correct with regards to the cloud formation? Let me know. Cirrus clouds are composed of ice particles. Cirrus clouds have a flat base and appear as rising domes. Cumulus clouds are white and thin and form delicate patches and give a fibrous and a feathery appearance. Cumulus clouds are classified as high clouds, which is the answer in this. Correct. The answer is A. Cirrus clouds are composed of ice crystals. Simple, safe answer. B. Why is B incorrect? Cirrus clouds have flat base and appear as rising domes. Flat base and rising domes. This is the condition of what is known as stratocumulus, a combination of horizontal and vertical layering. Stratocumulus. Cirrus clouds are white and thin and form delicate, cumulus clouds are white and thin and form delicate patches and give a fibrous and feathery appearance. That is done by the cirrus clouds, not cumulus. Cumulus clouds are classified as high clouds. They are your low altitude clouds. Right? I I hope that is clear. Now, the rainfall. Rainfall anywhere across the world can be classified into three basic parts or three basic categories. One is the convectional rain. Convectional rainfall, which is generally observed in lower latitudes, equatorial region. Now, this happens where you have the rise of air, convection current engine. Now, this rise of air brings about cooling, forms initially cumulus cloud, eventually leading to the formation of a large cumulonimbus cloud. And that is where in the afternoons, around 2 p.m. to 4 p.m., they will be associated with very heavy rainfall along with thunder and lightning. This is something basically associated with the case of equatorial region, and islands in lower latitude. In lower latitude. Okay. Then orographic or relief rain. That is because of the impact of the mountains. So whenever you have a mountainous feature, an escarpment of sorts, that is when the air is forced to rise up. As the air is forced to rise up, it will lose temperature, it will expand, form clouds, and bring orograph. Then you have frontal or cyclonic due to low pressure created during a front, cold front or warm front, or the cyclonic condition, you have rainfall. By the way, when you have a cold front, in that particular case, the cold front, you will have a vertical rise of warm air. So, which kind of cloud is associated with cold front? Always cumulonimbus. So, in the case of a cold front, you will always have the condition of very heavy rainfall associated with thunder and lightning. That is the association of cold front. Now, when you have the condition of a warm front, in the case of a warm front, what will you observe? A gentle rise of warm air over the incline of the cold air, a gentle rise. So that is basically where you have the case of stratus kind of clouds, nimbostratus, altostratus, right? Cirrostratus. Those kind of clouds are to be formed. So long, moderate spells of rain, okay, but not very heavy rainfall, continuous rain, nimbostratus. Okay, cumulonimbus is always associated with very heavy conditions of rainfall and very violent weather conditions. Okay. Now, then we have fog. Fog is formed when you have condensation, which tends to occur very close to the surface. That is when you experience fog formation, right? Or a cloud which is created closer to the ground surface. That is fog. Now, fog also tends to occur when the air cools down beyond the point of saturation, and that is when the air reaches the 100% relative humidity. If it cools beyond that, it basically leads to condensation. Now, this fog formation is of different types based upon how that condensation is. You have the condition of radiation fog. Okay, radiation fog is simple to or similar to the case of surface inversion. Now, here the surface loses heat continuously. So, the air closer to the surface will also lose heat, right? So, it reaches saturation, loses heat beyond, forms the fog. Now, for the condition of this radiation fog, what is the condition required? Again, long winter nights so that the heat can be lost in a prolonged manner. Long winter nights, clear sky, clear and calm conditions. Okay. In very stormy conditions, when the wind is very high, will you have a fog formation? No. All the droplets will be driven away by the wind. Then you have what is known as advection fog. Advection, movement of wind, horizontal movement of wind. So basically, let's suppose if you consider a particular region which is cold, right? Now let's suppose a warm air comes in this area. warm air. Now, the warm air will also become colder. It will reach saturation, lose temperature, cool down beyond that, undergo condensation, lead to formation of, that is the case of advection. Then you have what is upslope fog. This happens in the sloping region with gentle rise of the air, what is referred to as orographic uplift. Orographic uplift. Now, as this orographic uplift happens, that is when it tends to lose temperature, and that is when basically there will be condensation and fog fall. But the breeze has to be gentle. If it is a strong wind, it will lead to orographic rainfall. Gentle breeze. That is what leads to the case of the upslope. Then you have what is also known as the valley fog. Valley fog is observed in the case of the mountain valleys, as the name in itself tells you. So, when you have the cold winds from the mountain tops which sink into the valley bottom, the warm air is pushed up and the cold air tends to sink down. As this cold air tends to sink down, there is cold air which reaches here, warm air will cool down, isn't it? As the warm air cools down, it will reach saturation, it will beyond that, and there will be condensation, fog formation in the entirety of the valley. Then you have what is known as steam fog. Steam fog is formed over the water bodies early in the morning or late at night during the months of the winter. So that is basically the case of the steam fog. Water bodies, okay? That is the case of during late night and early morning. Late night or early morning. So how is it that steam fog is created? So basically, when you consider a water body and you consider the land area, let's suppose you consider a small water body itself. Now here, during early morning or late night, let's suppose there is some amount of evaporation which is happening from the water. If this is your water and this is your land. Okay. Now, let's suppose some amount of evaporation is happening. Meanwhile, you have cold winds from the land because the land is much colder during the nights and early morning. So, the cold winds from the land, they come over to this region. Now, they encounter the water droplet, the water vapor. Water vapor immediately will get cooled down due to the impact of the cold breeze. And that is where they will condense. They will appear as rising sections, and hence they are named as steam fall. Okay, so that is how you observe the formation of steam fall. Right now, after this, we come to the concept of cyclones and anticyclones. Everybody is comfortable up till here? I hope everybody is okay up till now. Right now, what is a cyclone and what is an anticyclone? When we talk about a cyclone, cyclones are basically intense low pressure regions. Intense low pressure regions which end up initiating a circular movement of air. Rising circular movement of air, that is the case of a cyclone. Right? So here, when we consider a cyclone, intense low pressure initiating the rising air will always lead to cloud formation. Cyclones are always associated with heavy rains. Anticyclone, on the other hand, is the region of sinking air. Clear sky, no cloud formation, right? Sinking air, lack of rainfall. So anticyclones, lack of rainfall, cyclone, intense rainfall. Okay? Now, they have a kind of a circulation pattern. So, for example, when we consider the northern hemisphere, Now, in that case, if you consider the cyclone, the low pressure is very intense. All the winds will be attracted towards the low pressure, isn't it? All the winds will be attracted towards the low pressure. Now, in the northern hemisphere, the winds will bend to the right. The winds will bend to the right. So, here, what kind of circulation do you observe in the northern hemisphere? In the case of cyclone, you will observe a kind of an anti-clockwise, isn't it? So, anti-clockwise circulation in the northern hemisphere. But when we talk about the southern hemisphere, the winds will bend to the left. Yeah. So, in case of low pressure, the winds will bend to the left. So, the winds here bend to the left. So, what kind of circulation is observed here? You have a kind of a clockwise. Similarly, for anticyclones also, you have a kind of a circulation both in northern, the southern hemisphere. Okay, so that is the case of the circulation. Why in anticyclone no rainfall? Because in anticyclone you have sinking air column. For any cloud formation, you need rising air. Sinking air will lead to warming. It will never lead to condensation. That is why. Okay, that is why the regions of high pressure, they don't receive rainfall. Okay, now after this, we come to the classification of cyclones, the two types of cyclones that we have, that is the temperate cyclone and the tropical cyclone. Now, temperate cyclones happen why? Because of frontogenesis. Frontogenesis is required for the temperate cyclones to get created. Always, without frontogenesis, temperate cyclones can never be created. Now, where will the frontogenesis occur? Always in the case of the mid latitudes, around 40 to 65 degrees north and south. That is where frontogenesis will occur. So, in the region of mid latitudes. Now, in which month will frontogenesis be very common or very frequent and very intense? It will be very intense and frequent during the winter months when the temperature between the tropical and the polar air is, the difference of temperature is very high. Okay, that is when the fronts get exaggerated. During the summer condition, the difference of temperature between the tropical and the polar air is slightly less. But during the winter, it is much exaggerated because the poles have a temperature of -40, -50 degrees Celsius. Right? So, frontogenesis now, mostly during winter, most common or frequent during winter. Now, here the movement will happen from west to east under the influence of westerlies. Move from west to east under the influence of westerlies. Now, will every frontal formation lead to a temperate cyclone? No. But without frontal formation, temperate cyclone is not at all possible. Please keep that in mind. Okay. Without frontal formation, temperate cyclone is not possible. We'll go for a break at around 10, 9:45 or 10. That is when we'll go for a break. And after the break, we will cover the portion of Indian geography. Okay. Before that, let's cover the portion of physical geography. Okay. Now, so here, when we talk about the case of the fronts, every front will not lead to a temperate cyclone, but no temperate cyclone can be created without the formation. Okay. So, a temperate cyclone, also referred to as mid-latitude depression, a wave cyclone, because that is where in the shape of the wave is how these fronts end up getting created in the entire shape of a wave. That is how the frontal formation happens. That is how the frontal deformation tends to happen as well, isn't it? Now, temperate cyclones are active above mid-latitude region, 35 to 65 degree latitude. Now, direction of movement is from west to east, more pronounced during winter seasons. It is along these latitudes that the polar and the tropical air masses they will meet, right? So that is basically the case of the temperate cyclone. Now, the formation of it. It starts initially with the stationary phase, where you will observe that the cold polar air and the warm tropical air, they are close to each other. So that is the stationary front, which is now at this particular position, two alternatives or two possibilities arise. One, either the air will mix with each other and there will be frontolysis. Dissipation of the front can happen, right? So it can lead to either exaggeration or distortion of the front, exaggeration of the front. How the exaggeration of front will happen? Cold air enters into the region of warm air enters into the region of cold. The front gets exaggerated. Or the air will mix with each other, gain a normal temperature. That is the case of basically frontolysis can occur. If frontolysis occurs, no further cyclonic formation can also occur. No further cyclonic formation. But let's suppose if you have the exaggeration of the front gets distorted and much more activated, then you can have the temperate. So the cold air tries to enter into the region of the warm air, and the warm air tries to enter into the region of the cold air as well. So, as a consequence, what you will observe is that there's distortion of the front. Now, as the cold air is pushing in this region, the front is getting distorted, and you will have simultaneous formation of two. That is, in one region, you have the formation of a cold front, and in another area, you have the formation of warm front. Now, remember, we talked about the fact that the cloud types in the warm and the cold front, they are different. In the region of the cold front, there's a vertical rise of the warm air. As there is a vertical rise of warm air, cumulonimbus cloud associated with thunderstorms, lightning, and very heavy rain. Whereas in the case of the warm front, a general rise, stratus kind of cloud, continued but moderate rain. But nonetheless, regardless of the type of fronts, in this entire region, you have an intense low pressure created due to rising air. It is a dynamic low pressure which gets created in this, isn't it? A dynamic low pressure. This dynamic low pressure will attract more winds from all different. As a consequence, on the ground, the cold air will start to envelop it. The cold air will start to surround the ground region. And that is where the occlusion starts to happen. The cold front and the warm front, they get very close to each other, right? They get very, very close to each other. So, unlike the case of a tropical cyclone where you have a uniform condition experienced, in the case of a temperate cyclone, you have varying conditions experienced in close quarter. In the region of the cold front, very strong winds will be observed. But in the case of the warm front, gentle winds will be observed. Okay, gentle conditions will be observed in the region of warm front. Eventually, it will close down, the front will close down, and the entire cyclonic circulation will dissipate. So that is the case of the temperate cyclone. Now, this temperate cyclone is also known for the condition of bombogenesis or bomb cyclone. Bomb cyclone, what is bomb cyclone? So, in certain conditions and during certain cases, the low pressure intensifies so rapidly. So, if the pressure drops, drops by more than 24 millibar, 24 millibar within 24 hours, that would mean rapid intensification of the low pressure, rapid rise of the air parcel, right? And that would basically mean more intensification of the cyclone. That is what is referred to as a bomb cyclone or bombogenesis or explosive cyclogenesis. most commonly observed in the case of temperate cyclone. Mostly observed in temperate cyclone, however, can be observed even in tropical cyclone. It is not the case of only, it is the case of mostly. Mostly observed in temperate, in majority of the cases, temperate cyclone. Temperate cyclones, few of them will have an eye, few of them will not have an eye. Not necessary that everything or every temperate cyclone will have an eye. They can last for a duration as long as the front gets distorted. So they can last for a duration of 20 days, 14 days to 21 days in general, right? Their diameter is very large to the extent of around 750 to 1000 kilometers is the diameter. But when we talk about tropical cyclones are much narrower, much smaller, much smaller, but they are more destructive. The wind speed is much higher. Why? Because of the thermal low pressure. Thermal low pressure is more effective in this case as compared to a dynamic low. So that is why the wind speed is very high. Destruction potential is much more higher any as compared to anything else. Right? Their size is also less. Around 500 kilometers is the radius that you will observe. Now, these tropical cyclones are observed within the tropics of the world. They are named differently. They are named as cyclones in the northern Indian Ocean, Willy Willies in the region of northern portion of Australia, typhoons in the region of Western Pacific and South China Sea, hurricanes in the region around North America. That is where they are named differently. But not every low pressure develops into a cyclone. So you need certain conditions which require to be fulfilled. Only then we refer to it as a kind of a complete. So in the case of a tropical cyclone, first most important condition is the presence of a large sea surface area with a temperature higher than 27 degrees. Only then will you have an intense low pressure. Intense low pressure. Only in that case, an intense low pressure will be created. Otherwise, it won't be. Secondly, presence of Coriolis force. Unless and until Coriolis force is present, a circular motion of winds will never be achieved. Never. So that is why Coriolis force is a must. That is why tropical cyclones are never formed at the region of equator. Tropical cyclones never formed at equator and also never cross equator. Never cross. However, sometimes due to the eddies that are generated, eddy currents which are generated in the oceans, you have the simultaneous formation of tropical cyclones in both northern and southern hemisphere. Those are known as the twin cyclone. Okay, so that is basically the case where simultaneous presence can happen, right? There's also the case where the tropical cyclones can end up converging with each other, colliding with each other. They can strengthen, they can weaken as well. So that is when the two tropical cyclones in close quarter, they interact with each other. And what is that referred to as? That is something which is referred to as the Fujiwara effect. So that is your Fujiwara effect. Basically meaning the interaction between two of the tropical cyclones, whether they get stronger, whether they get weaker, whether they spin off into multiple branches. That is the case of the Fujiwara effect. For that, they don't necessarily need to cross the equator. They can simultaneously be formed in the eastern and the western part of southern Indian Ocean, and they can crisscross, right? Or northern Pacific. Southern Pacific and southern Atlantic, they don't generally have the formation of tropical cyclone. The reason being what? That ITCZ rarely comes across, or that low pressure rarely comes across in the southern equatorial Pacific and southern equatorial Atlantic. Then, small variation in the vertical wind speed, what is also referred to as the wind shear. So that basically means the wind velocity at the surface and the wind velocity higher up, there should not be a massive difference. That is something which can be attainable only over water body, not over the land area. Otherwise, what will happen? All the cloud formation, circulation, everything will be carried away by the upper altitude. That is why you need a kind of a small variation in vertical wind speed, right? Can a tropical cyclone from the northern and southern hemisphere meet? Never. Never. Are tropical cyclones also move from west to east? No. They move from east to west. Why? Because in the tropics, the permanent wind systems are what? The trade winds. So they move from east to west. Right? If UPSC asks no cyclone can be formed at equator, we should mark yes. Okay? Fujiwara effect, you don't need to go into the depth of it, Niharika. Fujiwara effect is basically, let's suppose you have a cyclonic circulation like this, you have another cyclonic circulation like this. Now they will interact with each other. It can lead to one getting much weaker, one getting much stronger, or a combined much stronger one, or one stronger one, two smaller ones. So that is the interaction between the two cyclones. What is the intensity of them? How do they interact? Okay. Now, a pre-existing weak low pressure area. That is important. That is why when the ITCZ lies over these water bodies, that is an ideal condition for the formation of this cyclonic condition, right? And also upper air divergence. Upper air divergence. This upper air divergence is important for the maintenance of the low pressure on the upper air divergence. Okay. Now, after this, if you take a look at the formation of tropical cyclone, so basically you will observe that you have intense low pressure on the surface. This intense low pressure on the surface will attract winds from all directions. Now, these winds are warm and these winds are moist. Now, they will rise up in a spiral manner. As they rise up, they will lose temperature. They will undergo condensation. And when they undergo condensation, they will release latent heat of condensation. That latent heat of condensation is very important and vital for the entire upkeep of the tropical cyclone. Now, that latent heat of condensation eventually will be released in the central. So the temperature in the central portion increases. That is why there is no cloud formation in the central portion of the cyclone, and hence a tropical cyclone will always have a large eye, what is known as the eye of the cyclone. Okay. Now, in the meanwhile, here, as there is a rising spiral, in this region, you have some sinking air as well. Okay, in this region. Little amount, but sinking air. So, like this, the latent heat of condensation increases the heat in the central portion. That heat will intensify the low pressure on the surface. More winds will be attracted. More condensation will happen. More heat will be released. The cycle continues. That is why the tropical cyclone is also what is referred to as a heat engine. So basically, the entire process is low pressure on the surface. Now, this low pressure on the surface basically means moist winds and warm winds. Now, these moist and warm winds cool down and rise up and undergo condensation and condense, right? As they will rise up and will undergo condensation, latent heat is released. Heat is released. This latent heat, when it is released, will lead to what? It will intensify the low pressure, intensify the low pressure would mean what? more warm winds and moist winds will come in, and this is a self-fulfilling cycle, a feedback loop. That is why tropical cyclones are also what are referred to as heat engines. Now, that is the case of tropical cyclones. Now, these tropical cyclones in the region of the low pressure, as long as they remain over the water body, they will get stronger and stronger. Okay, as long as they have the low pressure, they will get over the water body, more moisture will be there, they get stronger. They will dissipate only when the moisture is cut off. That is when they will get in contact with the land. Then they will dissipate. So the tropical cyclones dissipate when they hit the land. However, in certain cases, the land is known to have some amount of rainfall previously as well. That is when certain cyclones like Titli, like Tote, all of them, they have further intensified. But that is a very rare occurrence. Mostly, they will basically weaken when they hit the land. Now, the cyclones are named by the Tropical Cyclone Warning Center. It detects the cyclonic disturbance and circulations in the various oceans. It alerts the regional specialized meteorological center. There are six regional specialized meteorological centers across the world. For northern Indian Ocean, the RSMC lies in New Delhi. For southern Indian Ocean, it lies in the region of the Reunion Islands. For southern Pacific, it lies in the region of Nadi. For western Pacific and South China Sea, the RSMC is in Tokyo. For the eastern Pacific, it lies in Honolulu. For the region of Atlantic, it lies in Miami. So these are your six different RSMCs. So these RSMCs, then when they get to know that a cyclone is actually getting formed, then they take out the list. And naming is done from the list. Okay. So here, when you talk about the list in the Northern Indian Ocean, the countries are basically arranged in an alphabetical manner, right? From top to bottom. And all the countries, so there are 13 countries in the list. All of them have given 13 names, which are arranged in the rows in front of them. And that is where you will observe one by one the name is picked. Any of the cyclonic names, a name which is given to the cyclone, if it causes immense amount of destruction or damage, that name is struck off, never to be utilized ever again. Right now, we have observed cyclone Fengal, cyclone Sakti is building up, right? So, be it in Arabian Sea or Bay of Bengal, right now there is a low pressure depression being created in the region of Andaman Sea. If it develops into a cyclone, it will be named Cyclone Shakti. Now, the next cyclone, wherever it will occur in the northern Indian Ocean, it will be named as Monta. So, like that, the naming is done in the case of the cyclone. Okay. Now, this is the basic difference between the tropical and the temperate cyclone, which you can revise with the PDF as well. Now, comfortable up till here? I hope everybody is comfortable, right? Now, after this, we basically come to certain atmospheric phenomena. Certain atmospheric phenomena like the ENSO, like the case of IOD, MJO, and jet stream, right? So here, by the way, don't need to remember the names of the cyclone. Please don't start remembering the name of the cyclone. If you have that much mental capability, remember something else, art and culture, etc. From but in the case of the cyclones, that question won't be asked. Okay. Now, starting with the basic Walker circulation. So, what is this Walker circulation? So, due to the influence of the trade winds, what tends to happen is that warm water from the region of the surface of the Pacific, that warm water is carried from east to west. So, that is where the warm water tends to accumulate in the region of the Western Pacific, right? This warm water, as it accumulates over the region of Western Pacific, it ends up creating a region of low pressure. Meanwhile, in the Eastern Pacific, you have the condition of upwelling. Upwelling creates a region of cold water. So that creates a condition of high pressure. So you have the trade winds itself. In general, the wind motion is from high pressure to the low pressure. The winds will rise up. They will be able to form clouds. These clouds will bring a lot of rainfall. And then there will be divergence. Okay, that is the kind of circulation which is referred to as the Walker circulation. So, in the condition of Walker circulation, what do you observe? Rainfall is observed across Western Pacific. Western Pacific. Whereas when we talk about Eastern Pacific, it is dry. Eastern Pacific due to high pressure, right? Peruvian coastline is very, very. So this is the case of the entire flowchart. Also, I have given for you, so you can revise it with this as well. So trade winds blow from a general direction of east to west. The winds blowing over the vast region of the Pacific gain a velocity because of low frictional force, and they will drag the surface water along with them. The surface water is a war mist which accumulates in the region of Western Pacific, creates a condition of intense low pressure, and that is the Walker circulation, right? So this is the entire circulation of the Walker cell. Now, what tends to happen sometimes is that these trade winds, they get strengthened. As they get strengthened, the region of warm water, that tends to increase. It gets exaggerated. So the low pressure across the Western Pacific becomes much more exaggerated. This attracts stronger winds, which creates upwelling in the larger area of Eastern and Central Pacific as well. And that means you have very cold waters in the region of Eastern and Central. So the trade winds become much more stronger as the pressure gradient force escalates almost exponentially. So the low pressure becomes intense, high pressure becomes more intense. So this is a kind of intensified Walker circulation. And that is what is referred to as the condition of La Nina. So when we talk about La Nina is intensified Walker cell. Okay. So in the case of La Nina, what do you experience in terms of rainfall, right? So in the case of Western Pacific, very heavy rainfall, flood-like conditions, flood-like conditions. Indonesia, Philippines, Australia, all of them will receive very heavy amount of rain. In terms of India, excess rains in India as well. Okay, during monsoon. Eastern Pacific, drought-like condition, drought-like. Okay, now during certain years, the Pacific gets warmed up. As the Pacific warms up, in that particular case, the trade winds become absent or very weak, due to which the warm water which was there in the Western Pacific, it tends to flow back. As it flows back, uh, I think you would have understood or you would have attended the session where I have talked about the table fan analogy, right? The table fan and the bucket analogy. So, as long as the table fan blows air to the bucket, the water appears to be accumulated on one side. The moment you switch off the fan, water tends to flow back, isn't it? So, that is where the water tends to flow back from West Pacific to the East Pacific. And that is where the warm water tends to come in the region of the East. So, this is basically where you have the creation of low pressure now. So, the winds get attracted to this low pressure. They will rise up, form clouds, cause excessive rains in this entire region. Okay, then they will diverge. Meanwhile, there is going to be upwelling and colder water in this region, high pressure. So, there is going to be a circulation like this. So, El Nino is the reverted Walker cell, reverse of Walker circulation, associated with lesser rainfall in India. Walker circulation. Okay. So, Australian coastline will be very dry, drought like conditions during summer. So, that will create wildfires, bushfires. Whereas when you talk about the Peruvian coastline, heavy amount of rainfall across the Peruvian coastline. So there is, as you can see, a general flow back of water from Western Pacific to the Eastern Pacific. A weakening of trade winds when the Pacific gets intensely heated up, mostly during the case of southern summers. That is in the month of November, December, January, February is when the condition of El Nino will always end up peaking. The impact of the monsoon is indicated by this chart, where you can see that the case of El Nino is associated with reduced rainfall in India. The case of La Nina is associated with increased rainfall in India. Okay. Now, take a look at this particular question as well. So, La Nina is suspected to have caused recent floods in Australia. How is La Nina different from El Nino? La Nina is characterized by unusually cold ocean temperature in equatorial Indian Ocean, whereas El Nino is characterized by unusually warm ocean temperature in equatorial Pacific. Incorrect, because we have not talked about Indian Ocean at all. La Nina is a factor of only the Pacific Ocean. El Nino has adverse effect on southwest monsoon of India, but La Nina has no effect on the monsoon. This is also incorrect because La Nina brings about excess rainfall to India. Then you have the condition of Indian Ocean dipole. So when you talk about Indian Ocean dipole, so this is basically at the region of equatorial Indian Ocean, the difference of temperature between the eastern and the western Indian Ocean, that is what is referred to as the Indian Ocean dipole. So Indian Ocean dipole also has got three phases, just like the ENSO. It has got neutral, which intensifies to form negative, and you also have what is referred to as the positive phase. For Indian monsoon, neutral and negative, they are associated with reduced rain. Reduced rain. Positive is associated with increased rains in India. Increased. Okay. So what is neutral? Neutral is when you have low pressure in the region of Eastern Indian Ocean. You have the condition of low pressure in the region of Eastern Indian Ocean. That is where the winds come towards the low pressure. You have upwelling in the region of Western Indian Ocean, and you will have a high pressure in this. So this is a kind of a neutral phase. Now, if the winds get stronger, they will carry more surface warm water in the Eastern Indian Ocean and it will be intensified. So, intensified form of the neutral phase is what is also regarded as the negative phase of IOD, where it is an intensified circulation as compared to the neutral phase, right? And here you have cooler than normal waters which are present and which are found in the region of Western Indian Ocean. Under the condition of neutral and negative IOD, cyclonic formations will be observed in the region of Bay of Bengal. But under the condition of a positive IOD, where the heating happens in the Western Indian Ocean, it is good for the monsoon also, and also more cyclonic formations will occur in the region of Arabian. Okay, so that is the case of the Indian Ocean dipole. Now, these are the pressure systems which are fixed in a particular area. Now, you also have a pressure system which tends to move. That is the case of what is referred to as Madden-Julian oscillation. Madden-Julian oscillation is a kind of a pressure system which tends to move from west to east along with the rotation of planet Earth. This is a circulation system which tends to move. So, it has got two distinct phases: low pressure or the phase of enhanced rainfall, and high pressure phase of reduced rainfall. The entire circulation tends to move. Right. Now, this circulation, wherever it lies, the low pressure region will bring rain. So, it completes the entire cycle across the planet for a period of 30 days or 45 days or 60 days. Now, during the monsoon period, If the cycle or the entire phase of MGO circulation, if it is shorter cycle, means what? That this MGO phase will come over India, the low pressure phase will come over India more frequently. So shorter cycle means more rains during monsoon. Means during, okay? Longer cycle means that it will come over India lesser number of times. So less rains experienced over India during the monsoon season or the monsoonal. Then we come across what is a jet stream. High altitude wind movement which is experienced over the region to the top portion of troposphere. That is from the altitude of 8 to 12, 13 kilometers. You experience very high altitude and very high velocity wind movement. Those are regarded as jet streams. Now, jet streams, why are they created? These are also a kind of geostrophic winds. Why are they created? They are created when there is a difference of temperature between the cold and the warm air. That is where in the upper altitude you have a pressure gradient force which is, and that is what leads to the generation of a jet stream. Okay, so that is the case of this particular jet stream. Jet stream basically is a very high altitude, high velocity wind which moves in the upper portion of troposphere. Right? Now, here, when we talk about the formation of the jet streams will always be created wherever you have difference of temperature in upper atmosphere. So, at the boundary zone between the Hadley and the Ferrel cell, at the boundary zone between the Ferrel and the polar cell, that is where the difference of temperature is present. So, this is where the permanent jets exist. So, the planet has got four permanent jets, right? The polar jet and the subtropical westerly jet in both the hemispheres. Four permanent jet, and you also have many temporary jets, like the Somali jet or the Findlater jet, the tropical easterly jet, the Siberian jet. There are multiple temporary jets as well, but you have the four permanent jet streams, right? Now, take a look at this question. Let us solve this particular question. So, jet streams occur in the northern hemisphere only. Only some cyclones develop an eye. The temperature inside the eye of the cyclone is nearly 10 degrees Celsius lesser than the surrounding. The correct answer in this case is going to be C. That is 2 only. That is because are the jet streams formed only in the northern hemisphere? They can be formed both in the northern and the southern hemisphere. Right? Now, only some cyclones develop an eye. Correct? Tropical cyclones will always develop an eye. Temperate cyclones might or might not develop an eye. The temperature inside the eye of the cyclone is 10 degrees Celsius lesser than the surrounding. Temperature inside the eye of the cyclone is always higher. Always higher than the surrounding. Getting it? So that is why basically it is incorrect. So that is why the correct answer is D, that is 2. Right? Now, along with that, let us cover the portion of Indian climate also, the Indian monsoon. So when we talk about the Indian monsoon, you see, Indian monsoon is a phenomena, even though we have covered it previously in the compilation videos as well. But very quickly, if we talk about it, so in the case of Indian monsoon, monsoon means what? Monsoon is a seasonal reversal of wind. Why this, sir? Podvantage. Why higher temperature in the eye? Because of the latent heat of condensation which is released in the eye. Okay, that is why. Now, when we talk about the Indian monsoon, so you see, monsoon means seasonal reversal of the wind. The wind direction completely reverts. That is the case of Indian monsoon, right? Now, Indian monsoon is dependent on multiple different factors. Initially, the heating of the land creates a substantial low pressure over the land mass of India, where the temperatures frequently they are in the range of 40-45 degrees Celsius. So a substantial low pressure is created over the land area. Comparatively, the water bodies are cooler. So they experience or they exhibit a kind of a high pressure. So the winds will always blow from the high pressure to the low pressure. They will carry the amount of moisture. But along with that, the ITCZ, which represents the thermal low pressure, that also tends to shift northward. It lies over the Indian subcontinent. As it lies over the Indian subcontinent, that is when there will be the trade winds from the southern hemisphere crossing all the water bodies, bringing all the moisture, bringing all the rainfall. But they will not bring rainfall as long as you have the southern branch of the subtropical westerly jet stream. The subtropical westerly jet stream, basically, that will be the ones which will be, or the southern branch of it will be moving over the Indian subcontinent. With the shifting of the pressure belts, the southern branch of the subtropical westerly jet stream also shifts north, disappears. As it disappears, that is when you have the onset of the monsoon. Meanwhile, the heating of the Tibetan highland creates that intense low pressure over the region of Tibet. You have the high altitude winds which are generated. One of them moves over the Kolkata Hyderabad axis from east to west, reaches the region of Horn of Africa, strengthens the entire monsoon circulation, what is known as the tropical easterly jet. The strength of the high pressure in the region of the Mascarene Islands in southern Indian Ocean is equally very important in order to supply the winds coming over to the Indian subcontinent. And that is why you basically have the case of the Mascarene high pressure being a key point in terms of the Indian. Okay, so that is basically the case how the monsoon phenomena occurs. One by one, if you take a look at it, so you see the heating of the land, the substantial heating of the land means the ITCZ comes over to India in the month of May, June, July. Now, once the ITCZ comes over to India, the trade winds, the southern trade winds, they will be attracted to the ITCZ. They will be moving like this, crossing the region of the equator. Look at this. This is the satellite imagery of the trade winds. The trade winds will be moving like this towards the ITCZ. They will bring a lot of moisture, but they will not cause rainfall as long as you have the southern branch of the subtropical jet stream. Because the jet streams, they act like a blockage. They don't allow a free flow of air happening under. So that is why that will serve as a blockage. But slowly and steadily, with the heating of the landmass, this jet stream, as this jet stream disappears, that is when you will have the rush of the winds over to India. And that is when the rains start occurring in the region of Kerala coastline. And that is what is referred to as the of onset of monsoon. Okay. Now, after this, you have the case where the Tibetan highland gets heated. As the Tibetan highland gets heated up during the month of the May, June, July, that is when you have the winds which rise up from the Tibetan highland. Intense low pressure is created. As the winds they rise up, that is when the winds will then diverge in all directions. One of the winds that follows this axis, it moves across the region of Horn of Africa, then bends to the left in the southern hemisphere, settles down around the region of the Mascarene Islands, and that, in a way, fuels the surface winds moving over to India. So that is what your tropical easterly jet is. Tropical easterly jet. Now, this tropical easterly jet, it will always strengthen the monsoon, makes the monsoon stronger. Okay? Monsoon stronger. Always. Okay? Now, here, why? Because it will strengthen the Mascarene high and will generate more amount of winds over to Indian. Now, the impact of Enzo cycle, if you consider the El Nino, La Nina conditions. During the condition of El Nino, what happens? Mascarene high pressure is weakened, right? Mascarene high pressure is weakened. So that is why low rainfall over India. Low rains over India. In the case of La Nina, masculine high pressure is strengthened. Masculine high becomes stronger. Now, as the masculine high pressure is stronger, more winds over to India. More rains and more winds. Okay? For India. So that is the phenomena of monsoon. Now, eventually, with the withdrawal of the ITCZ, the ITCZ starts retreating. As the ITCZ starts to retreat, then basically the wind system set in. As the ITCZ, let's suppose, comes over here, so the wind system set in like this. The withdrawal of the ITCZ post 17th of September. 17th of September. So after 17th of September, you have the withdrawal of the ITC. That is also what is referred to as the retreat of the monsoon. Of monsoon. What is this mascarene? You have mascarene islands present in the southern Indian Ocean. That is the region of the high pressure which is created, which becomes the supplier of the winds. So that is the high pressure which is very important for the strength of the trade winds. If the mascarene high pressure is not strong, you don't have enough trade winds. So less rainfall is caused in India. The mascarene high pressure is very strong, more trade wind. What causes the burst of monsoon? So the sudden disappearance of the southern branch of the jet stream causes intense convection both at mid and the low altitude, due to which very thick and intense cumulonimbus clouds are created, which causes rainfall continuous for 3 to 4 days, what is regarded as the burst of monsoon. Can equator consider revolution? What? Which revolution? How does it affect the trade wind? Basically the shifting of the ITCZ. If the ITCZ moves north, the trade winds they move further, they are dragged to the north. If the ITCZ moves south, the trade winds are dragged to the south. Okay. Now, then comes the portion of the withdrawal of the ITCZ. As the withdrawal of the ITCZ tends to happen, so as a consequence of that, you basically have the retreat of wind system becomes winds become in the direction northeast to southwest. They will cause rains post 17th of September, rains in the region of Coromandel coastline. Coromandel. Okay, that is the case of retreat of monsoon. How does La Nina weaken the effect of western disturbance over North India? Sudarshan. See, when you have the condition of La Nina during those particular cases, in the case of the Indian Ocean, you have the high pressure which gets created in the central and southern Indian Ocean. This also generates a wind pattern. If I can use this, a wind pattern somewhat like this. Now, when this wind pattern is generated, that works antithetical to the condition of the western disturbance. That is why the western disturbances will not cause lot of rainfall. However, the winters become harsher in the case of central and southern India. So that is the difference. Okay. But UPSC will never ask that in the GS portion. In GS paper, it will never ask that. Right? Tropical easterly jet is something that we have already taken a look into. It generates from here, moves like this, sinks in the region of the mascarene high, and then you have the surface. There is also a role of another jet stream. So in total, for the monsoon, you have three jet streams which are involved. Three jet streams are involved. Which are those? You have the subtropical westerly jet stream, subtropical westerly jet. Then after that, you have the tropical easterly jet. Then which is the other jet stream? Final one is basically the Somali jet. Somali jet, right? Somali jet is a low altitude jet stream which moves from the region of Horn of Africa towards Arabian Sea. It drags moisture towards the region of the Arabian coastline, and that is why it brings more. So both of these, if they are strong, increase rainfall in India, rains in India. Whereas subtropical westerly jet is important for the onset of monsoon, right? I hope that is. Now, this is the annual rainfall pattern in India. The amount of rainfall reduces as you move from south to north and as you move from east to west. The region which receives the monsoonal rains, if last, is the region of northwestern India. And that is the region where the monsoon withdrawal happens the earliest. So that is the case of the rainfall. As you move away from the source of moisture, the amount of rainfall reduces. Then you have the condition of the western disturbance. Western disturbances, Mitali, we won't go into the details of the impact of Lewin current, not required for your GS. This is basically Lewin current when it brings water from the region of the Pacific. So basically, when you have the presence of the Lewin current, it carries on the effect of Enso circulation beyond the immediate months, carries on the Enso circulation's impact over the next year as well. Not relevant for your GS. This up to the level of optional. We will leave it in. Now, the Western disturbances. So basically, westerly jet is the western disturbance. No, 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 no. Westerly jet is very different from western disturbance. Understand the western disturbances first. So in the region of the Mediterranean Sea, during the winter months, the water is comparatively warmer and the air or the land over Europe is very cold. So there is a front development of frontogenesis, which that frontogenesis oftentimes leads to a low pressure circulation or disturbance, and that low pressure disturbance or circulation then travels eastwards under the influence of westerlies as well as the jet stream. Both of them play their role. So, as they move to the west, during the months of November, right up till almost April, they will have multiple such occurrences of these low pressure systems which move over to the east. They come from west to the east, bringing that low pressure system along with the clouds. Now, as they hit the region of the Himalayas, they cause snowfall in the region of Jammu Kashmir, Himachal Pradesh, Uttarakhand, exaggerating the cold waves in India, and rainfall in Punjab, Haryana, Delhi, northern Rajasthan, Uttar Pradesh, Bihar, sometimes all the way till Assam plains. Okay, so this is the case of western disturbance, which is created over the region of Mediterranean Sea. Now, this is carried by westerlies, becomes a part of the westerlies, in fact, and subtropical westerly jet. Okay, that is how it is carried. And locally, this western disturbance is known as Mahawat. It causes the winter rainfalls, which are very important for the sowing of the Rabi crops. That is, the crops such as wheat, they get benefited out of the rains which are received in western disturbances. Let us take a look at this particular question. Consider the following statements about the phenomena of El Nino and its effect on Indian monsoon. So, El Nino. It occurs in the region of South Pacific and hence has no impact on Indian monsoon. It leads to increased rainfall over Indian subcontinent during the monsoon season. Only one option fulfills that. Its impact can be neutralized by Indian Ocean dipole and the Madden-Julian oscillation. Okay? The correct answer in this case is going to be basically C. Right? Now, which of the following correctly describe the phenomena of western disturbance? These are aggravated monsoon winds blowing from west to east, They originate over the region of the Mediterranean Sea and are carried to India by winds. Their effect can be felt mostly during the months of July to September. They can bring rains over the hilly tracts of Himachal Pradesh, only over the hilly tracts of Himachal. So they originate over the Mediterranean and are carried over to India by the. Now, when it comes to climatic classification, the world climate, we have already done a video on that. I urge all of you to take a look at that particular video in it, right? The climatic classification, the various Köppen classification, that is something that we have taken a look into. Ocean currents is something, and Indian geography is something that we will cover next. Before that, we take a break. We take a break for half an hour, and after that, we come back. Okay? I hope that is fine. After that, we have to, in Indian geography, we will cover the some map portion of Indian physiography, the portion of Indian river systems, rivers and tributaries, the listing I will give to you, the case of forest and soil, basic idea about the type of forest classification along with the map, and then the case of the agriculture mineral distribution. Okay. How long will the class go? As long as it takes to finish all the topics. Till then, the class will go. Okay. I want this session to be so comprehensive enough that after this, after attending this session, I know you will be exhausted. I know it will take a toll. But after that, you should not have any other area which remains untouched. When it comes to physical geography, when it comes to Indian geography, the portion relevant for that, you should be able to have a minimum bit of confidence associated. Okay. So that is where, regardless of the time taken, if it takes up till 12, I'm ready to be here up till 12. If it takes up till 1, I will continue up till 1 p.m., 1 a.m. as well. Okay. So don't worry regarding that. Places and news regarding India. So, see, basically, when we talk about the protected areas, etc., and those compilations, that would suffice. If required, I will come up with a fresh video. Okay. So let's take a break, and we'll take a break for 30 minutes. And it is 10 of 12. So we will resume at again 10. Okay, so I hope I'm audible and visible and the video is clear. So, till now, we have basically covered the entirety of the portion of geomorphology, the entirety of the portion of climatology, including the portion of Indian geography when it comes to Indian climate. That is the Indian monsoon, the factors influencing the Indian monsoon, the concept associated with Western disturbances. That is something that we have already covered. Now, in this final run, we are going to cover the portion of ocean currents and associated with the Indian geography, Indian physiography, forest and soil, rivers and tributaries, as well as the agriculture and the mineral resource. Now, most of those portions in the portion of Indian geography, that is something that you can revise with the help of the PDFs itself. And there you will have the details which are included in the PDF also. So that PDF will be uploaded on the Telegram channel tomorrow. So you can take a look at that and you can further aid the revision process. Now, again, for all of you who are basically anxious regarding the initial portions of the video which is not available, which is not appearing to be available right now. So please don't worry about it. That is because of the restarting of the stream in between, due to which you are unable to see that right now. Once the entire session is completed, then if you take a look at and the session is ended, after that you will get an access to the entire video altogether. Okay, so please don't worry about it. You will get all the videos associated. Okay, the entirety of it. Now, coming to the portion of ocean currents. Now, for your examination in the terms of ocean currents, what is important for the exams? So, first of all, here you need to understand the ocean currents, the property of them, whether they are warm currents or cold currents. From here, a prelims based question can always be warm currents or cold currents. And secondly, the ocean currents, the names can be given, and you have to also end up, or the question can be asked that this ocean current is to be found in which of the oceans, right? So, the concerned ocean, in which ocean you will find the ocean currents. So, that is the one which is relevant for your prelims preparation. Now, when we talk about ocean currents, what are these? These are basically a kind of, in a way, regularized movement of water in the oceans in a fixed or a set direction, in a fixed or set movement or a pattern. That is what is referred to as an ocean current. Now, the oceanic water tends to move from one region to another continuously. And there are multiple factors which aid the movement of oceanic water. The influence is substantial when you consider the ocean currents. They also have the influence over the region of the local climate or the microclimate of a particular area. So, here, when we talk about the factors which influence the ocean currents, you basically have some of the factors associated which are listed here. So, one of the most important factor is basically the heating by the sun. Now, in the lower latitude, the water is heated excessively by the solar rays, the solar insolation. The high amount of solar insolation in the lower latitude increases the temperature of water in the lower latitude. Now, as the temperature tends to increase, almost immediately, that leads to a slight expansion in the water. The volume of water tends to expand, right? So, if you consider the oceans, in the lower latitude, you have a slight expansion of, right? It has got a slight amount of expansion. Then after that, now this expansion basically means a height difference of around 8 to 10 centimeters as compared to the higher altitude or the higher latitude regions or the polar regions. Their water tends to have a height gradient of 8 to 10 centimeter. Now, the water, because it has got a greater amount of height, it will always tend to flow towards the direction where the height is less. So the natural tendency of water will be to flow from lower latitude to higher latitude. Having said that, after that comes the role of the winds. The winds provide direction and also the kind of motion which is associated. Okay. So the winds are always associated with the kind of direction required. So, for example, let's suppose when you consider the wind movement in the lower latitude, so you have the presence of the trade winds, then in the mid latitude, the westerlies, then in the higher latitude, the presence of polar easterlies. So, all of this has got an influence in terms of the direction that the ocean water tends to take. So that is why the winds also end up providing a kind of a distinct direction of. That is also something which becomes important. So here, heating by the sun provides the height gradient, provides a height gradient, okay, which will initiate the flow. Initiate the flow. After that, you basically have the role of the winds. And when we talk about the winds, you basically have the role of the permanent wind systems. Permanent wind. Now, these permanent winds, they provide the direction of. Okay. And then after that, you basically have the role played by Coriolis force, for example. So when you talk about Coriolis force, now in the northern hemisphere, it will have a bend to the rightward direction. In the southern hemisphere, it will have a bend to the left direction. So that basically means in the northern hemisphere, if the ocean current is moving like this, it will always bend to the right, keep on bending to the right. So that is why in the northern hemisphere, the circulation of the oceans is always in a clockwise manner. Please don't compare it with the cyclonic circulation. Then you will get confused. This is a different circulation of the ocean. Cyclonic circulation is independent, so the clockwise, anti-clockwise in cyclonic circulation is different, and the clockwise, anti-clockwise in the southern hemisphere or in the oceanic circulation, that is different. Okay? So in the northern hemisphere, the circulation is clockwise. Okay? Whereas when we talk about the southern hemisphere, in the southern hemisphere, the circulation is reverse. So basically, the circulation basically reverse. The oceanic water, basically, you will observe it bends to the left. So that is where in the southern hemisphere, the circulation is anti-clockwise. Mind you, there is an exception to it. What is the exception? Is the northern Indian Ocean. Northern Indian Ocean is the exception where you have seasonal change in the direction of the ocean currents owing to the factor or the involvement of the winds. Right? So, here circulation is anti-clockwise. Okay. Now, basically, this is the case of the circulation induced because of the Coriolis force. So, this is the case except Northern Indian Ocean. Northern Indian Ocean. Okay. Then you have the role of the shape of the coastline. Shape of the coastline also directs these oceanic circulation or the oceanic water in a particular direction, right? So based upon if let's suppose you have protrusion in the coastline or if the coastline has got a lot of indentions, the oceanic current is also impacted because. And then you have the bottom relief feature. When I talk about bottom relief features, I'm talking about the mid-oceanic ridges, etc. So, example, the case of the ocean currents in the northern Atlantic, they get impacted because of the part of the mid Atlantic ridge, which is known as the Wyville Thompson Ridge. So, there they get trifurcated in general, right? So, that is where you will find the impact created by these particular factors in the oceanic circulation and in the case of ocean currents. Now let us take a look at these ocean currents and let us try to understand how do they move and which are the ocean currents basically which are important. So we will understand the property in the case of and revise the property in the case of the Atlantic Ocean. That is something which will be replicated almost entirely in the case of the Pacific Ocean. However, in the case of Northern Indian Ocean, that changes ever so slightly. So understand this step by step. So you see, the water around the region of equator ends up gaining a kind of a height gradient. Now, after that, under the influence of the trade winds, they will carry the water from east to west. So that is where the trade winds, they basically carry the water from east to west. You have the north equatorial current in the northern Atlantic, south equatorial current, which is present in the southern Atlantic. Now, all that water will end up accumulating across the western Atlantic. Now, shape of the coastline in itself directs the water in a way, bifurcates some of the water to the north and some to the south. But there is some amount of accumulated water which is still left in the region of western Atlantic. Aided by the rotation of planet Earth from west to east, that accumulated water tends to have a flow back. And that is what you have in the form of counter equatorial current. So that is what you have as the counter equatorial current. Now, this north equatorial current, basically, as it moves over, it comes across the Caribbean islands. Now, there it gets split. You have the Caribbean current, the Antilles current around the Antilles island. So it splits up. One portion enters through the Yucatan Peninsula. This is your Yucatan Peninsula, right? In the map pointing in the places in news, we have covered that ample number of times. So basically, you have the Yucatan Peninsula. So there, the water tends to enter into the Gulf of Mexico through the region of the Yucatan Peninsula. After that, as it moves through the region of Gulf of Mexico, it emerges from the region of Florida as Florida current. There it meets the Antilles current, which was coming from the northern portion of these Caribbean islands. And together, they combine the water to form the strongest warm water current, amongst the strongest warm water current witnessed anywhere across the planet, that is in the form of Gulf Stream. Gulf Stream carries large volume of water with a very high speed. That is why the name stream is associated here. Now, meanwhile, aided by the polar easterlies and the winds coming from the region of the higher latitudes, you have from the region of Labrador Sea a cold current which comes in. And that is known as Labrador current. Now, the Gulf Stream water and the Labrador current that meets in the region around Newfoundland, and that ends up creating ideal fishing ground, mixing of warm and cold water, warm and cold water. That ends up creating a condition of ideal fishing grounds. Okay. Now, after this, the Gulf Stream, which is still very warm, that is aided and its movement is aided by the westerlies. So it basically tends to move from west to east and is known as the North Atlantic Drift. It is here that it encounters the Wyville Thompson Ridge underwater as well, and also aided by the shape of the coastline, it gets almost trifurcated. The Norwegian current, you have the Irminger, Rennell, all these different types of bifurcations and trifurcations happen to the North Atlantic Drift at this region. North Atlantic Drift is a warm water current. It is not as if it is very, very hot. It is not as if North Atlantic Drift will have a temperature of, let's suppose, 30, 35 degrees. No. Even if the temperature is 15, 16 degrees Celsius, it is much warmer as compared to what you expect at these latitudes. That is why it is warm current. Now, this Atlantic Drift, North Atlantic Drift, and the Norwegian current, they keep the regions of the North Sea, etc., ice free for most parts of the year, aiding in trade and navigation as well. In the meanwhile, there is the bending due to the Coriolis effect, due to which the ocean current again bends to the right. Now, after this, if you observe, water is coming from higher latitude to the lower latitude. So even if the water temperature, let's suppose, is 15 degrees Celsius, it is much colder if you compare the temperature of the tropical water. Tropical water on an average will have a temperature of 24, 25 degrees Celsius. So that is where the same current which moves, that is known as the cold Canary current, as it moves across the region of Canary Islands. So that is basically where you have the cold Canary current, and it completes the entire cycle. Now, in this entire cycle, you will observe that the central portion of it, which lies in the region of the subtropical high pressure zone as well, the central portion of it remains undisturbed. There is not much motion there. So that undisturbed area has got a growth of large amount of seaweeds in general. And that is what is also referred to as the sargasso, because the seaweeds in Portuguese, they come out to be sargassum. They are referred to as sargassum. And from there, the terminology has been derived, sargasso. So there, it is a nightmare for navigation activities. You have a lot of these seaweeds getting trapped in the hulls of the ships, vessels, leading to shipwrecks and disasters. So this is the ocean current in the North Atlantic Ocean, right? Starting from the North Equatorial Current, then aided by the shape of the coastline, moving on to the Caribbean Current and Antilles Current, enters into the region of Gulf of Mexico, emerges, the water is combined to form the Gulf Stream. You have cold water coming from the Labrador Sea, the Labrador Current, creating ideal fishing grounds. Then after that, the westerlies carry it over to the region of Europe, the form of North Atlantic Drift. It bends again to the right and brings water to the region of the lower latitude, and that is the cold Canary Current. Okay, now then you have the South Equatorial Current. Now, in the case of the South Equatorial Current, you will observe that again, this time it will bend to the left owing to the Coriolis effect and owing to the shape of the coastline. That is when it forms the warm Brazil current. You will find that it will form the warm Brazil current. Meanwhile, across the entirety of the stretch of the Southern Ocean, aided by the westerlies, you have the west wind drift, which is continuously moving from a direction of west to east. Now, from that west wind drift, there is a leftward deviation around the Falkland Islands, and that is what forms the cold Falkland current. Now, this Brazil current is subsumed into the west wind drift, and this west wind drift then again bends to the left owing to the Coriolis effect, and you have the cold Venezuela current. So that is the case of the entire circulation in the case of Atlantic Ocean. Now, the same template will be applicable even in the case of the Pacific Ocean. When you talk about the Pacific Ocean, so here again, basically, the trade winds in general, you will observe that these trade winds, they will carry the water from east to west in the form of North Equatorial Current as well as in the form of South Equatorial Current. There again, some amount of excess water accumulated in the region of Western Pacific flow back in the form of counter equatorial current, which will be V. Now, this North Equatorial Current moves over, bending due to the shape of the coastline and also aided by the Coriolis effect. Now, it moves across the region of Japan and Korea across the Tsushima Strait, and that is what forms the Tsushima current and a stronger Kuroshio current. Now, this Kuroshio current is very similar to that of the Gulf Stream. even though it is not as powerful as the Gulf Stream. But Kuroshio current also represents a similar phenomena. Just like in the case of Atlantic, Gulf Stream met with the Labrador Sea and the Labrador Current, here Kuroshio meets with the cold current, that is Oyashio. Here again, ideal fishing grounds are created, right? Fishing grounds are created, ideal for fishing activities are to be observed. Now, then the westerlies, they will carry this particular warm water current in the west to east direction. As they carry the warm water current from the west to east direction, then eventually they hit the coastline of America and there they get bifurcated. This water goes to the higher latitude where it appears as the warm current, and the same water goes to the lower latitudes. Lower latitudes, the temperature generally is much higher, so the same water will be termed as the cold California current. In the southern Pacific, you will observe basically that the South Equatorial Current, one part of it enters into the region of Indian Ocean to the north of Australia. It enters into the region of Indian Ocean under the name of New Wind Current. New Wind Current. Okay. Now here you will observe that this South Equatorial Current then bends to its left on the region of eastern part of Australia, and that is what is referred to as the East Australian Current. Right? After that, it merges with the west wind drift, which continuously moves from west to east direction. This west wind drift, under the influence of the shape of the coastline of South America and the Coriolis force, then will move leftwards and rather northwards in this case to form the Humboldt current, what is also regarded as the cold Peru current. So this ends up creating an entire circulation in the region of the Pacific Ocean. But however, when we talk about the Indian Ocean, in the case of the Indian Ocean, the situation is different. Why? Because if you compare it from the region of the Atlantic or if you compare it to the region of the Pacific, the northern Indian Ocean is blocked by landmass. It is always blocked by landmass. So that is where the influence of the winds in this region becomes much more effective in influencing the direction that the ocean currents they tend to take. Now here you will observe that you have different months. In the month of June, July, August, right? That is June, August. You will observe basically that the winds are southwest, northeast. This is the direction of the winds in general during the month of the advancing monsoon, right? So that is why the water basically is something which moves in a clockwise manner in the northern Indian. It moves in a clockwise manner. So that is the southwest monsoon current in the northern Indian. But in the month of September to December, January, you will observe that the wind direction reverts northeast to southwest. So accordingly, observe the flow also tends to revert. It becomes now almost anti-clockwise. That is where the counter equatorial current also tends to develop. Right. Now, that is the case of the northern Indian Ocean. However, having said that, in the southern Indian Ocean, you will observe that you have the same phenomena of South Equatorial Current. Here you have the Mozambique and the Agulhas Current. There you had in the Atlantic Brazil Current, in the case of Pacific East Australian, right? Then the west wind drift carries the water from a generic direction of west to east, and then aided by the Coriolis force and the coastline of Australia, you have the cold Australia current, which is also the West Australia current, right? Now, in this particular case, one has also got to focus about the impact of the ocean current. After that, we will take up this question: impact of ocean current. Now, those of you talking about the marathon session of environment ecology, please understand that we have already covered that in our various phases of Conquer Prelims. We have done the marathon session for environment ecology in various different phases. Take a look at the Telegram channel. You'll find the link of all those previous videos as well. So we have had many videos regarding the cases of environment from Ramsar sites to the protected areas, the case of conventions and protocols, to the case of the compilation of current affairs, more than sufficient species in news, areas in news. All of that has been covered continuously. So take a look at that, will be more than sufficient. Okay. Now, impact of ocean currents. So when we take a look at the ocean currents, so here basically you have multiple roles. First of all, navigation. It helps in navigation, right? Now, it will also form ideal fishing ground wherever you have the mixing of the warm and the cold current. You have the formation of ideal fishing grounds, right? Then, other than that, in the region where the warm and the cold ocean current meet, there is fog formation, sea fog. Then, these ocean currents help distribute the heat. Heat and salt balance across the planet is maintained by the movement of the ocean currents. Heat and salt budget of the ocean, salt budget of the ocean is maintained. Then, other than that, you also have the case where when we talk about these ocean currents, they also help in replenishing the nutrients from one region to another, which helps in the survivability of multiple species, right? So, nutrient cycle or nutrient circulation. Then, after that, the impact on climate is manifold. So, it can lead to causation and occurrence of rainfall as well. Okay. Causation of rainfall it can lead to. At the same time, in the region where you have cold ocean currents, in those areas, it will lead to the formation of deserts. Okay. Wherever you have cold ocean currents, in those areas, it will lead to formation of deserts in most of the areas. Deserts in nearby land. Example, Atacama Desert, Mojave Desert, Victorian Desert, Namib Desert, some parts of Sahara Desert, all of them come under this. Okay, so that is basically the case of the ocean currents. Right? Now, let us take a look at this particular question. Which of these represent the warm ocean currents? Out of all of these, which are warm ocean currents? This should be simple. This kind of a question is to be expected in the examination. Right? So Gulf Stream is a warm ocean current. Canary Current, cold ocean current, the region of Atlantic. Kuroshio, again a warm ocean current. California, again a cold. The correct answer in this case is going to be A, 1 and 2. Okay. Now, after this, we come to the portion of Indian geography. Now that the entirety of physical geography is done, and also the portion of in Indian geography, Indian climate is done, some of the remaining portions of Indian geography, very quickly, we will browse upon this with respect to the maps and with respect to some of the detailings required for the examination. Now, physiographical division of India, that is important for your examination, but what is also important for you to know for your mapping purposes? Which are the particular states through which Tropic of Cancer passes through? Which are the particular states through which you have the uh, standard meridian, the Indian Standard Time, which is kept with regards to the standard meridian? Which are the states which lie on the standard meridian? So, first of all, talking about the Tropic of Cancer, which are the states through which Tropic of Cancer passes through? From west to east, if you have to talk about, starting from Gujarat. Then after that, Rajasthan. Then after that, Madhya Pradesh. Then after that, Chhattisgarh. Then after that, Jharkhand. Right? Then after that, West Bengal. Then after that, that's it. Now, you also have Tripura, and then you also have Mizoram. Okay? So these are basically the states through which Tropic of Cancer does pass through. This is something for which you should have an idea. Okay? Please don't ignore. Many of the times when we think about Tropic of Cancer, we miss out on the states like Rajasthan and Mizoram. So these are one of the tricky areas. Then we come to the standard meridian. When we talk about the standard meridian that it passes through which particular state, so standard meridian overall, if you will observe, so it passes through the states of Uttar Pradesh, right? Then Madhya Pradesh, it touches the region of Madhya Pradesh, Chhattisgarh, then Odisha, right? And after that, Andhra Pradesh. So there are two such states where both standard meridian as well as the Tropic of Cancer passes through. There are two such states. Which are those two states? Basically, Madhya Pradesh and Chhattisgarh. Madhya Pradesh and Chhattisgarh are the two states to which both standard meridian and the Tropic of Cancer passes. Please don't end up rectifying this. Anybody who is forming the analogy and the mnemonics for rectifying this, you will only end up preparing for that kind of question only. But UPSC is not going to ask you same simple question. Okay. So please keep that in mind. So two such states where both of them are there. Tropic of Cancer as well as the standard meridian. Madhya Pradesh, Chhattisgarh. One state where the Tropic of Cancer crisscrosses with the standard meridian. And that state is the state of Chhattisgarh. Okay? The state of Chhattisgarh is where the standard meridian and the Tropic of Cancer passes through. Okay? Now, after this, basically, regarding the neighborhood that we have, now we share our border with various different countries, both land and the sea borders as well. Now, many of us have the misconfusion and the misconception that when we talk about international border, it only includes this area. But that is not true. International border also includes the portion of the water boundary. Water boundary is also your international. Please keep that in mind. Okay, that is also a part of the international border, right? Now, the longest border that we share with a country, that is with Bangladesh. With Bangladesh, we share the largest border. And the shortest border we share with the country, that is Afghanistan. With Afghanistan, we share the shortest border. Okay? So here, Afghanistan shares its border with the region of Jammu and Kashmir through this narrow panhandle shaped land, and that is the Wakhan corridor. Wakhan corridor has always been important, even historically, for the movement of trade, people, traders, everyone. So that is why Wakhan corridor has been used for multiple years and multiple centuries now. So that is our shortest border. It is through this Wakhan corridor that China is seeking to expand its infrastructure in order to be able to reach the region of Arabian Sea, bypassing the Karakoram Pass, which lies in the region of Jammu Kashmir. So that is why China is seeking an alternate route into the region through the Wakhan corridor into Arabian. So that is the case of Afghanistan. Okay. Now, physiography of India. Overall, when you talk about India in general, you have various physiographic divisions. Different physiographic divisions are there, starting with the northern and northeastern mountains, right? So these are the dominating structures across the region of northern India and eastern part of India as well. Then you have the northern plains, the very fertile northern plains which are present. Then you have the Thar Desert, the Peninsula Plateau. Then you have the coastal plains, and then you have the island. These are your major physiographic division. One by one, if we take a look into it, Himalayas are the most massive and the mightiest of these physiographic features that we have. Now, Himalayas, they serve as a natural frontier for us. And Himalayas, they provide us with water, they influence our climatic condition, and they also serve as a deterrent against the enemies. Now, you see, Himalayas were created as a consequence of continental convergence. Earlier, before India collided with the Eurasian landmass, you had the presence of Tethys Sea in that particular region. Now that Tethys Sea got compressed, the sea floor got uplifted, and then you had a complete continental convergence between the Indian and the Eurasian plate, leading to the formation of the Himalayan. So that is how you have the formation and the presence of the Himalaya. Okay. Now, in this particular case, when we talk about the region of the Himalayas, the Himalayan ranges include what? Three parallel ranges moving from east to west. So you have Himadri or the Great Himalayas, the northernmost, the tallest one. Then you have the Himachal, the middle Himalayas, and then you have the outer Himalayas in the form of Shivaliks. Shivaliks have been formed, the latest and mostly continuous, barring certain areas in Uttarakhand and the region around Sikkim. These are mostly parallel to each other. Their extent from east to west is almost for a distance of 2,500 kilometers. Now, these Himalayas, if you will observe, now they have a kind of a bend in the axis of the Himalaya. And then here. These are what are referred to as syntaxial bends. Syntaxial bend. Now, in the case of Himalayas, you basically have the presence of two syntaxial bends. One which is present in the western part. So the syntaxial bend which is present in the west is which peak? It is Nanga Parbat. Nanga Parbat is the syntaxial bend. And in the east, you basically have Namcha Barwa. Namcha Barwa. So these are your syntaxial bend. To the north of Himalayas, you also have mountain ranges, but they are not very continuous. They are not as continuous as you observe in the case of Himalaya. So they are not considered to be a part of the Himalayan mountain range. So here you have the Karakoram, the Ladakh, Kafkar, and the Kailash range. These are also what are referred to as the Trans Himalayas. So when we talk about the Trans Himalayas, trans means beyond. So here, Trans Himalayas, that is beyond the reaches of the Himalayas, you basically have the case of Karakoram range. Then you have the Ladakh range. Then you have basically got the presence of Kaskar range and also the Kailash range. These are the part of Trans Himalaya. Now, these Himalayan ranges, they are named differently in different areas. For example, in the northeastern states, they are named after the tribes. In the region of, for example, if you consider Himachal Pradesh, the middle Himalayas are named differently. You have the Dhauladhar ranges as they are referred to. Then when you consider the region of Shivaliks in the region of Jammu, they are known as the Jammu Hills. So they are named differently in different regions as well. Okay, but they are a part of the larger Himalayan. Now, in the region of the Kashmir Valley, you basically have the formation of very fertile deposits, which have been created as a consequence of a large ancient lake which was created with Pir Panjal range on one side and Zaskar and Himadri on the other side. So you had the flow of the rivers which would happen from the Trans Himalayas and the Great Himalayas, and that would be blocked by the Pir Panjal range. As a consequence, water kept on accumulating in that region for a long period of time. Water accumulated and formed a very large lake, creating deposits, very fine deposits underneath it as well. So that is where basically you also have the creation of what are known as lacustrine deposits. Lacustrine deposit. The name lacustrine deposit is referred to the term or refers to the term where you have the deposits created in a large lake-like body. Slowly and steadily, the water level kept on increasing, and the water eventually exited from the Baramulla Gorge to the south. Baramulla Gorge south is from where the water managed to exit. And that is when the leftover portion of these lacustrine deposits, they were known as karevas. They are very, very fertile. Okay? Very fertile. Okay? And these karevas, they are used for cultivation, orchard farming, general agricultural practices in the region, and at the same time, growing one of the most costliest spices in the region, that is the saffron. Saffron is grown along with cotton, along with the orchard farming and other fruits in this area. So, saffron cultivation does happen. Then you have even the case of orchard farming. Okay, that tends to happen in the region of Karevas. Occupies a very large extent of the Kashmir Valley. Then, in the case of the middle and the lesser Himalayas, right? So, basically, when you consider the region of Himachal and Shivalik, in between the region of Himachal and Shivalik, as the Himachal was created, the Himachal ranges was created roughly around 35 to 40 million years ago. Now, rivers and the streams started to originate and move from the region of these hills and the mountains. After some time, you basically had an upliftment further ahead in the form of Shivaliks. Now, in certain areas, this managed to block the water flow. And the water was not only blocked, eventually, it had lot of deposits created in the. As the water level increased, the water exited from the sides of these valleys, leaving behind the deposit. These fertile deposits which have been left behind, they are known as dunes and duars. So it is the same landform known as dunes where in the region of Western Himalaya. Dehradun, Kotli Dun, Patli Dun, all of these are examples of dune in the region of Western Himalaya. And then you also have what are known as duars. Duars are the same landform created in the region of Eastern Himalaya. Okay, so these are the kind of the landforms that you will observe, be present. Okay, now, uh, so that is the landform that you will find to be associated with the Himalayas. One of the other landforms that you find, particularly in the region of Punjab and Himachal Himalayas, is the presence of what is referred to as chos. So here, this is generally to be found in the region of Punjab and Himachal Himalayas. And that too in the southern slope. Now you see, in the Himalayas, in the entirety of the region of the Himalayas in general, you will find the physiographic feature is such that you will have a steep southern slope and a gentle northern slope, which is to be found. This is also what is referred to as the hogback topography. Hogback topography. That is the general feature of the Himalayas. Okay, that is known as the hogback topography. Now, in the steep southern slope, particularly in the region of Punjab and Himachal Himalayas, if you consider the face of the southern slope, during the rainy season, you have multiple seasonal streams which originate and drain from this area. And they carve out almost indentions and depressions in the region. And these make the region unfit for agricultural practices, etc. So these such seasonal streams creating a lot of erosion, that is what is referred to as chores. So here, seasonal streams, seasonal streams creating erosional structures, erosional gullies in a way you can say. Okay, where in the southern slope of Punjab and Himachal Himalaya. Okay, now then the regional classification of Himalaya. As you move from west to east, Himalayas are classified into various different types. So basically, you have the case of Kashmir or northwestern Himalayas. Now, in the Kashmir Himalayas, you will have the presence not only of the three ranges of Himalayas, that is the Himachal, Himadri, and Shivalik, but at the same time, you also have the presence of the Trans Himalayas. So that is also present in the case of the Kashmir Himalaya, right? So both or the three ranges along with Trans Himalaya. That is something that you will find there. Then after that, when you consider the Himachal and the Uttarakhand Himalayas. Now in the Himachal and Uttarakhand Himalayas, you will find the presence of grasslands, dunes, duars you will find in this area. You will also find presence of lot of beautiful hill stations, valleys, and you will also find the presence of the seasonal grasses in the region. Lot of seasonal grasslands, summer grassland, right? Ravines you will find on the slightly plain areas. Okay, Sudarshan. So here, seasonal summer grasslands at greater altitude, summer grasslands, and these are known as bugyals. Beautiful. Now, bugyals and such seasonal grassland, they are used by the pastoralists and the nomadic population to, in a way, take their animals for pastures and feed them with the grasses during the summer season. During the winter, they come down the slope. That is a phenomena of nomadism, what is also referred to as transhumanes. Trans, okay, that is your pastoral nomadism. Okay, then Arunachal Himalayas. In this region, you basically will find that the hills are named after the tribal population that is there in this region. So here you will find the presence of the Shivaliks. The Shivaliks are named differently as Dafla, Miri, Mishmi, and Abor. Okay, named after the local tribes. Then after that, you have the Eastern Hills. So in the region of the Eastern Hills, you basically have Bareil and Mikir ranges. Okay, so this is basically how you can classify the Himalayan region in the region from west to east, from one area to another. Okay. Now, northern plains. In the case of northern plains, also there is a classification. There's a regional classification starting from the Punjab region, that is the Trans Ganga plains. Then you have the upper Ganga plains, middle Ganga plains, lower Ganga plains, and so on. So that is the regional classification in the northern plains. You have in the region of Rajasthan, the alluvial deposits, they are also known by the name of Rajasthan Bagar. So, like that, you have the classification there also. But northern plains, they are also further subclassified as you move from the foothills of the mountains into the river valleys and the flood plains. They are also classified differently. For example, immediately at the foothills of the mountains, you will find larger boulders and rock pieces which are dumped by the rivers. In fact, the river ends up moving underneath them. So it appears as if the river has disappeared from the region. So that is what is also referred to as the Bhabar Tract. That is the Bhabar Tract. It is unfit for cultivational practices. A random one or odd trees you will find here and there, but unfit for cultivational practices in. Now, immediately as it emerges from the region of the Bhabar Tract, it doesn't have any defined channel of flow. It tends to flow anywhere and everywhere. So that is where you will find the presence of marshy lands, and those marshy lands, these are known as tarai. Okay, very rich in terms of biodiversity. Very rich in biodiversity because moisture is abundant, so vegetation will be abundant, so automatically you will have lot of biodiversity. For example, if you consider the region of the Tarai and the elephant reserve, one of the large elephant reserves which have been established, the Tarai belt, then Corbett, some part of it is in the Tarai belt, Rajaji Tiger Reserve, some part of it is in the Tarai belt, Dudhwa Tiger Reserve, some part of it is in the Tarai belt, Buksa Tiger Reserve, some part of it is in the Tarai Belt. So, in this entire region, typically and historically, you had the presence of tiger population, one horned rhino population, and also elephant population. Right, due to excessive deforestation during the time of British India, that is where the biodiversity in the region has experienced or suffered a massive decline. Then you have the plain areas. Now, in the case of the plain areas, the river moves through fixed river channels. Now, there, the river carries out fresh deposits and older deposits as well. The deposits, the fresh deposits which have been created by the river almost on a monthly, annual basis, those are known as khadar. But the river would have deposited something which is much older, which has been created much earlier, and those are known as bangar. It is in this bangar where you will have coarse grains, right? And calcareous concretions, which are known as conquers. Calcareous concretions. These are known as conquers. Now, obviously, Khadar is much more fertile as compared to Bangar, right? So, in Khadar, you can grow almost all type of crops, whereas in the case of Bangar, pulses, maize, these kind of crops are typically to be. Now, again, important for the portion of your mapping is the case of the Peninsular Plateau. In Peninsular Plateau, basically, if you will observe that you have multiple different small plateau regions, hill regions, etc. Now, here, the locational aspect is important. Peninsular Plateau is a flat, almost a kind of a featureless table land like structure dotted with hills and ranges in between. So, when you talk about the Peninsular Plateau, very old structure. Definitely the oldest structure in India, possibly one of the oldest structures across the world. Now, it is dominated by multiple small plateaus as well. So, when you talk about the Peninsular Plateau, starting from the region of the Meghalaya Highlands, right? That is the Shillong Karbi Anglong region. Here you have the Garo, Khasi, and the Jayantia Hills. Then, after that, you have the Hazaribagh Plateau, particularly around the region of Rajmahal Hills. Here you have Rajmahal Hills. Rajmahal Hills. It is beyond the Rajmahal Hills that River Ganga takes a southern turn. That is why this portion, this gap between Rajmahal and Garo, this is also what is referred to as the Malda Gap or the Rajmahal Garo Gap. Here, the land has undergone subsidence over the history. Malda Gap or Rajmahal Garo Gap. Garo Gap. Okay? Then you will observe in this region the presence of Chota Nagpur Plateau. Chota Nagpur Plateau, one of the older plateaus which are there, one of the most oldest of the plateaus which are there in any part of the country. The Chota Nagpur Plateau, along with the Bastar Plateau, they form the older portions of the plateau area. Now, beyond the Chota Nagpur Plateau, you find the presence of the Garjat Hills. Again, a very old hill structure which is created at the boundary zone between the Chota Nagpur Plateau and the region of the Bastar Plateau. Garjat Hills, they lie in the region around Odisha, some part of Chhattisgarh, but mostly in the region of Odisha. Then you have the Kaimur Hills in this. Kaimur Hills extends, it is like an offshoot of the Vindhyas, extends slightly to the region of southwestern part of Bihar as well. That is the region of Kaimur Hills. Then here again you have a very old landmass in the form of Bundelkhand, billions of years old, very old landmass. And the oldest fold mountains in the country in the form of Aravali Range. You basically have the Aravali Ranges, this particular area. Okay. Now it is also referred to as a residual mountain because most of it has been eroded. Right. Then here you have the continued presence of the Vindhyas and the Satpura range. In between the Vindhyas and the Satpura, you have the drainage of river Narmada through the Rift Valley. But river Narmada is not the only river which drains through Rift Valley. Please keep that in mind. River Damodar is also one of the major rivers which will drain through the Rift Valley system. Okay, so please don't restrict only river Narmada to the case of Rift Valley. Meghalaya Plateau is not the oldest. No, Meghalaya Plateau is not the oldest. It is the Chota Nagpur Plateau, which is amongst the oldest in the country. Okay. Now, then after that, you have the region of Baghelkhand. Extending across Madhya Pradesh and Chhattisgarh lies this plateau region of Baghelkhand. Then here you have the Ramgarh Hills, right? Then you have the Bastar Plateau. To the south of Bastar Plateau, you have the region of Dandakaranya. Here you have the Mahadev Hills, Ajanta, Satmala, and then Hari. So repeat this again and again, and that is sufficient for your mapping. Start from the Meghalaya, Shillong, Karbi Anglong Plateau, Garo Khasi Jaintia in the northeast. Then after that, come to the gap, that is the Malda Gap. It is also known as the Rajmahal Garo Gap. That is where you have the Rajmahal Hills in the easternmost extent, beyond which River Ganga takes a southern turn. Now, immediately next to the Rajmahal Hills, you have the Hazaribagh Plateau. Then you have the larger Chota Nagpur Plateau. As you move slightly to the west, you have the Kaimur Hills, which are an offshoot to the Vindhyan Range. Kaimur Hills, then to the south of it, in the region of Chhattisgarh and Madhya Pradesh, you have the Baghelkhand. Move further to the west, you have the Bundelkhand region. Move further to the west, you have the Aravali. Then come to the south, here you have the Malwa Plateau, right? Then after Malwa Plateau also has got flood basalt deposits and black soil in that region. Then after that you have the Vindhyas and the Satpura. Then further again going to the region of the Garjat Hills in Odisha. Then you have the Bastar Plateau. After that you have the Mahadev, Mikir, Ajanta, Satmala, Harishchandra range. Okay, so that is the case of Dandakaranya Plateau is basically to the region of southwestern. It is Dandakaranya will be somewhere here. Chota Nagpur is here. Okay, keep that in mind. West to east, I think we can take a look from the map itself, or do you want me to write it down? Please take a look at the map itself. Like, because if I write it down, why I'm not writing it down? I don't want you to rectify. Because is UPSC going to ask you this? Arrange this from east to west. No. UPSC is going to ask you a question which it had asked previously, that which of these shares the region between the region of Madhya Pradesh and Chhattisgarh. The answer was Baghelkhand. Then all the mnemonics, old auntie and all those kind of mnemonics that I saw, that will be something which you will still be trying to recall and you won't be able to find the answer. Okay. So please don't do that. There is a limit to the spoon feeding. After all, you want to become an IAS officer. So please keep that in mind. I want you to take a look into the kind of the map on your own as well. Okay. So basically, that is why I'm not writing it down. I have underlined it. I have repeated it. I will repeat it again. I will repeat it 10 different times, but I will not write it down for the basic purpose. I want to help you clear the examination. I don't want to cripple you so that you never clear the exam. Okay. Now, after this, basically, the region of the Western Ghats. Western Ghats, they are also what are referred to as the when you talk about the Western Ghats, also referred to as the Sahyadris. Right. So here basically confirm Bhadar. There is nothing known as Bhadar, Tarai, Khadar, and Bangar north to south. Just confirm. Okay, Babar. Babar, Terai, Khadar, and Bangar north to south. Okay, how many of us are interested in rectifying north to south and east to west? Please understand one thing, my dear. There is something known as logic. I want you to apply logic. I don't want you to throw logic out of the window. Okay, so understand one thing. Bhabar will always be almost the northernmost. Let's suppose this is River Ganga. Now there is something known as the Tarai belt to the south of Bhabar. After that, you will have Bangar. Then you will have Khadar. Again, you will have Khadar. Again, you will have Bangar. Right? So on both sides of the river, you will have Khadar and Bangar. So accordingly, how it fits your entire decorum of north to south, how it fits your decorum of east to west, please fit into this. Now, after this, I am getting a kind of an idea. Many of you will be acutely disappointed if there is no particular question of north to south and east to west, isn't it? Many of us are preparing for north to south questions. Last time UPSC asked these north to south questions was, I think, not after 2014, right? So that was 11 years ago. So that is good going. That is what I call as the application of logic. Anyways, so here, when we talk about the region of the Western Ghats basically they exist through the region of 6 states. I will write this north to south. Okay, Western Ghats passes through 6 states, starting from the state of Gujarat. Gujarat is to the north. North of what? To the north of Maharashtra. Maharashtra is to the south of Gujarat. Okay. All those who did not know this earlier, so now I hope you know. To the south of Maharashtra, you have the region of Goa. Then after that, the region of Karnataka. Karnataka lies to the south of Maharashtra and to the east of Goa. Then after that, it moves through the state of Kerala and then Tamil Nadu. Okay? These are the 6 states to which the Western Ghats does pass through. Okay? Now, north to south, east to west arrangement, howsoever you want to take a look into it, take a look into it. But Western Ghats, what is important, what I would want you to focus upon rather, is basically the fact that when you talk about Western Ghats are not mountains. These are what come under the category of escarpment. Escarpment. Okay? That is basically the Western Ghats. This is an escarpment. Escarpment is what? Created as a result of normal fault. As a result of normal fault. normal. Okay. Then Eastern Ghats is much more divided, much more subdivided. So in the case of Eastern Ghats, it is divided by the river systems of Mahanadi, Godavari, Krishna, Kaveri. So in the Eastern Ghats, you will have some of the ranges like the Nalamala range, Chevroy, Javadi. These are some of the ranges that you find in the region of the Eastern. Then comes the eastern coastal plains. They are much wider as compared to the western coastal plains. In the case of eastern coastal plains, they are again named differently as you move from north to south. In the case of eastern coastal plains, you will observe that the northernmost, they are known as northern sarkars. Northern sarkars. Right? Now, even within the region of the northern Sarkars, you have the Odisha coastline. Odisha coastline is known by the name of Utkal Coast. Then you have what is known as the Coromandel Coast. Right? Coromandel Coast, which we talked about, that receives rainfall only during the month of retreat of the monsoon and then the northeast monsoon. Okay? Western coastal plains are also subdivided. They are much narrower, but western coastal plains are also subdivided on a regional basis. You basically have the Kutch and the Kathiawar coastline, yeah, where it is broader. Kutch and Kathiawar coast, Kathiawar coast. Then after that, it gets very narrow, and that is the region of the Konkan coast. After that, in the region of Karnataka, it is also known by the name Kanara coast. And then in the southern part, it gets broader, where you have the low lying areas, where you have the backwaters and lagoons which get created. That is what is also referred to as the Malabar Coast. Because of the low lying nature of it, that is where the seawater enters inwards and creates the Malabar coastline, having a lot of these backwaters, which are also known as kayals. Now, then, when we talk about the islands, Andaman Nicobar and Lakshadweep are the major islands. In the case of Andaman Nicobar, you will observe that the 10-degree channel separates the Andaman group of islands from the Nicobar group of islands. The southernmost island is the Great Nicobar. Okay, so you have the Andaman group of islands, and then you have the Nicobar group of islands. Here you have the Sentinel Island. Sentinel Island has been in news again this year. After almost around 6 years, Sentinel Island has again been in news owing to one of the transgressions which have happened by a foreign tourist in that particular area. So keep in mind where these are located. So 10-degree channel separates Andaman group from the Nicobar group. When we talk about Lakshadweep, so Lakshadweep has got a lot of coral islands in formation. Now, in the region of Lakshadweep, you have the 9-degree channel. The 9-degree channel becomes instrumental in the region of Lakshadweep, separating one area from the other. Okay, so Minicoy, which is one of the major islands, lies to the south, and then you have Kavarati, Kilton, all of those which lie to the north of the 9-degree channel. So this is the case of physiography of India, right? I hope this is understood. I hope there is no particular doubt associated with this. Now, the rivers and tributaries, the river systems of India. Now, for your examination, which are the river systems that you should study? And which are the river systems that you should focus upon? So, there are seven such river systems that you should be focusing upon: Indus River System, Ganga River System, Brahmaputra River System, the Mahanadi, Godavari, Krishna, Kaveri. That's it. These are the only river systems that you should consider, along with the cities that lie on the banks. I will provide you with a list of all of them as well. After all, that is something that the PDF collectors will be very excited about. So, in the PDF that you will be able to download, you will get the list as well. So here, basically, the river system which is in news quite significantly right now is the Indus River system. Now, Indus River is one of those river systems which originate from the region of Tibet, closer to the Mansarovar lake, and it basically then drains to the northwestern direction. As it drains to the northwestern direction here, it is joined by the Himalayan tributary, both from the right bank side, mostly from the right bank side, less from the left bank side initially. You have the river systems like Gilgit, Shyok, all of them, Hunza, Shigar, Dras, all of them, they end up joining this. Now, this is basically then the one which enters into Pakistan. Now, it flows through the region of Pakistan and forms a large delta around the region of Sindh province, around the region of the Arabian Sea coastline before merging into Arabian Sea. Now, for the river Indus, you have the Himalayan tributaries which are definitely there. So, Shyok, Gilgit, Zaskar, Hunza, Nubra, Shigar, and Dras. But here, what is important is the left bank tributaries for Indus. Which are the left bank tributaries? They are also known by the name of Panjnath. That is five rivers, based after which the land Punjab has been named. Punjab, land of five rivers. You have Doab, land of two rivers. Similarly, you have Punjab, land of five rivers. So, Indus River system is in news. Indus River system is important this time. Okay. So, Panjnath, which are the Panjnath? Jhelum, Chenab, then after that, Satluj. Satluj also originates very close to the region of Mansarovar Lake. It enters India through the Shipkila Pass in the region of Himachal. Shipkila Pass, very important, very old pass, important for the trade and cultural ties as well. Then you have Ravi, and then you have Byas. These are your Panchnath. Now, in as per the Indus Water Treaty, Jhelum, Chenab, and Indus, they are considered to be the western rivers, where we have had earlier, as per the Indus Water Treaty, we had limited access. And eastern rivers is where we had complete access. Eastern rivers would constitute of Satluj, Ravi, and Byas. Right? Now, the origin, where each of them originate. So, Indus originates from the Bokharchu Glacier near Lake Mansarovar. Okay. Jhelum originates from Verinag Glacier and then drains through the fault zone, creating the Vuller Lake and so on. Chenab originates from the region of Lahore Spiti from the Baralacha Pass. As Chandra and Bhaga, they join together. Then Satluj originates from the Rakas Tal near Mansarovar. Ravi from the Kulu Hills near the Rotang Pass. And Byas from the other side of the Rotang Pass. So this is basically the origin of the various different important river systems. Then comes the Ganga River system. Now, last year UPSC had asked a question regarding the Ganga River system. Chances are it won't repeat it again this time, but if it repeats it again, so you should be able to solve it. Basically, the question which was asked was the tributaries which join River Ganga when. So, Ganga River system, first of all, in the region of Uttarakhand, it originates in the form of Alaknanda and Bhagirathi. Bhagirathi is the one which originates from the Gomukh glacier near Gangotri. It is joined by Alaknanda at the region of Devprayag. After that, it is known as River Ganga. Now, as River Ganga comes into the plains from the region of Haridwar, before that, in the region of Uttarakhand itself, it is joined by multiple smaller tributaries which eventually constitute River Ganga. And the confluences, they are also known by the name as Prayags. So Ganga is very famous for the Panch Prayags, which are present in the region of Uttarakhand. As it comes into the plains, one of the first streams that joins it, major streams, is Ram Ganga. Ram Ganga ends up joining it. Yeah. Then after that, as you can see, you have River Gomti. Gomti is the one which drains through the capital city of Lucknow. So, in the twin cities of Lucknow, Kanpur, as they are referred to, Kanpur is drained by River Ganga, Gomti is drained by, or Lucknow is drained by River Gomti. Both of them polluted. Gomti, much more so, but the pollution level is slightly coming down. After that, you have the massive and the mighty antecedent river in the form of Ghagra. Now, Ghagra River crosses through the region of the Himalayas and then joins River Ganga, the region around Bihar. Then after that, you have Gandak, Kosi, and then Mahananda. These are your left bank tributaries. So I can write it down that it is easy. So tributaries, basically, initially, when we talk about the left bank, the first tributary, that major tributary will be Ram Ganga, right? Then after that, you have Gomti, draining through the capital city of Lucknow. Keep that in mind. Then after that, you have Ghagra, then Gandak, then Kosi, then Mahananda. On the right bank tributary, the major river system that you have is basically River Yamuna. That is the major tributary that you have. So here on the right bank, you basically have Yamuna. Yamuna followed by the smaller streams like Tamsa and Son. Tamsa. Okay. Now, Son also has got a tributary in the form of Rihand, on which you have the very famous Rihand Dam. So basically, here you see on the map the presence of Panj Prayags, which together make up River Ganga. So in the case of Panj Prayags, you will observe that here Ala, the river Alaknanda originates from the region of Satupant Glacier near Badrinath. That is where Alaknanda does originate. It is joined by Dholi Ganga. Dholi Ganga is the stream which drains through the region around Joshimath, right? It is the stream where frequent landslides, avalanches, etc. keeps on happening. So Dholi Ganga joins Alaknanda at the region of Vishnu Prayag. So keep a track of and don't simply copy it, read it, close the notes, and then maintain it. So you have Dholi Ganga, confluence of or Vishnu Prayag, confluence of Dholi Ganga and Alaknanda. After that, it is joined, Alaknanda is joined basically by Nand Prayag, which by Nandakini, which joins it at Nand Prayag. Nandakini originates near the region of Nanda Devi. So that is where Nandakini ends up joining river Alaknanda at the region of Nandaprayag. Okay. Now, from the other extremities of Nanda Devi, you also have the genesis of the river that is known as the Pindar or the Pindar Ganga. It joins river Alaknanda at Karnaprayag. And after that, from the other side, it is joined by the stream Mandakini. Mandakini is the stream which drains through the region of Kedarnath. So that is where Mandakini joins Alaknanda at the region of Rudraprayag. Then after that, you will observe that it is joined by Bhagirathi at Devprayag. After that, as River Ganga. So again, revise it again. So you have initially Vishnu Prayag, where Dholi Ganga meets Alaknanda. After that, you have Nand Prayag, right, where Nandakini joins Alaknanda. Then you have Karna Prayag, where Pindar joins Alaknanda. After that, you basically have Rudra Prayag, where Mandakini joins Alaknanda. After that, Dev Prayag. These are the Panch Prayags that should be kept. And the tributaries, other tributaries, we have taken a look into. Yes, Prerag, they are. Now, the Brahmaputra river system. Now, when you talk about the Brahmaputra river system, basically, the Brahmaputra river, one of the most powerful rivers in the region of South Asia in terms of the volume of water carried, originates from the Chemyongdong Glacier, again near the region of the Mansarovar Lake. It moves across a very straight line in the Tibetan highlands. Then it takes a sudden southward syntactial bend around the region of Namcha Barwa. That is where you will observe it takes a southward bend. Now it enters into the region of Arunachal Pradesh in the form of very narrow but fast moving stream nonetheless. That is the case of Brahmaputra. There in Arunachal Pradesh, it is known by the name of Tiang. It is joined, it enters the plain area around the district of Sadia, where you have the very famous Dola Sadia Bridge. So, around the region of Sadia is where it enters the plains. And there it is joined by a tributary in the form of Lohit. Lohit is the tributary which joins that. After that, you will observe that Brahmaputra basically moves into the Assam plains and up till the region of Dhubri in Assam, that is where it is referred to as Brahmaputra. After that, it enters Bangladesh, where it joins with River Ganga. It is joined by various different left bank and right bank tributaries. So, amongst the right bank, Subansiri, Kameng, Manas, Tista, and Sankosh. Left bank, Budi Dehing and Dhansari, Dibang, Sikang, Lohit. These are your important tributaries. Okay. Mahanadi. Mahanadi originates from the region around Dhamtari in Chhattisgarh, around Raipur. Now, in the upper course of the river, moves through the kind of tough or the rough terrain region in the upper course. And here, River Mahanadi, if you will observe, in the lower course becomes very favorable for navigation. It used to cause immediate or humongous amount of floods in the region of Odisha. So Mahanadi would also be referred to as the sorrow of Odisha. Now, Mahanadi, basically, you will find that is joined by large tributaries like Sheonath. Amongst the largest tributaries, you have Sheonath, then you have Hasdeo, Mand, Ib, Ong, and Tel. These are some of the tributaries, basically, which are associated with Mahanadi. These tributaries of all these rivers are necessary to rectify? No. Some of the famous ones so that you are able to distinguish from the options. That's it. Don't end up rectifying all of these. Please do not rectify all of these. The easiest way to know this or easiest way to get a hold of this is basically by multiple repetition, where what you can do is you can draw the one like this. Let's suppose you have drawn Mahanadi like this. So the one which has joined the earliest, what is its name? That is Shivnath. Then after that, Hasdev joins in close quarter. Like that, you can have a kind of repetition, and that is the only way. But the purpose of it should be that if, let's suppose, UPSC has given a question that Indravati, Shivnath, Hasdev, which of these are tributaries of Mahanadi, you should be able to distinguish. Indravati is associated with that of Godavari, right? So that should be the purpose. UPSC is never going to ask you that stand in front of me and enumerate all the tributaries. So accordingly, you have to focus upon it. Okay. Now, then comes the case of Godavari. Now, Godavari, also known as Dakshin Ganga, right? So here, basically, if tributaries are asked of a main river and secondary tributary is given, yes, that would also be case of tributary, right? Only Prerak, that is the correct approach. The ones which are mentioned in current affairs, that is something which should be taken a look into. Okay, right. Very good, Megha. Now that you know this, fair enough. So that should help you in the exam also. Okay. Now, when we talk about Godavari, Godavari is a river which originates from Trimbakeshwar in the Nashik district. It is known as Dakshin Ganga, owing to the fact that it has got a drainage of around 1450 kilometers, and it is the longest stream in the region of Peninsular Plateau. So that is the case of River Godavari, right? Now, here, when we talk about River Godavari, it is joined by various different tributaries, both from the left bank and the right bank side. Among the right bank tributaries, the important tributary is River Manjra. River Manjra is what you can keep in mind. It is the important right bank tributary. Why? Because what is the reason for its importance? Because of the water storage structures which are present in that area. Which are the water storage structures which are present across River Manjra? Let me see. Singur, very good. And Nizam Sagar. Beautiful. So across River Manjra, you have Singur and Nizam Sagar. These are used basically to provide water to the otherwise drier regions around the area of Vidarbha region of Maharashtra and Telangana as well. These are your water storage structures. Water storage structures. Okay. Now, these are some of the tributaries of the river Godavari that you can take a look into. Pravara, then Purna, Manjra, that is the right bank. Penganga, Vardha, Venganga, the combined water of these, that is what is known as Pranhita. So Pranhita joins river Godavari from the left bank side. Then from the region of Odisha, Chhattisgarh comes the river Indravati, across which you have the Indravati Tiger Reserve as well, which is located in that. Then you have Maner and Sabri. These are the smaller streams which are associated with Godavari. Okay. Now, then Krishna river system. Krishna originates from which region? What is the point of origin? All those who have done the portion of mapping. Where is it that river Krishna originates from? Krishna river originates near Mahabaleshwar. Very good. So originates from the region of Mahabaleshwar in the Sahyadris and then moves to the east in the region of Bay of Bengal. Now Krishna is joined by various tributaries like Bhima, Ghat Prabha, Mal Prabha, etc. And mind you, at the time when River Bhima joins River Krishna, at that point of time, till that point of time, River Bhima is much longer than Krishna. But it is still referred to as the tributary of Krishna. Why? Because a river is regarded as a tributary not only because of its length, but also the channel gradient which is maintained, something that we have discussed in the sessions and the classes earlier as well, the concept of the channel gradient. So the river, when it is able to maintain its channel gradient, that is the one which is regarded as the main river, and the adjoining river is the tributary. Yes, correct, Manikandan. So that is the case of the river Krishna. You have Bhima, right? Then after that, you have Ghat Prabha, Mal Prabha, Tungabhadra. Tungabhadra in itself, you basically have Tunga and Bhadra coming together. Bhadra is where you have very rich biodiversity. The very famous Bhadra Tiger Reserve is there, rich in iron deposits in that particular area. It is also joined by River Musi. Musi is where, on the banks of River Musi, you have the region of Hyderabad. Musi is also in a lot of news this year owing to the kind of riverbank beautification which is being carried out in. And then you have one of the most disputed regions or one of the most disputed rivers in our country, that is the River Kaveri. River Kaveri, basically, you will observe that it is the one which receives rainfall both by the southwest monsoon as well as the northeast and the retreat of the monsoon. By the way, everyone who is present here, northeast monsoon and retreating monsoon, is it the same or is it different? What do you think? Retreat of monsoon and the northeast monsoon, is it same or is it different? Beautiful. Okay. It is different. Okay. Please understand. Just because the wind direction is the same does not mean both of them are same. Okay. After the retreat of the monsoon is complete, that is when the northeast monsoon sets in. Northeast monsoon sets in during which months? During the months primarily end November, December, January. Retreat of the monsoon is from September up till October, November. Okay? Right. So keep that in mind. After the retreat is complete, after the withdrawal is complete, after that, northeast monsoon is something which sets in. That is something I'm sure All of you who have attended the classes, you would have done that in greater detail. No doubt should be associated with that. Now, then we have the Kaveri river system. Kaveri river system here, the river in itself originates from the Brahmagiri hills, right? Brahmagiri hills. Brahmagiri hills in the region of Thalakaveri in the Kodagu district of Karnataka. That is where it originates. And basically, here it is joined by certain tributaries, very important tributaries like Kabini. Now, when you talk about the river Kabini, there is a dam which is built in the reservoir, which is built in that area. And Kabini has been in news this year. Why? Because of the frequent sighting of Black Panther. That is why Kabini has been in. Okay. So that is again something which is important, right? Yes, Manisha. That is why you have the entire region experiencing rainfall throughout the month of November, December, January to, through the entire months. Okay. Now, Radhakrishna, yes, you have the storage structures for the perennial river systems as well. For example, consider the case of, let's suppose, all the dams that you have, New Tehri Dam that you have, then a dam is coming across River Subanasiri, then you have consider the Bhakra Nangal. So you have storage structures which are built. You have multiple barrages, right? You have the East Ganga Canal. All these are the case of the water storage structures, all of them. Harike Barrage is close to the Bhakra Nangal project in itself, right? Okay. Now, here, in the case of River Kaveri, the Kaveri Delta or the lower stretches, they become very fertile. Historically, they have always been very productive in the sense of the agricultural crops which can be grown in the particular region. So this is a list of the rivers, the tributaries, and the associated regions, the banks of those rivers. So we'll do one thing. We'll basically end the session here today, right? Few portions are there in the PDF itself, which you can take a look into. Before that, let us attempt the question, the final question. After that, we'll end the session. So, which of these is a tributary of River Godavari? Do let me know. Vardha, Indravati, Penar, Penganga, and Sabri. What is the correct answer? Which is not a river system of or a tributary of River Godavari? Out of this, which is not the river of or the tributary of Godavari? Penar is not a tributary of Godavari. Other than that, all of them are. Okay? All the rest of them are the tributaries of River Godavari. Okay? So that brings us to the end of the session. Thank you for being so very patient. And I hope this session turns out to be helpful and productive. Now, I will provide you with the entire PDF of the session tomorrow. You can revise it from your end as well, which will include the lists of everything which is required for the prelims revision. And this is going to be more than sufficient for your examination. Okay. I hope that you have basically enjoyed the session and you have added to your already existent information set. If you have liked the session, please don't forget to click on the like, share, and the subscribe button. And whatever has been your feedback, whatever has been your experience, put that in the comment section below. Till we meet again, take care. Goodbye. Thank you.